Welcome to the course. I'm sure you're ready to get on to learning the Gradle techniques to move your project forward as soon as possible. So I'll keep this introduction brief by just saying, hello, I'm Tom, and I'm excited to join you on this journey of discovery into Gradle. Practically speaking, the course is organised into 5 chapters that are designed to be taken sequentially. By learning the fundamentals in the earlier chapters, you'll more easily be able to see what to do in any given situation when working with Gradle. As you progress through the course, what you learn in one chapter stacks on top of what you learned in the previous chapters, meaning that each new concept introduced makes sense. That's why in Chapter 1 you'll get a rapid introduction to the most important high-level concepts used to create basic Gradle projects. Projects, build scripts, tasks and plugins you may have heard of before, but here you'll see clearly how they relate to each other and why they're important. Everything else that follows is built on these foundations. Having created a basic Gradle project in a practical at the end of Chapter 1, in Chapter 2 you'll uncover how best to interact with it on the command line, then through your IDE. You'll get more of an understanding of what Gradle is actually doing when you execute tasks in a project by learning about the Gradle wrapper, the daemon and the build lifecycle. With the first 2 chapters serving as somewhat of an introduction, in Chapter 3 you'll learn everything you need to know about the Gradle build script. The build script can be written in either the Groovy or Kotlin languages. You'll learn both here, as well as knowing how to decide which is right for your project. We'll cover each aspect of the build script in enough detail that you're confident to use it. In Gradle there are sometimes different ways to get the same outcome, so you'll often see both the best way to do something as well as the legacy approach. This will help you understand existing projects that aren't necessarily up to date with the latest Gradle version. Brimming with this new build script knowledge, in Chapter 4 you'll learn how to configure your Gradle build to do everything you'd need to do in a Java project. And not just the fundamentals like building, running and testing your application, but also how to use features from the latest Gradle releases, such as specifying the Java toolchain version to ensure consistent results. By this point, you'll have confidence to start building or more effectively maintain Java applications with Gradle, but Chapter 5 shows you some common problems you might encounter with growing projects and how to fix them through effective project organization. You'll learn why you'd want to implement a multi-project build and how to do it, as well as how to reuse build logic between projects with custom tasks and plugins, promoting long-term maintainability. So that's the Gradle Hero course in a nutshell, but before we wrap up this lesson, here are some quick pointers to bear in mind as you go through the course. Some chapters have lessons which are specifically designed to give you practical experience in Gradle and are clearly labelled as such. These practical lessons often follow on sequentially from each other, so please make sure to complete these by following along with the video or the step-by-step instructions in the notes below the video. Many of these practical lessons have links to the Gradle Hero GitHub repository, where you'll find the code examples ready to clone and run. If you ever get stuck at any point in these practical lessons, you can post a question and I'll get back to you with how to proceed. In terms of the environment I've used to record these videos, I'm using a Linux-based terminal within Windows. Whether you're using Linux, Mac or Windows doesn't matter for the purpose of taking this course, but I wanted to let you know what my setup is to avoid any confusion during the lessons. When I execute commands on the command line, that's Linux via Windows subsystem for Linux. My file system is in Windows, and when I run IntelliJ IDEA, that's running in Windows. Speaking of which, the first part of this course is conducted very simply through the terminal and text editors. As the course progresses, the IDE becomes the primary editor for Gradle projects, but we'll still use both the terminal and the IDE for executing Gradle tasks. It's important to get an understanding of the Gradle fundamentals, and the best way to do that is via the terminal. As already mentioned, you can write Gradle build scripts in Groovy or Kotlin. Chapter 3 discusses this at length and shows you how each build script concept works with both languages. By default, in the rest of the course, when you see a build script, you can assume it's written in Groovy. Finally, I hope you can clearly understand my British accent. If you need to slow me down or speed me up, you can do that through the course player. I've chosen the words I use carefully to try to make myself understandable from wherever you are in the world. One thing you might notice though is my use of the word brackets, which I use to mean these types of brackets, also known as parentheses. If I'm talking about these brackets, I'll say curly brackets, or these ones, square brackets. With that said, that's everything you need to make the most of this course. What better way to start then by seeing why the Gradle build tool has made such a splash in the software industry and how it can help your project meet its goals. See you in the next lesson. Before jumping in to learn about the Gradle fundamentals in Chapter 1, let's assess the landscape and figure out what problems we're actually trying to solve with build automation tools. You'll see why Gradle is the best option for this compared to other tools, along with some real-world use cases from popular software projects. When it comes to writing software, what's left once it's been written, at least in the case of Java, is a collection of source files sitting in a repository that on their own have no real benefit. The goal is to have a deployed application in production fulfilling business requirements, but there's a massive gap to get there, the build gap. You've probably got a good idea of what's needed to bridge that gap. Compiling code, packaging the application, running and testing it, publishing, deployment, and more. Well, it turns out that this job isn't trivial. Over the years, we've seen several attempts to solve it in the Java space. First, there was Apache Ant, a build tool that allowed developers to define their build in XML. It assumed no project structure and had no dependency management though, which led to the creation of the more advanced Maven build tool. This was still XML-based, but favoured convention over configuration with inbuilt phases such as compile and install. It assumed a standard Java project layout and had a plugin system to cover a wide range of functionality. Given the convention over configuration approach, Maven's XML files were smaller than Ant's, but still verbose and cumbersome to maintain in growing projects. One other drawback was that Maven builds weren't as easily customizable as with Ant. Gradle entered the market in 2007, combining many of the good aspects of Ant and Maven. It took an opinionated view on how projects should be built, but with a high level of customizability. Gradle ditched the XML file for a developer-friendly Groovy, then Kotlin domain-specific language, or DSL. This led to much smaller configuration files and the ability to treat build configuration as code for improved flexibility and maintainability. Fast forward to today, and Gradle has gained a lot of momentum. According to the 2021 JVM Ecosystem Survey by SNCC of over 2,000 developers, 38% are now using Gradle and 76% Maven, and that's increasing year on year. With open source JVM projects on GitHub though, Gradle is now the most popular build tool. I can't predict what will happen in the future, but based on current trends, Gradle usage will continue to grow as more developers become aware of its benefits. Speaking of which, one other compelling reason to use Gradle is its team's focus on what it calls developer productivity engineering, or in other words, not only giving development teams the tools to build their application, but the ability to do so in the fastest, most efficient way. This leads to increased productivity since the time that developers are waiting for builds to complete decreases. It also makes developers happier since they can maintain their state of flow without long interruptions. Here's a quote that neatly describes this idea. In many industries, there are engineering disciplines dedicated to the practice of making production efficient and effective, such as chemical engineering and industrial or process engineering. They have their own degrees and are much respected within their broader field. Developer productivity engineering is of similar importance when it comes to the production of software. The software industry is at the beginning of this realization. It is a very exciting time to work in this area. And this is from Gradle's founder, Hans Doctor. This sentiment is reflected in many of the features that have been added since Gradle's initial release. One important example is the incremental build feature, which ensures that actions in your build, such as compilation, don't get rerun unnecessarily. Before we wrap up this lesson, let's take a look to see how Gradle has helped several open source projects deliver software more effectively. In January 2020, Spring Boot released version 2.3.0.m1, the first version to be built with Gradle rather than Maven. The team had decided to make the switch due to frustrations waiting for code to be built and tested after making changes. Their blog post on this topic states that after making the switch to Gradle, their local builds were on average 20 to 30 times quicker than with Maven, an amazing result. Other notable open source projects using Gradle are Elasticsearch, a distributed search and analytics engine, Kafka, a distributed event streaming platform, and finally Mockito, the framework of choice for mocking in Java unit tests. Hopefully you can see now that building software is complex, with several attempts by different build tools over the years. Gradle is the latest and I believe the best of these tools, with many improvements over its predecessor Maven in terms of maintainability and performance. Gradle has a strong focus on developer productivity, making it an increasingly popular build tool in general in the Java space, but especially in the open source community. Wherever you are on your journey with Gradle, you've made a great decision to discover this powerful tool that's becoming more and more popular as it helps real-world teams solve their build and productivity issues. It's time to move on to the rest of this course and learn how Gradle can help you and your team. See you in the next lesson. Welcome to this first chapter where you're going to get an overall picture of Gradle and how it works before jumping into the details in later chapters. We'll talk about the key concepts of Gradle, including the Gradle project, which is the container for your entire build, the Gradle build script, which describes what your build does, Gradle tasks, which are individual units of work added to your build script, and Gradle plugins, which are pre-packaged components which add helpful tasks to your build. These four concepts are really all you need to understand before creating simple projects in Gradle. In fact, while I've been talking, you may have noticed something happening in the corner of the screen. That's the 30-second Gradle project being built. Yes, it's so straightforward to get started with Gradle that you can create a project in 30 seconds. Don't worry about the details for now, as we're going to cover all the aspects of the 30-second Gradle project in this chapter. By the end of this chapter, you'll be able to create the project yourself from scratch. So, let's get started. The highest level concept in Gradle is the project. It represents the entirety of the application you're building. An example of a Gradle project you might have heard of is Spring Boot. Gradle builds the Spring Boot project into libraries that you and I can consume to build our applications. Before we get into a demo of a Gradle project, here's a quick overview. There's no limit to the size of a Gradle project. It could represent the smallest microservice you can imagine, which accomplishes a specific task, or a huge monolithic application. As you go through this course, you'll encounter several Gradle projects, starting off very simple, then growing slightly in size and complexity. Maybe you're wondering, practically speaking, what does a project look like? In its simplest form, it consists of a project directory, and within that, a single file named settings.gradle. Inside that file, we specify the name of the Gradle project. Once a Gradle project has been created, you can interact with it on the command line using the Gradle command, which we'll cover in detail in later lessons. For the 30-second project we'll be working on in this chapter, we have a project directory named 30-second project. In there is the settings.gradle file. And it contains the name of the project specified using root project.name equals and then the project name in quotes. With this file in place, we now have a Gradle project we can interact with. If I run the Gradle tasks command inside the project directory, we get a message, tasks runnable from root project 30-second project, and a list of tasks available in this project. This shows us that our project is properly set up and Gradle understands it. More details on all of this, including understanding what tasks are, is coming up in later lessons. Let's talk a bit more about naming your Gradle project. You can name it anything you like. It doesn't have to match the name of the project directory. Be imaginative. Strictly speaking, you don't have to specify a project name in settings.gradle, but it's a good idea because it means that if someone clones your repository into a differently named directory, the project name remains the same. Before you move on to the next lesson to learn about the project's build script, here's a quick note on terminology. If you hear me or others talking about Gradle builds, then it's just another way of talking about Gradle projects. They're the same thing. In the rest of this chapter, we'll build on top of the simple project we just created to explore more Gradle fundamentals. See you in the next lesson. As you saw in the previous lesson, a settings.gradle file in a project directory is all we need to create a Gradle project. At this point though, our simple project isn't much fun as it doesn't actually do anything. When you want to start doing stuff with your project, like actually building your application, that's when you need to add a Gradle build script. It contains the definition of how your application is going to get built. When it comes to writing your build script, you have a choice of languages. You can use Groovy or Kotlin. Since you define your build script as code, it's very flexible because you can write any code logic you want to do pretty much anything. You'll learn all the details of the build script in later lessons, including the differences between the Groovy and Kotlin syntax, and how to choose which one is right for your project. For now though, let's extend our 30-second project to illustrate a simple build script example. In our project, we'll create a file called build.gradle, and this will contain our build script written in the Groovy programming language. Inside this file, we can write any code that we want to. Don't worry if you're not familiar with Groovy, as you'll learn more about it later. But for now, we'll just use the println function, which prints the string you pass it. So I have a single line in my build.gradle, println, this is the 30-second project. If I run the Gradle command from within this project's directory, let's see what happens. Okay, it says, this is the 30-second project. Cool. Likewise, I could define some variables, a and b, and print out their sum like this. Now when I run the Gradle command, I get the output 5, which is 2 plus 3. That's very nice, you might be thinking, but I don't really want to have to write my entire build in code like this. No problem, because actually defining Gradle builds requires very little real coding. In Gradle, you reuse predefined tasks, plugins, and other elements which you configure together in the build script to seamlessly build small or large projects. Yes, by the end of this course, you'll be very familiar with all of these elements, and you'll have the confidence to apply them in your own projects. For now, just remember that the Gradle build is where your build logic lives. In the rest of this chapter, you'll be introduced briefly to two of the most important elements of the build script, tasks, and plugins, as we finish creating the sample project. Lastly, if you've used the build tool Maven before, you're right. The build.gradle file is the equivalent of Maven's pom.xml. As you'll find out soon though, Gradle's build script is a lot more flexible. See you in the next lesson. In the previous lesson, we learnt how you can define a Gradle build script in a build.gradle file, and in that file, write any code you want. To start creating useful Gradle projects though, we need to use one of the components Gradle makes available to us called the task. It represents a unit of work to get done in your build, whether that be copying files, compiling code, running tests, or anything else. Every task that's part of your Gradle build script can be executed from the command line. Your Gradle project could consist of many tasks, and it's up to you which ones you choose to run at any particular time. And as you may have already guessed, Gradle comes with many pre-packaged tasks which we can use directly in a build script to achieve specific outcomes. With these pre-packaged tasks, all the code logic to do whatever the task does has been written for us. We just have to define an instance of the task and configure it how we need it. If we need to do something that isn't supported by one of the pre-packaged tasks, we can always create our own custom tasks. So how do we use a task in our build script? To show you how, in our build.gradle file, I'm going to define a task to copy a file from one location to another. We'll use one of the pre-packaged Gradle tasks, unsurprisingly called copy. To define an instance of this task, we'll need only 4 pieces of information: the task name, the type of task, which is copy, the source file location, and the destination file location. Once the task is defined, we'll run it from the command line to copy the file. Let's go back to our project as we left it in the last lesson and create a new file to be copied called importantMessage.txt. Within there, we'll write this extremely important message. Now back in our build.gradle file, we're going to define our task. And first of all, I'm just going to remove all the code we wrote in the last lesson. And the syntax for writing tasks is tasks.register, and then the task name, which will be copy message, and then the type of task, which in our case is copy. And to define the source and destination file locations, we need curly brackets like this. And then we say from importantMessage.txt and into, and I'm going to use the syntax of, in double quotes, $builddir. And this is going to copy this file into Gradle's default build directory, which is just called build. And now we're going to run the copy message task from a command prompt within the project directory. So I'm just going to run Gradle copy message. And we've got a successful build output. And now we can see we have a build directory. And if I go in here, we've got importantMessage.txt. And this contains the extremely important message. And just to show that this is all working correctly, I'm going to delete the build directory. So that copied file has completely gone now. I'm going to run the Gradle task again. And now we've got the build directory again, and once again we've got the important message. In summary, that was a very simple use case of the copy task. It's very flexible though, and can be scaled up to copy whole directories, and even do token replacement within files. Don't worry about remembering the syntax of defining tasks right now, as we'll be covering it again many times in later lessons. Later on, you'll also learn about the other types of Gradle tasks, including the Java-related tasks, as well as creating your own custom tasks. For now, all you need to take away from this tasks introduction is that tasks do some work within your project. They can be pre-packaged tasks or custom tasks, and they can be executed from the command line. See you in the next lesson. In the previous lesson, you saw how to define a task in your build script and then execute it from the command line. The last fundamental Gradle concept I want to introduce you to in this chapter is the Gradle plugin. Plugins allow us to automatically add helpful tasks into our Gradle project using pre-packaged code that either us, Gradle, or some third party has written. And if you're thinking at this point that this diagram is starting to look a bit like a face, trust me, it was totally unintended. Before we get into a practical example, here are some key points to understand about plugins. Plugins automatically register tasks into our Gradle project, so we don't need to do that ourselves in the build script. That means you just have to apply a plugin and then you're able to execute any of the tasks it exposes. The tasks that plugins expose may be prepackaged Gradle tasks, like the copy task you saw in the previous lesson, or custom tasks written by the plugin author. Finally, plugins allow us to add rich functionality to our Gradle project, including multiple tasks which work together. To illustrate how to use plugins, we're going to make some more changes to our build.gradle file. You'll see that the syntax for applying plugins is simple, involving just a one-line change, and the plugin we'll apply is one of the most basic plugins called the base plugin. This plugin adds some additional tasks to our project which are common to many Gradle projects, hence its name. We'll be able to list these tasks using the Gradle tasks command, then we'll execute one of them. Now we're back inside the 30-second project directory as we left it in the previous lesson, and if we open up build.gradle, this is where we're going to apply the base plugin, and to do that we need to insert some space before tasks.register, as plugins need to get applied first, and we use the syntax plugins and then curly brackets and then ID space base in single quotes. And that's all we need to do to apply the base plugin. And now back at the command prompt, I'm going to run Gradle tasks. And we can actually see 3 additional tasks now listed under build tasks. The only task I want to talk about right now is the clean task. In the previous lesson, we deleted the build directory manually. The clean task made available by the base plugin allows us to delete the build directory automatically from the command line. As you can see right now, we do have a build directory inside our project directory. So back on the command line, if we run Gradle clean, that was successful. And back in our project directory, we now have no build directory. So just to show you that again, I'm going to run the Gradle copy message task we added in the previous lesson. That's created a build directory with the important message inside. And now, because we have the base plugin applied, I can run Gradle clean, and that's cleaned out the build directory. That doesn't exist anymore. And that's all down to the fact that we've applied the base plugin in the build.gradle, which has exposed the clean task. Later in this course, you'll learn about other plugins, such as the Java plugin, which add rich functionality to projects. For now, all you need to remember from this introductory lesson is that you can easily apply plugins to a build script, and plugins automatically add helpful tasks to your project. See you in the next lesson. Now it's time for you to bring together the Gradle concepts from the last 4 lessons, the project, the build script, the task, and the plugin, and create your first project. This is a practical lesson, which means you should do the steps I demonstrate in this video yourself to properly learn these concepts. You can follow along with the steps from this video, or find the full step-by-step instructions in the notes below the video. Let's get started. The situation is that we've been asked by a company that manages theme parks and amusement parks to help them with their software builds. As you go through this course, you'll encounter several situations where we'll be creating Gradle builds on this topic. For this lesson, the requirement is very simple. We have several files which contain descriptions for theme park rides. Since we may be running this build for different theme parks, we need to substitute in the correct theme park name in the description. Here's an example of the rollercoaster.txt file and what the generated file should look like, including the substituted theme park name. And of course, we're going to accomplish this important assignment using Gradle. Before we get into the implementation though, you need to get Gradle installed on your machine. Depending on whether you're working in a Windows, Mac or Linux environment, the procedure will be different. I've included full step-by-step instructions on what you need to do in the notes below. Once you've followed these steps, you know you're ready to continue if, when you open a terminal, type Gradle and hit enter, you see output like this. If you've got an error trying to run the Gradle command, make sure that the Gradle bin directory is in your path environment variable. If you're still having problems, you can start a discussion on this lesson and I'll give you a hand. Now that Gradle's installed, we can start creating the Gradle project. For this lesson, I suggest using a simple file explorer and text editor of your choice to fully understand the fundamentals. Later on in this course, you'll learn how to make the best use of Gradle IDE integration to increase your productivity. We're going to create all 4 fundamental Gradle elements already discussed in this chapter, including the project, the build script, the task, and the plugin. So let's start off by creating a Gradle project. Create a new directory wherever you like called Theme Park Rides. Go into that directory and create a new file called settings.gradle. Open it in a text editor and we're going to specify the name of the project using the syntax root project.name space equals space and then in single quotes theme park rides. Save this file and that's it. You now have a Gradle project. At the command prompt, navigate into your project directory theme park rides and then run Gradle space tasks. You should see the output tasks runnable from root project theme park rides. This means Gradle recognizes your project and you're good to continue. Now we're going to create the files for the theme park ride descriptions. Each description will have a token which during the build process will be replaced with the name of the theme park we're running the build for. Within the project directory, create a new directory called descriptions. Within descriptions, we're going to create a new file and it's going to be called rollercoaster.txt. Open that file and type in or copy the description from the notes below this video. Save the file. Notice the section between the @ symbols which says theme park name. This is the token which Gradle will recognize and replace with the actual theme park name. And we're going to repeat the same process for 2 more theme park rides. The first one is logflume.txt. Open it up and copy in the highly amusing message. And then lastly here, we're going to have teacups.txt. Open it up and copy and paste the message. With these files in place, now it's time to create the build script. Go back to the project directory and create a new file, build.gradle. Right now, this is an empty build script, and of course, on its own, it's not going to do what we need. We need our build script to create copies of the ride description files with the theme park name token replaced with the actual theme park name. To achieve this outcome in our build, we're going to use the copy task you were introduced to earlier. Not only does the copy task allow you to copy files from one location to another, it can also replace tokens in the files at the same time it copies them. So to define our task, we'll need to configure 5 pieces of information: the task name, the task type, which is copy, the source, the destination, and the token replacement name and value. So back in our build.gradle file, we're going to use the syntax you saw earlier to register this task. And it's tasks.register, and then in brackets, the name of the task, which is going to be generate descriptions, comma, space, copy, and then in curly brackets, we're going to say where we want to copy from. And in the previous lesson, you saw that we copied from a specific file. You can also use actual directories, and the task will copy all the files it finds within that directory. In our case, we have a directory called descriptions. And into, we're going to use the syntax you saw earlier in double quotes, $build_dir, which is the build directory, and /descriptions. And that's going to copy the description files it finds into the build directory, which is build/descriptions. And in order to do the token substitution of the theme park name token, we need to use an additional syntax, which is filter, and then in brackets, replace tokens, comma, space, and then tokens, colon, space, and then in square brackets, it's the name of the token, which is in capital letters, theme_park_name, colon, and then the theme park name in double quotes, which is going to be Grelephant's Wonder World. And then we need to close the brackets here. And the last thing we need to add here, because we're using the replace tokens filter, is an import statement right at the top, which imports the replace tokens filter. And that's everything we need to do the copy and theme park name token replacement. And if you don't want to type all this out yourself, you can just copy from the notes below the video. Execute the Gradle task by going to the command line and running Gradle space generate descriptions. You should see build successful, and you should now have a build directory, and inside here a descriptions directory, and in here the 3 different ride descriptions. So we've got log flume, and notice that in each ride description that our Gradle task has replaced the theme park name token with the actual theme park name. And that's the case for all 3 files. That's cool, but what if we want to see it working again from scratch by deleting the build directory? Rather than doing that manually, let's apply the base plugin so we can execute the clean task. Back in the build.gradle, after the import statement, we're going to use the plugin syntax, which is just plugins, space, and then in curly brackets, ID, and the ID of the plugin in this case is the base plugin. That's all we need to apply the base plugin. And then back on the command line, we're going to run Gradle space clean, build successful, and in our project directory we can see we no longer have a build directory. So once again we could run Gradle space generate descriptions, and we've got the build directory again with the descriptions. That's great, well done, you've managed to achieve the desired outcome. I know this is a simple example, but copying files and doing token substitution is common when building projects with Gradle, especially when handling property files. And you've just done this in a new Gradle project with a copy task defined in your build script, along with the base plugin for cleanup of the build directory. If you have any questions about this practical lesson, you can review the notes below or start a discussion on this page and I'll get back to you. That's nearly everything I wanted to cover in this chapter. You've had a quick introduction to the most important Gradle concepts, which are projects, build scripts, tasks, and plugins, by building your own project from scratch. To solidify your knowledge, a small quiz is coming up, followed by a short extension to this practical where you'll have a chance to explore another Gradle task type. See you in the next lesson. The last thing to do to finish off this chapter is an extension of the practical lesson from earlier. In that lesson, we built a simple Gradle project which copies theme park ride descriptions, replacing tokens with the theme park name. The theme park company we're working for have requested that to save precious time, we should automatically zip up these ride descriptions for later deployment to their production environment. This is a type of lesson which I call a challenge because I'd like you to attempt to add some new functionality yourself, referring to the Gradle documentation where required. These scenarios are important as they're similar to when you're working with Gradle projects on your own. To be clear about the end result, I expect to be able to run Gradle generate descriptions to generate the descriptions as we saw in the practical earlier, and then I want to be able to run Gradle zip descriptions, which should package all those description files into a zip file located at build/descriptions.zip. To get you started, here are a few pointers. you'll need to create a new Gradle task called zip descriptions. The task will need to be of type zip, and you can find Gradle documentation for this task type if you follow the link in the notes below. Last tip, here are the 3 properties you need to set on the task: from, destination directory, and archive file name. It's up to you to figure out the correct values. Okay, so now it's over to you. If you get stuck or you want to compare your working solution to mine, you can find a link to the sample solution GitHub repository in the notes below. You can also start a discussion on this lesson and I'll give you a hand. Good luck, and I'll see you in the next lesson. Welcome to the next chapter where you're going to become proficient at interacting with Gradle through the command line and IDE. Whether you're a developer, DevOps engineer, or any other role where you have to interact with Gradle, properly understanding that interface will allow you to do what you need to do more effectively. Specifically, by the end of this chapter, you'll have the knowledge and practical skills to be able to create projects using the Gradle command line wizard, interact with existing Gradle projects on the command line effectively, understand the Gradle project layout in detail, including what should go into version control, and know how to work effectively with a Gradle project in your IDE of choice. Before we kick off, there's another note on terminology to clear up. As you've seen already, you can execute tasks on the command line using the Gradle command. For the rest of this course, and in the Gradle documentation, you may see references to running or executing a build. This is just a shorthand way to say executing one or more tasks on the Gradle command line. So running a build and running some tasks you can think of as the same thing. See you in the next lesson. Up to this point, we've been manually creating the Gradle project files, such as settings.gradle and build.gradle. Fortunately, from now onwards, we don't have to do that anymore, as Gradle provides a mechanism to generate a project skeleton for us, using the Gradle init command. The best way to explain this is by actually doing it. So on the command line, we're going to create a new directory called Gradle init test and navigate into it. Now let's run Gradle init. We get asked a series of questions about the project we want Gradle to create. The first one is what type of project to generate. So let's select Basic by typing 1 and hitting Enter. Now we need to choose a build script DSL. DSL stands for Domain Specific Language, and it's a way of defining build scripts using Gradle specific syntax. What this question is really asking is, do you want to write your build script in the Groovy or Kotlin language? The difference between these options will be covered in later lessons, but for now, we'll select Groovy by typing 1 and hitting Enter. The last question here is to provide the project name, which defaults to the name of the directory. You can provide a different name, or just hit Enter to accept the default. It says Build Successful, which means we can now interact with this project. Let's run Gradle tasks. And it says Tasks Runnable from Root Project Gradle Init Test, and lists out all the tasks we have available. Let's see what files have been created here, which I'll do using ls as I'm in a Linux environment. We have 5 files which have been created, so let's step through them one by one. The build.gradle you should be somewhat familiar with from previous lessons. It's the main Gradle build script. Let's have a look inside, which I'll do using the cat command. There's just a comment saying that this file was generated by the Gradle init task, otherwise it's empty. The settings.gradle you also know about, and it contains the name of the project. Let's have a look inside. And we can see that Gradle has automatically set the project name for us. The last 3 files, one of which is the directory, are related to what's called the Gradle wrapper, which is a script we'll be using a lot from now on to interact with Gradle projects. You'll learn about the wrapper in detail in the next lesson. That's all you need to know right now about the Gradle init script. You've just learned how to create a basic Gradle project from the command line. We'll cover the other types of project you can create with Gradle init in later lessons. Feel free to try out the Gradle init command now, or wait until the practical at the end of this chapter. See you in the next lesson. So far in this course, we've been using the Gradle command made available to us by a local Gradle installation. In this lesson, you'll be introduced to a better way to interact with your project called the Gradle wrapper. The Gradle wrapper is a script that's added to your Gradle project and used to execute tasks. The three main advantages of this are that you don't need to have Gradle installed on your machine to execute tasks against your project, since the wrapper downloads Gradle from the internet automatically and caches it locally. The wrapper guarantees you'll be using the version of Gradle required by the project, preventing any version incompatibilities with your locally installed Gradle version. And finally, you can easily update the project to a newer version of Gradle and push those changes to version control to ensure other team members will use that new version. The good news is that it's really easy to add and use the wrapper script. In the previous lesson, we created a project using the Gradle init command, and it automatically added the wrapper for us. Let's go back into that project and look at the wrapper in a bit more detail. I'm going to use the tree command to see all the files, including those in subdirectories. We have 4 files here relating to the Gradle wrapper. Gradle wrapper.jar contains the code required for downloading the correct Gradle version from the internet. The Gradle distribution itself doesn't get stored in the project directory, but in the user home directory. You'll learn more about this in the next lesson. Gradle wrapper.properties is the configuration file which contains properties such as the distribution URL for the required Gradle version. Gradle W is a shell script for executing a Gradle build using the wrapper on Linux. And GradleW.bat is a script for executing a Gradle build using the wrapper on Windows. Let's take a quick look inside the Gradle wrapper.properties file using the cat command. The one property I want to highlight is the distribution URL, which points to a location on the internet where the wrapper downloads this version of Gradle, currently version 7.1.1. Like I said earlier, using the Gradle wrapper means that whenever we interact with the project, we're using this specific version of Gradle. So how can we execute tasks using the Gradle wrapper? Since I'm in a Linux environment, I just need to run /gradlew space the task name. For example, I can run /gradlew space tasks to see a list of tasks. Here's how that looks on a Windows command prompt. Just run gradlew or gradlew.bat space the task name. Note that if we don't specify any task, Gradle runs the default help task, which prints out some getting started information. If you're at all confused at this point as to when to use the Gradle wrapper and when to use the Gradle command, then the best rule of thumb is to always use the Gradle wrapper when interacting with the Gradle project. If you're working with a project which doesn't have a Gradle wrapper, then please add one as soon as possible. We'll cover how to do that in the next lesson. The only time you shouldn't use the Gradle wrapper and use the Gradle command instead is if you're working outside of a project. The main use case for this is when you run the Gradle init command to initialize a project. In this case, you're using your locally installed version of Gradle to initialize a project and generate a Gradle wrapper. The most important point to remember from this lesson is that you should always use the wrapper to interact with the Gradle project, to make sure you're using the version of Gradle which your project expects. The single scenario in which you don't use the wrapper is when running Gradle init to initialize a new project. See you in the next lesson. Now that you know how to interact with the Gradle project using the wrapper, in this lesson you'll learn how to manage the wrapper to handle several other use cases that might be thrown at you. First off, you'll see how to add the wrapper to an existing project rather than using Gradle init, then how to update the wrapper to use a different Gradle version. Finally, we'll unwrap the wrapper, see what I did there, to discover where it stores Gradle distributions on your local machine in case you ever need to do any troubleshooting. Let's get started. You already saw how to use Gradle init to initialize a project which automatically generates the Gradle wrapper for us. How, though, can we add the wrapper to an existing Gradle project which doesn't currently have one? For example, the theme park rides project you saw in the earlier chapter doesn't have a Gradle wrapper since we didn't use Gradle init to create the project. The wrapper can be added by executing the command Gradle wrapper. Once this is run, the same four Gradle wrapper files are added to the project, and we can run tasks using the wrapper. The next question is how can we update the wrapper to use a different version of Gradle? Remember that one big advantage of using the Gradle wrapper is that the Gradle version is fixed. If a new version of Gradle is released, you might want to change the Gradle version. First off, let's see what version of Gradle this project is currently on using /gradlew --version. It's on version 7.1.1. We can change the version by running /gradlew wrapper --gradle version equals then the new version. Let's change the version to 6.9, which in this case is a downgrade from version 7.1.1. Running /gradlew version again, we can see we're now on version 6.9. We can easily jump back to version 7.1.1 by running the wrapper task again. And now we're back on version 7.1.1. Note that the Gradle wrapper generated by both the Gradle init and Gradle wrapper commands use the same version of Gradle as your local Gradle installation. If you have an out-of-date version of Gradle installed locally, then as soon as you generate the Gradle wrapper, you can update it to the latest Gradle version. The last thing I want to show you is where the Gradle distributions get stored. Whenever you change the Gradle version to a version you haven't used before, the wrapper has to download the distribution from the internet. The first time you run a build, you might notice a delay as the new version is being downloaded. This only happens once though, as all the Gradle versions are stored in your user home directory under .gradle/wrapper/dists. Right here we can see all the Gradle versions that I've used in the past. Since I'm currently working in a project which uses version 7.1.1, if I delete the distribution using the rm-rf Linux command, and run /gradlew, it's downloading the distribution again from the internet. And if I run it again, it's fast because it's using the cached Gradle distribution. You just learned how to add the Gradle wrapper to a project and how to update it. That was a lot of information in these two Gradle wrapper lessons, but that's really everything you're going to need to know about the wrapper to work effectively with Gradle. See you in the next lesson. At this point, you should be familiar with how to initialize a Gradle project both manually by creating files and automatically using Gradle init. You also already know about many of the files and directories in a Gradle project. By the end of this lesson, you'll be totally comfortable with the layout of a working Gradle project, as well as what should be committed into version control and what should be ignored. As a quick recap, so far in this course you've learned about the following files and directories: the build.gradle, which contains the Gradle build script definition, the settings.gradle, which contains the project name, the build directory, where generated files and artifacts are created, and the four Gradle wrapper related files, gradlewrapper.jar, gradlewrapper.properties, gradlew, and gradlew.bat. We'll go into a lot more detail on the settings.gradle and build.gradle later in this course. Now though, let's talk more about the build directory. The The build directory is the default directory into which Gradle generates project artifacts. This could be compiled classes, jar files, or anything else that gets created as a result of running your Gradle build. This all goes into a specific directory so that it can be cleaned up easily and so we can make sure it's not committed into version control. If you've used Maven in the past, the Gradle build directory is the equivalent of Maven's target directory. The fact that the build directory is named build is a Gradle standard. It is configurable, but you should only change it if absolutely necessary. It's the best practice to reference the name of the build directory dynamically using builddir in the build script. You saw earlier that this can be used in a string like this. This is the full Gradle project layout. You're now familiar with all but 3 of these, so let's fill in the gaps. The .gradle directory is a project-specific cache generated and managed by Gradle. That's all you need to know about it, since it's used by Gradle internally. The optional build source directory is used to encapsulate build logic in a central place outside of the build.gradle. We'll cover why that's important and how it works later in this course. The optional Gradle.properties file is a list of properties specific to this project. It can contain either built-in Gradle properties to control your build or your own custom properties. More on these in later lessons. When it comes to committing your project into version control, all these files and directories should get committed except for the .gradle and build directories. It's important they all get committed since they contain the full description of your Gradle build, and the wrapper-related files allow anyone that checks out this project to immediately interact with it. The .gradle and build directories are transient directories that get created as a result of running a build, and therefore shouldn't be committed. You can add them to a .gitignore file to ensure they don't end up in version control like this. In fact, this file is even automatically generated for you when you run the Gradle init command. Before we finish, and to avoid any confusion, it's worth noting that these files and directories we're talking about are Gradle specific and apply to any type of Gradle project. Of course, you'll have other files and directories in your project, such as Java source files, HTML, CSS, or whatever else is relevant to your project. For example, if you're working with a Java project, then Gradle expects a particular project layout, which you'll learn in full in a later chapter. So you just learned the full Gradle project structure, which should help you immediately feel at home working in any Gradle project. See you in the next lesson. Now it's time to get a lot more comfortable interacting with Gradle on the command line. Later in this chapter, you'll learn how to use Gradle within an IDE, but to properly understand Gradle, it's important to know some key command line options. After all, any IDE integration is just a wrapper around the command line. By the end of this lesson, you'll know how to use more of the Gradle inbuilt tasks which come with every Gradle project, like the tasks task and the wrapper task you saw in earlier lessons. Run multiple tasks within a single Gradle command. Specify a project's default task to run when no Gradle task is provided. Do more with less typing using abbreviated task names. And use some of the most important command line options, like those which help you get more detailed log output from Gradle. Let's start at the top then and explore more of the standard Gradle tasks. Here we are in the Gradle init test we were using earlier in this chapter. And to see what tasks we have available, we're going to run /gradlew space tasks. And by the way, from this point onwards, I'll just say GradleW and the task name rather than /gradlew space, because I think you know what I mean by this point. So here are all the default tasks which come with this empty project, and some of them you've already seen. For example, init we know is used to initialize a new Gradle project. Wrapper is used to either create the Gradle wrapper script or update the version of the Gradle wrapper. Help is the default task. So we've seen before that if we run just Gradle W, without specifying a task, it runs the help task. And of course, the tasks task is what we use to get this output we're seeing right here. Another task we haven't seen yet is projects. So it says here it displays the subprojects of the root project. Let's try this one out. So it's just telling us that our root project is called Gradle init test and that we have no subprojects. This might be more useful when we get into multi-project builds later on. You may have noticed that right here we have tasks that fall within two particular groups. So we've got build setup tasks and help tasks. These are two separate groups and each task is assigned a particular group. I'm going to navigate back to the theme park rides with zip project that we saw in the previous chapter to illustrate what I mean. And you may remember that we added two custom task definitions, one for generate descriptions and one for zip descriptions. But if we run Gradle W tasks within this project, you'll see that there's no sign of these tasks in this output here. And the reason for this is that these tasks haven't yet been assigned a group. If you want to see all the tasks which haven't been assigned a group, we just need to run Gradle W tasks and we pass the -- all option. And right here we've got a list of other tasks and within there we can see generate descriptions and zip descriptions. If, for example, we wanted to assign generate descriptions to a specific group, we just have to edit the build.gradle. And the syntax we use is group and then the group name. And we can also provide a description for our task. And that's description and then the description name. So let's run Gradle W tasks again without the -- all option. And now you can see we've got a new group, theme park tasks, and it contains the generate descriptions, and that task now has its own description. So now that you understand how to discover the tasks available in a Gradle project, let's see what different ways we can run them on the command line. So for example, we know that we can run the projects task, but within a single command we can also run as many tasks as we want. So we could run projects and help together. So that's given us the output from projects followed by the output from help. They're run in the order on which they're specified. A more useful example of this is the generate descriptions and zip descriptions tasks. Rather than running each task separately with a different Gradle command, we can now combine them. In the next chapter, you'll learn a better way to do this using task dependencies, which means that generate descriptions will be run automatically when you run zip descriptions, without you having to remember to add it to the command line. And that's what this error is telling us here. We'll cover how to fix this later. During the Gradle wrapper lesson, you learned that if we run Gradle W without specifying a task name, Gradle by default will run the help task. That's the default behavior, but it can be easily customized to whatever task or tasks you want. For example, you could set the most commonly run task in your project as the default. Let's set the default task in this project to generate descriptions. So in the build.gradle, we just need to say default tasks and then a list of the task names. And now if we run Gradle W, that's no longer running the help task, it's running generate descriptions. A really useful productivity tip is to use the so-called abbreviated task names when running tasks on the command line. It works like this. You only need to provide just enough of the task name so that Gradle can determine what you're looking for. For example, Gradle WH is enough for Gradle to know that it needs to run the help task. For camel case task names, you can use the first letter from each word. For the Generate Descriptions task, the abbreviated name is GD. If there's a clash with other task names, Gradle will tell you what the candidates are, and you just need to provide more of the task name to find a unique match. The last thing to cover in this lesson are the command line options. These are flags you can apply when you're running the Gradle command, normally starting with a single or double dash. There are 54 options available, most of which you fortunately won't need to know about to still work effectively with Gradle. Let's cover a few of them right now. The most important one, I think, is --help or -h, which prints out a list of all 54 command line options. If you know this option, you know all of them. Note that the --help option is different to the help task. Another very useful command line option is --info or -i, which sets the log output to info, giving you a lot more detail about what's happening in your build. So normally when we run the Generate Descriptions task, we don't get much output apart from Gradle telling us that the build was successful. If we provide the info option, you can see we've got a lot more output here telling us what's going on at each stage of the build. And when you specify a command line option, you can put it either before or after the list of tasks, and Gradle will still pick it up. The final command line option to cover at this point is --console, which lets you change the format which Gradle outputs text. The options are plain, auto, rich, and verbose. The default is auto, which means Gradle detects how it should output text. Normally this means that you get color output and a dynamic bar at the bottom which shows you what Gradle is doing right now. You can try out these different options to see what effect they have, but I often set the console to verbose, which makes it easier to see what Gradle has done during your build once your build is completed. Normally when we run Generate Descriptions, we just see build successful, but if we run with --console equals verbose, it tells us what tasks have been executed. Later on, you'll learn how to set this permanently using a Gradle properties file. As we go through the rest of this course, we'll uncover more of the most useful command line options. You now know the most important ways to interact with Gradle on the command line. The key points to remember from this lesson are the list of Gradle tasks is grouped. Tasks which aren't in a group can be found with a --all option. The Gradle command can take 0, 1 or multiple task names. Gradle by default picks the help task, but you can change this to whatever task you want. You can save time and your fingers by using abbreviated task names. And Gradle has many command line options which you can list with --help. And just as another reminder, remember to always use the Gradle wrapper when interacting with a project. See you in the next lesson. In the previous lesson, you learned how to execute tasks on the Gradle command line. There's actually quite a lot going on up to and including the point of the task actually being executed. This complete process is called the Gradle build lifecycle. It consists of 3 different phases, and executing tasks is only one of them. The other 2 phases are initialization and configuration, and they happen before task execution. Knowing at a high level about the 3 build lifecycle phases will help you work more effectively with Gradle. Specifically, you can more easily diagnose build issues if you understand in which phase the issue is occurring. You can apply performance improvements to your build, such as ensuring the configuration phase is as efficient as possible. And many of the Gradle best practices and the documentation will make more sense with this knowledge. So let's run through each phase one by one, starting with initialization. And the initialization phase is the easiest to understand. It's where Gradle figures out what projects are going to take part in the build. All of the Gradle projects we've worked with so far in this course are just a simple single project, but with Gradle you can have multi-project builds. We'll cover this in detail later on, but for now you just need to understand that whether your Gradle project consists of one project or a project with many sub-projects, it's during the initialization phase that Gradle determines this. Practically speaking, this phase is where Gradle executes the settings.gradle file, which you learnt earlier can be used for setting the project name. This file is also where any sub-projects are listed, so during the initialization phase, Gradle figures out all the projects involved in the build along with their names. The next phase is configuration. It's where Gradle learns about all the tasks in your project. In fact, this is where all the build.gradle files of all projects are executed. The build.gradle file is actually a configuration of your build. When this file is executed, it means that Gradle is building an in-memory model of your project, ready to actually execute tasks in the next phase. So the next phase is execution, which is where Gradle figures out, based on what you passed on the command line, which tasks will be executed. Even if you've asked Gradle to execute a task, it doesn't always do it since it knows not to execute a task again if nothing has changed. This is the incremental build feature. And in this phase, Gradle goes ahead and actually executes the tasks. Then that's your build completed. It's important to understand the difference between the configuration and execution phases. During configuration, the build scripts are executed, creating a model for Gradle to understand your project. During the execution phase, it's the tasks themselves that are executed. Let's see a quick demonstration of all three phases in action in a real Gradle project. Here we are back in the Gradle init test project we used earlier, and we're going to add some logging to make it easy for us to see the different build lifecycle phases when we execute a task. First off, we're going to edit the settings.gradle. And settings.gradle is executed during the initialization phase, so I'm just going to add a println statement saying initialization phase. Now we'll edit the build.gradle. And this file is executed during the configuration phase of the build, so I'll add a println statement saying configuration phase. Now we also want to print some output during the execution phase, which means that we need to add a task which will actually get executed during that phase. Now one way we can tell Gradle what we want to do during the execution of our task is to use this doLast syntax. And anything between these curly brackets is the action which gets run when this task is executed. We'll cover this doLast syntax in more detail in later lessons, so don't worry for now. So when this task is executed, we'll print execution phase. So now if we run this task, and in this output we can clearly see the three different phases of the build lifecycle: initialization phase, configuration phase, and execution phase. Let's jump back to the theme park rides project to explore another way to look at the Gradle build lifecycle. Earlier in this chapter, you learnt about the --info option, which logs output at the info level. Let's run the generate descriptions task with --info. Interestingly, this log output is actually grouped by the three different phases. So first up here, this log output is during the initialization phase, where it's working out what projects take part in the build. This log output is the configuration phase where build.gradle gets executed. And lastly here is the execution phase, where we can see details of the generate descriptions task. And one thing you might have noticed is that next to the task name here, it says up to date. And this is related to the incremental build feature I mentioned earlier. It means that this task isn't getting executed again because Gradle knows that it's already been run and nothing else has changed. If we run a clean first, this time the task isn't marked as up to date and it's actually executed because Gradle knows that it needs to regenerate those files. Another way to see this without the info flag is just if we run generate descriptions. It says one actionable task, one up to date. So Gradle didn't actually run generate descriptions this time. If we run clean and run generate descriptions again, now it says one actionable task, one executed. So because we cleaned the build directory, Gradle worked out that it had to run generate descriptions again to copy those files into the build directory. We'll cover all this in a lot more detail later on, but I just wanted to mention it here in case you're wondering what these things meant. The key points to take away from this lesson are that there are 3 phases in the Gradle build lifecycle. The build lifecycle will come up again and again in the rest of this course, so remember that the initialization phase works out what projects take part in your build. The configuration phase executes all your build scripts and creates a model of your project. And the execution phase executes tasks based on what you passed on the command line. See you in the next lesson. A very important feature, but one that normally works in the background without you noticing, is the Gradle Daemon. A daemon is just a background process which you don't interact with directly. The Gradle Daemon is a Java process that continues running between build executions. Every time you run any Gradle command, by default it will be using the Gradle Daemon to actually run the build. The reason this exists is mainly for performance. By reusing the Gradle Daemon between build executions, we can benefit from faster startup due to not having to wait for the Java virtual machine, the JVM, to start up, using in-memory caches of projects, files and tasks, and JVM runtime code optimizations. As Java code is executed again and again, the JVM figures out ways to optimize it. Interacting with the Gradle Daemon isn't something you'll do every day, but knowing it's there will help you diagnose any issues you come across. There are a few simple commands you can use to help understand how the Gradle Daemon is running on your machine. Here we are back in the Gradle init test project, but these commands will work from any project. So let's say we wanted to execute the default task, and there's nothing in this output that tells us anything about the Gradle Daemon, but we have the -- status option, which gives us information about any running daemons. So in this output, we can see that I have 2 daemons listed. The first one has a status of idle, which means that it's not currently doing any work and it could potentially be used for a build. And under info, it says 7.1.1, which is the Gradle version that this daemon is tied to. And this is the daemon that was just used to run the default task within this project. I also have another daemon which has the status of stopped, which I stopped earlier on. So if we wanted to stop all the Gradle daemons, including this daemon in the idle status, we just need to use the -- stop option. Now if we run -- status again, we can see that both of these daemons are stopped. They won't be used for any builds from this point onwards. So let's once again run the default task. And we can see in the output at the top here that it says starting a Gradle daemon. So because there were no daemons available, there were no daemons in the idle status, it had to start a new one. So now when we run status, we've got 3 daemons, one of which is in the idle status. So when we run the default task again, that reuses the same daemon. Now, one other option that's interesting is the -- no - daemon option, which forces your build not to use a daemon. Now, if we look at the performance of this, we can see that this build executed in 3 seconds. If we take that option out, which means that we're going to use an existing Gradle daemon, we can see that this build is a lot quicker. So it's running in about 700 milliseconds as opposed to 3 seconds. And hopefully with this simple demonstration, you can see the benefit to reusing the Gradle daemon between executions within your project. And it's worth mentioning that the Gradle daemon is enabled by default, and the recommendation is to always use the daemon in all environments to benefit from the performance improvements. See you in the next lesson. Let's talk about how to make the most of the integration between IntelliJ IDEA and Gradle. And in this lesson, I'm going to be using IntelliJ IDEA 2021 and Gradle version 7. And first off, we're going to talk about how to import and create Gradle projects in IntelliJ IDEA. And the first scenario is where I have in my local file system a project that I want to import into IntelliJ IDEA. So here I've got the Gradle init test project that we looked at earlier, and I want to import that. This is the IntelliJ IDEA homepage, and we can go to Open, select the directory, so navigate to the directory, and then just select that and hit OK. And IntelliJ is now importing this project as a Gradle project. It knows it's a Gradle project based on the files that it finds within there. And now we know that this has been imported as a Gradle project because on the right-hand side here, we have this Gradle panel, and we've got a list of tasks. So that's been imported. The other way to reach this option is by going to File, Open, and then just select a project and hit OK in the same way. Another scenario might be where you find a Git project that you want to import directly into IntelliJ IDEA. Here's a project. I'm going to copy the Git URL. And then from the welcome screen, I can go to Get from VCS, paste in the URL. You can provide whatever directory you want to, and hit clone. And once again, IntelliJ IDEA is automatically recognizing the fact that this is a Gradle project. It's imported that project, and on the right-hand side here, well, once it's finished importing, we're going to see the list of tasks available. There we go, here's all the tasks. So we know that's imported successfully. And the other way to access this option is by going to File, New, Project from Version Control, and then likewise just paste in the URL there. Another scenario is where you have a project in IntelliJ IDEA and it's not currently a Gradle project, but you can convert it to a Gradle project or you can import a Gradle project from a directory. So as an example, here is the Gradle Hero project, and within these directories I've got different Gradle projects. So Theme Park Rides, this is a Gradle project. And all I need to do here is click on this build.gradle, right click, and scroll down to import Gradle project. And now that I've done that, we have the Gradle panel here, and here's my Theme Park Rides project, and I have a list of tasks. Now let's move on to creating a new project in IntelliJ IDEA. And from the welcome screen, this is very simple. We just go to New Project. And on the left, we have different types of project. We've got Gradle selected by default. You can pick a Java SDK for the project. And you can select additional libraries and frameworks. We're going to untick all of them. But depending on what you choose here, this will set your project up in a different way. And we'll cover the Java option in a later chapter. Hit Next. Give the project a name, hit Finish. And now IntelliJ IDEA has automatically created this Gradle project for us. It's got all of the essentials. It's got the build script here. It's got a settings.gradle with the project name specified. And it's also got the Gradle wrapper. So we've got the Gradle W, the Gradle w.bat, and the files inside the Gradle/wrapper directory. And of course, IntelliJ recognizes this as a project. Here we have the list of tasks. And this is a little bit like doing Gradle init, although there are some small differences. But this is a good way to get started with a project, and from this point you can start editing this project how you need it. And the other way to create a new project is by going to File, New, Project, and then you've got the same dialog here you can run through. Now let's talk about editing your project, so making changes to the build script of your project. And we're going to use this project that we just created using the new project dialog. So now I can edit the build.gradle with some degree of autocomplete and syntax highlighting, which is a lot nicer than editing using a tool like Vi, which I was using earlier. So as an example, let's create a copy type task. And as soon as I start typing here, task, I can see what options I have. So I want to say tasks.register. And I'm going to copy the settings.gradle into the build directory. And here it's suggesting what I can use for build.dir. And you can see that IntelliJ IDEA has highlighted certain aspects of this build.gradle. Now, one thing you might have noticed as I've been making changes is this small dialog in the top right-hand corner. And if we hover over this, it says load Gradle changes. So whenever you make a change to a build.gradle, you have to load changes. It doesn't automatically reload. And you can do that by clicking this button. Or if we make another change, the shortcut is Ctrl-Shift-O. And what this is actually doing is IntelliJ IDEA is creating its own in-memory representation of your build. And it uses that for things like populating the list of tasks here. So here we can see my special copy. If I rename this task, you can see that this hasn't automatically updated. I have to click this button. Now there is an option here. If we click this tool icon, auto reload settings, we can change this to reload project after changes in the build script, change it to any changes. Hit OK. And now if I make a change here, that got automatically reloaded and we can see the new task. So that's a nicer way to do it, I think, when you're working with small projects. The reason IntelliJ IDEA has got this set so that you have to manually re-import is that if you have a large project, it can be quite slow if you're making lots of changes to have to keep waiting for it to import. But if you're working in a small project, then certainly go ahead and change this auto reload setting. For the rest of this course, though, we'll leave it on the default setting. So when you hear me say load Gradle changes or reload Gradle changes, that's what I mean. Now let's cover how IntelliJ IDEA can help us with running tasks. And you've already seen that we have the list of tasks on the right-hand side, this Gradle panel. The other way to access this panel is if you hit Control-Tab in Windows and then press G. And here we have the list of tasks by group. So the new task that we added, special copy, is within the other group because we didn't provide a group name. And it's really easy to execute a task, you just double click. So in the output down here, it's telling us that this was successful. That's what the green tick means. And we can see the actual text output, but also IntelliJ parses the output to some extent, and it's telling us how long it took to execute this task. Another way to run tasks is by clicking this Execute Gradle Task icon. And here we can type whatever we want. So we could say special copy, and we can also pass whatever options we want. So if I just type --, it's actually suggesting what I might want to do here. So I want to run with --info. So I can just select that and hit enter. And now we can see that we've got info level output here. So you can customize this without having to revert to the command line. Another option you have is that as soon as you run a task, it adds a run configuration at the top. And we can edit that. And we can pass whatever arguments we want. So I could say, I want the --info, okay. And now when I run this run configuration, it's running with info. Lastly, if you want to, you can actually select multiple tasks from this list. So earlier in the chapter, we ran projects and help. So I can select those two tasks, right click and hit run. So that's a few different ways of running tasks in IntelliJ IDEA. I think the most straightforward one to start with is just finding the task you want to execute and double-clicking it like this, and then seeing the output. Next, let's see how we can configure Gradle within IntelliJ IDEA to work exactly how we want it to. And we need to go to IntelliJ Settings, which we can get to by File, Settings, or Control-O-S on Windows. And under Build, Execution, Deployment, Build Tools, we have a Gradle option. So here is the JVM setting, Gradle JVM. This is telling IntelliJ IDEA what JVM we want to use to run Gradle. So currently it's set to 11. If I wanted to, I could set it to 15, 16, or even download a different JDK from the internet. Another setting that's worth knowing about is this build and run setting. So normally when you build your application in IntelliJ, it uses Gradle, and likewise it uses Gradle for running tests. You can change that behavior here to use IntelliJ rather than Gradle. And it says here, in a pure Java or Kotlin project, building and running by means of the IDE might be faster thanks to optimizations. So if you're working in a really large project and you're having performance issues, that's really the only time you should consider changing this, but it's something that's worth knowing about in case you come across this situation. Lastly here, let's talk about how we can debug our build scripts by making use of the IntelliJ IDEA debug features. So here I am in my build script, and it's very easy to add a breakpoint. If you're familiar with IntelliJ IDEA, you know it's just by clicking on the left. And now from the Gradle panel, I just want to right-click the task I want to run. So special copy, right-click, and hit debug. And now this line is highlighted blue, which means that execution has been paused. And we've got the standard debug features, like we can see the stack here. We can see what variables we have available. So for example, here we have the special copy task, and we can see all the information about that. So I'm not going to go into any more detail than this, but it's good to know that this option is available. And later in the course, we'll be exploring how we can debug applications that are started by Gradle, for example, Java applications. But that's all you need to know for now about how to use Gradle from IntelliJ IDEA. So I'll see you in the next lesson. So you can commit as much as possible of this chapter to memory, we're going to recreate and build the Gradle project you created in the practical in the first chapter, only this time using Gradle init, the Gradle wrapper, and the IDE. We'll also commit everything into version control. If you're thinking that this sounds like a lot of work, don't worry, it's really quick and easy using Gradle init. This is a practical lesson, so please do the steps in this video yourself to properly learn these concepts. You can follow along with the video or find the full step-by-step instructions in the notes below. In the previous practical lesson, we created a Gradle project called Theme Park Rides, which had a single Generate Descriptions task to copy files from the description directory into the build directory. It also did token substitution in those files to insert the theme park name. Here's the plan for this lesson. Step 1 is to create a new project using Gradle init from the command line. We'll then edit the build.gradle to add the Generate Descriptions task, as well as add the descriptions directory and files. Next, we'll initialize the project directory as a Git repository. Then we'll check that .gitignore is set up correctly so that only the required files and directories will be committed. We'll commit the project to a local Git repository. Finally, using the IDE to open the project, we'll run the task using the Gradle wrapper. Let's get started. We're going to start off at a command prompt, but we're going to end within the IDE. So the first thing to do is to create a new directory for this project. The previous project was called Theme Park Rides, so let's call this Theme Park Rides from scratch. So I'm going to use mkdir to create a directory in Linux. Let's cd into that directory. And now we're going to run Gradle init to initialize this directory as a Gradle project. We want to create a basic project, so press 1 or just hit enter to accept the default. We want to use the Groovy DSL, so that's 1 or just hit enter to accept the default. And lastly, yes, we want the project name to be Theme Park Rides from scratch, so just hit enter. We now have a Gradle project, and if we run ls to inspect the files, we've got all the files that we expect from a Gradle project. We now need to add the description files and the task to this project. So to save time, we're just going to copy it across from the project in the previous chapter. So I'm going to use cp-r in Linux to copy the description directory from Theme Park Rides into Theme Park Rides from scratch. And now we have descriptions. And likewise, we're going to copy the build.gradle using cp. And if I look at the contents of build.gradle using cat, we can see that we have the generate descriptions task. So let's check that everything's working by running the generate descriptions task. And of course, we'll be using the Gradle wrapper. So that's /gradlew in Linux or gradlew.bat in Windows. Space. And let's use the abbreviated task name for generate descriptions. So that's lowercase g, uppercase d. That's successful. Now let's inspect the contents of one of the generated files. And we can see that this file contains the description of the roller coaster with a substituted theme park name. So everything's working correctly. Now that we're happy with this project, we want to commit it into version control using Git. If we try running git status within this project, it fails because this project hasn't yet been initialized as a Git repository. To fix that, we just need to run git init. And if we run git status again, that looks better and it's listing out all the untracked files we have. So let's add all of these to be staged to be committed using git add dot. And now when we run git status again, these are the files we're going to commit. And it includes the build.gradle, the descriptions directory, the Gradle wrapper files, and the settings.gradle. That looks good. And the first two files we have here are hidden files, which we didn't see before because we were using ls, but they're actually generated by Gradle init. The first file, .getAttributes, is there to ensure that the line endings in gradlew.bat are in the correct Windows format. And the second file, .gitignore, is there to ensure that the generated Gradle directories are not committed into version control. Let's have a look inside there. And we can see the two directories are .gradle and build. So if we run ls-la in Linux to show all files and directories, including those that are hidden, we do see that we have a .gradle directory and a build directory, but the .gitignore file added by Gradle init is set things up so that we won't commit that into version control. So let's double check with git status. And this looks good, so let's go ahead and commit this using git commit -m and then a message. Running git status again shows that everything has been committed. The last thing to do here is to open this project within your IDE of choice. I'm going to be using IntelliJ IDEA. So from the welcome screen, I just need to hit open. Select the directory Theme Park Rides from scratch. Hit OK. And now IntelliJ IDEA has successfully opened this as a Gradle project. And over here, we can see that we've got a list of tasks. Within the other group of tasks, we do have generate descriptions. So let's go ahead and run this by double-clicking. And of course, within the IDE, it's a lot easier to browse files. So we can look in the build directory. We've got the descriptions directory, and we've got the descriptions for all the different rides here. And if we want to double check, we can open up the build group here and run clean. That's removed the build directory. Now let's run generate descriptions again. And here are our descriptions. Well done, good work. You've now got practical experience of creating a new Gradle project using Gradle init, interacting with that project using the Gradle wrapper and abbreviated task names, making sure that only the correct files get committed into version control, and lastly, opening the project in an IDE and executing tasks from that IDE. For any questions about this practical lesson, you can check the notes below, or start a discussion on this page and I'll give you a hand. That's nearly the end of this chapter. You now have a solid understanding of how best to create and interact with a Gradle project. Coming up is a short quiz to help you retain as much knowledge as possible. See you in the next lesson. Welcome to the next chapter, where you'll dramatically increase your effectiveness with Gradle by getting a full understanding of the build script. Everything up to this point has been somewhat of an introduction, but now we're going to go into a lot more detail about the build script languages and its different features. By the end of this chapter, you'll be comfortable with the most relevant concepts of the Groovy and Kotlin languages relating to writing Gradle build scripts. You'll know about the advantages and disadvantages of each language, helping you decide which one to use for your Gradle project. And you'll find it easier to read and understand build scripts with full knowledge of plugins, tasks, dependencies, repositories, and more. Before we kick off this chapter by diving headfirst into Groovy and Kotlin, let's review what we know about the build script so far and add a bit more high-level detail. First off, when we talk about the build script, this means the build.gradle file, or as you'll see soon, the build.gradle.kts file in Kotlin. They're the same thing, and you'll hear me use these terms interchangeably. As you learnt in the first chapter, the highest level Gradle concept is the project. Everything that happens in the build script is actually configuring this project. The project is a Java object, and anything we do in the build script manipulates that object, whether that's applying plugins, creating tasks, or anything else. You also know that there are 3 phases in the Gradle build lifecycle: initialization, configuration, and execution. And the build script is executed during the configuration phase. And you've got practical experience with 2 important components of the build script, the task and the plugin. A task is an action that happens in your build, and it can be executed directly from the command line. A plugin is pre-packaged code that is applied to a Gradle project to automatically make some specific tasks available. For example, the base plugin adds the clean task, which you can run to delete the build directory. We'll get into the other components of the build script later in this chapter. See you in the next lesson. There are certain Groovy language features used by Gradle to make writing build scripts simple and concise. In this lesson, you're going to learn more about those features, since understanding them will help you to make sense of Gradle build scripts. By the end of this lesson, you'll understand the most important language features of Groovy and how Groovy differs from Java, how Gradle uses Groovy to create the Gradle DSL, and how this DSL is really just a collection of methods you call from the build script, which let you manipulate the project object. Let's start at the top then and see what makes Groovy so groovy. Groovy is a JVM language. This means that Groovy code gets compiled to bytecode just like Java. For this reason, you can write standard Java code in Groovy and use all the standard Java libraries. That said, there are some important differences with Java, including that Groovy is dynamically typed, meaning that when you declare a variable, you don't have to say what type that variable is. You can also reassign a variable to another type. Here's an example Groovy script, and we're defining a variable, which we do using this def keyword. Def myvar is the variable name, and we're assigning it 123. That's an integer. And then we print the value of that variable. And then after that, you can see we're reassigning that variable to a string hello. So that same variable was assigned to an integer, and now we're reassigning it to be a string. And then we're printing that value. So if we run this script, we get the expected output showing that this variable was assigned an integer and a string. So that's the dynamic type feature of Groovy. This is in contrast to Java, which is a statically typed language where you always have to assign a type to a variable. And Groovy aims to be less verbose than Java. For example, semicolons at the end of lines are optional. So in this same example, if we wanted to, we could put semicolons at the end of each of these lines, but generally we leave them out because it's less verbose that way. One barrier people have learning Gradle is making sense of how Groovy is used in the build script, or in other words, understanding the Gradle DSL. Sometimes it can seem like magic, especially if you're used to more restrictive languages like Java. We'll now run through 4 key Groovy language features that are used heavily by Gradle. For each feature, you'll see how it's used in plain Groovy code, what the Java equivalent is, if there is one, and how it's used in Gradle build scripts. And the first Groovy language feature is that you can run code as a script. You don't have to define everything as a class like in Java, although you can if you want to. So in plain Groovy, this is how this looks. We can just use the println method to print a string, and we can do that directly within a single file which gets treated as a script. We don't need to wrap it in a class, which is what you'd have to do in Java. So this is how that looks in Java. We have to create a class, and then within there we have a main method, and then within that main method we print the string. That's a lot more verbose. And the equivalent in the Gradle build script is the same as Groovy. So of course we can write Groovy code in the Gradle build script, and we can call the println method. So the Gradle build script is really just a Groovy script that gets executed. The second language feature is that brackets are optional if the method has at least one argument. So here's an example of how that looks in Groovy. We've got a method that gets defined using this def keyword. The method name is multiply. It takes 2 parameters, first and second, and it prints the value of first multiplied by second. And later on we call this method, and you can see we're calling it with the values 2 and 3. But importantly here, we don't have any brackets. And this is a nice feature that makes things a little bit less verbose if we can leave out the brackets. And here's an example where we have a method that has 0 parameters. It just prints a string. And when we call this method, we do need to use brackets because we can only leave the brackets out when there's 1 or more arguments to that method call. And here's how the multiply example would look in Java. Don't worry about the detail, but the important thing to note is that, of course, in Java we have to provide brackets whenever we call a method. And in the Gradle build script, this language feature is used all over the place. And here's an example you saw earlier where we're applying the base plugin to our project. And we use this syntax id space and then the string base. And this is actually calling a method called id, and it's passing it an argument of base, the string. And once you understand that brackets are optional, it makes the build script a little bit easier to understand. So here's the same example in IntelliJ IDEA. And if I control-click on ID here, it takes me through to the method definition, and we can even see that this method takes as its parameter a string. So often in the Gradle DSL, you're just looking at methods being called and arguments being passed to those methods. And in this example, we could just as easily put brackets around this, and that would also be valid Groovy syntax. The next important Groovy feature is that it supports closures, and you can think of a closure as a block of code that can be passed around like a variable and executed at a later point. So here's how that looks in Groovy. We're defining a variable, call me later, and we're assigning it the value of a closure. And to define a closure, we use this curly bracket syntax, and anything within those curly brackets gets executed when the closure gets executed. So later on, we call the closure, so we just use the variable name and then brackets, and that executes that closure. And that's going to print the string ring ring. Here's a slightly more complex example to show how we can pass closures around. So we have a method pickupPhone. It takes a name, which we're expecting a string, and it takes phone noise, which is a closure. And then it executes that closure. And then after that, it prints a string using some concatenation. So afterwards, we call the pickupPhone method. We pass it a string. And as the second argument, we pass a closure in curly brackets. And within that closure, it's going to print the ring ring string. So let's try executing this example in IntelliJ IDEA. And the output here is ring ring, hello Tom here. So closures is quite a powerful language feature that Groovy supports. And the 4 main points to remember about Groovy closures are that you define them using curly brackets. You can execute them at any point, you can assign them to variables, and you can also pass them as method arguments. And there's no direct equivalent in Java. And in Gradle, it makes heavy use of Groovy closures. And in fact, almost all the times that you see curly brackets, that's actually a closure. So here's an example of tasks.register. We're passing a task name. And then we're also passing a closure. And it's a block of code that Gradle is going to execute at some later point. And here's that example in IntelliJ IDEA. And I just want to show you that if I control-click on register of tasks.register, we can actually see the method definition here. So register takes a string and it takes an action. And this is actually a closure. So often when you see this kind of syntax and you see curly brackets, that's just passing a closure to a method. And the last important language feature here is that if a closure is the last argument of a method, it can be passed outside of the brackets, if brackets are used. So in plain Groovy, this is how it looks. So we've got the same pickup phone method that we had before, but when we want to call this method, we open the brackets, we pass the first argument, which is Tom, we close the brackets, and then outside of that, we pass the closure. And this is a nice language feature that makes things a little bit more readable, since we don't have to have the bracket at the end of the closure. And of course, there's no equivalent in Java because Java doesn't have closures. And in Gradle, this is used all the time. So this is the same example that we saw before where we're registering a task called closures in action. And the way that this is generally done in Gradle is that the closure is passed outside of the brackets. So here's the same example open in IntelliJ IDEA, and we can see that the closure is passed outside of the brackets. But I could just as easily change this syntax. And now we have the closure inside of the brackets, and this is perfectly valid syntax to use in the Gradle build script. But generally, to make things a little bit less verbose and more readable, we put the closure outside of the brackets. And I've included all these code examples in the notes below. Feel free to try them out yourself until you're comfortable how these language features work. And if you're working with IntelliJ IDEA, you'll be happy to know that there's a very easy way to run Groovy code from within that IDE. You just go to Tools, Groovy Console, and then you can type any Groovy code you like. And then just hit the Run button, and that executes the code. So that's a nice way to try out these language features for yourself. And of course, within any Gradle project, we can write Groovy code within the build.Gradle. And in this case, we've added some code to build.Gradle. And if we execute any task, that will also execute this code. And here's the output. And remember that if you want to get more familiar with what's happening under the hood, you can control-click to see the definition of any methods that are being called here. So the key points to remember from this lesson are the Groovy language features used in the Gradle DSL, and that's that you can run code as a script, brackets are optional, Groovy supports closures, and you can pass closures outside of brackets. And if you understand these language concepts, you'll go a long way to understanding the build.Gradle. And the last point to make here is that Gradle has supported Groovy build scripts from the beginning. They still are supported, and they will be for the foreseeable future. Of course, now you also have the option to write build scripts in Kotlin, which we'll explore in the next lesson. See you there. As well as its Groovy DSL, Gradle also has a Kotlin DSL. This means that build scripts can be written in the Kotlin language. The good news is that there aren't many differences between the Groovy and Kotlin DSLs. If you can read and understand Groovy build scripts at a high level, you should also understand those written in Kotlin, and vice versa. That said, when writing build scripts, it's more important to know the differences. So in this lesson, you'll learn the main differences between the Kotlin and Groovy languages, most relevant to Gradle build scripts, how to create Gradle projects with Kotlin using Gradle init, how to configure tasks and plugins in your build script with Kotlin. You already know how to do this in Groovy, so you'll get up to speed with the Kotlin equivalents. and how working with Kotlin within IntelliJ IDEA is a better experience than with Groovy. Let's kick off with a high-level overview of Kotlin. Kotlin was developed by JetBrains, the people behind IntelliJ IDEA. They've taken a lot of inspiration from Groovy, which is why Gradle has been able to keep so many similarities between the Groovy and Kotlin DSLs. Kotlin is also a JVM language, just like Groovy. There are more differences between Kotlin and Java than Groovy and Java, but you can still call Java code from Kotlin. The main difference between Kotlin and Groovy is that it's a statically typed language, meaning variables must be declared of a specific type. On the other hand, Groovy variables can be dynamically assigned a value of any type. From a build script perspective, this is good news, since the code becomes less ambiguous and errors are detected earlier during compilation. In Kotlin, strings must always be defined using double quotes, whereas in Groovy, you can either use single or double quotes. And a note on terminology: in Java and Groovy, methods are called methods, whereas in Kotlin, they're called functions. Now let's look at some actual Kotlin code. We'll make a Kotlin versus Groovy comparison of the 4 language features discussed in the previous lesson. In these examples, syntax highlighting has been removed so we can more easily compare Kotlin to Groovy. First up, we can also run Kotlin code as a script. That's useful because the build.gradle is also a script. No differences here with Groovy, except Kotlin requires double quotes to define a string. With Kotlin, brackets are not optional. Here's the same multiply function from the previous lesson. In Kotlin, we define the function with the fun keyword instead of def, and must provide a type for the parameters. When we call the function, we must include the brackets. However, there is one exception to this rule, which we'll explore in the 4th language feature. Just like in Groovy, Kotlin has closures, although in Kotlin they're called lambda expressions. You can see that the syntax is very similar to Groovy, the only difference here being that we define a variable in Kotlin with the val keyword. In Kotlin, you can also pass a closure outside the brackets when calling a function. Here's the example from the previous lesson, written in Kotlin. You can see that we pass the lambda expression to the pickUpPhone function in the same way as in Groovy. If you're passing a closure to a function that has a single parameter, you can leave out the brackets. This is an exception to brackets not being optional. These are all reasons that Kotlin build scripts look so similar to those written in Groovy, as you'll see shortly. Now that you've got a better idea of the differences between Kotlin and Groovy, let's see how to create a Gradle project in Kotlin. We're going to create the theme park rides project from chapter 1 from scratch using the Gradle init command. So here we are on the command line, and we're going to create a new directory for our project, theme park rides Kotlin. Now we're going to cd into that directory. And now let's start the project setup wizard with Gradle init. And this is going to be a basic application. We'll press 1 and hit enter. And importantly here, we're going to select Kotlin. So I'm going to type 2 and hit enter. And we'll accept the default project name, Theme Park Rides Kotlin. So hit enter. Now the first thing we're going to do is run the ls command to see what files have been created. And you may have noticed here that rather than having a build.gradle and settings.gradle, we have a build.gradle.kts and a settings.gradle.kts. And the KTS extension stands for Kotlin script. And this is how Gradle is going to know that this is a Kotlin project and not a Groovy project. Everything else remains the same. We've got the same Gradle wrapper scripts that we had with Groovy projects. And we can start running tasks against this project. So let's run the tasks task to see what tasks we have available. And that runs fine. So at this point, we need to start editing this project so that we have the generate descriptions task that's going to copy descriptions and do the token substitution. First off, let's copy those description files from the theme park rides project we looked at in chapter 1. I'm going to use cp-r to copy that directory into this new project. And now we're going to open this project in IntelliJ IDEA. And from the welcome screen, we just click on Open, select the project directory and hit OK. And now that IntelliJ has imported this project, if we click on the Gradle panel, you can see that we have all the tasks available. So this has been imported fine, and it's a Kotlin project rather than Groovy. So let's go ahead and edit the build.gradle.kts. We're going to apply the base plugin, which, if you remember, we added to our project so that we can clean the project. And then we're going to add the generate descriptions task. So let's open the build script. I'm going to delete the contents of this file. Now to apply the base plugin, we start off with the same syntax. It's plugins and then curly brackets. And this is using the feature I just mentioned where normally we have to provide brackets when calling functions, but in this case we're calling a function only with a closure, so we can leave out the brackets. And then to apply the base plugin, all we have to do is type base. And this is some syntactic sugar added by Gradle, which is very helpful because it's a compile time check. If, for example, I was to try to apply a plugin that isn't a built-in Gradle plugin, for example, Tom Gregory, we get a syntax error because that isn't a valid plugin. So that's one very useful change as compared to the Groovy DSL. Now we need to register this task, and the syntax starts the same, tasks.register. Now we need to provide the type of the task, which is copy, and we do that in less than and greater than symbols. And then in brackets, we provide the name of the task, remembering to use double quotes. And then outside of the brackets, we can pass a closure. And this is where we configure the copy task to how we need it. So we need to say from descriptions into the build directory /descriptions, and then we need to do the token replacement configuration. A difference here is that when we specify the from directory, we need to remember to include brackets. And same for the into directory. And just like with Groovy, we can use this template substitution inside a string. Now we need to do the filtering, and the syntax here is significantly different. First off, we'll import the replace tokens task. And now we use the syntax filter, replace tokens, :class. That's how you refer to a class in Kotlin. And then to provide the actual tokens to replace, so we need to replace theme park name with Grelephant's Wonderworld, we use this syntax here. So you can see that it's quite different from the Groovy syntax. We don't need to know all the specifics, but it's just a different way of creating a map in Kotlin. So now let's re-import this project in IntelliJ IDEA given our changes. So click this button here. And if we go to the Gradle panel, we should see our new task within the other group. Here's generate descriptions. Let's run this by double-clicking. Now we should have in the build directory descriptions, and we can see that each description, the theme park name has been substituted correctly. And because we applied the base plugin under build, we also have the clean task. Let's run that by double-clicking. That's deleted the build directory. Let's rerun generate descriptions. And here are our descriptions again, all good. Now, one nice thing about using the Kotlin DSL within IntelliJ is that it seems to work a lot better for autocomplete. So, for example, in this context, within this closure, it knows that this is a copy task. For example, if I start typing in and hit Control space, it's giving this suggestion here of include, which is a property you can configure on the copy task. And I might want to use this include here, which takes a string. And I might want to say ****star.txt to include all text files. Let's compare that with the Groovy version, which I've also got open here. If I type in and then Control space, I get very generic suggestions. It's not specific to the fact that I'm within the copy task here. And I think this integration is very helpful, and it's probably no surprise given the fact that firstly, Kotlin is a statically typed language, and secondly, JetBrains are the ones behind this language, so the IntelliJ IDEA integration is very good. The key things to take away from this lesson are that Kotlin and Groovy share many language features, such as closures. This means that the Gradle Kotlin DSL isn't too different from the Groovy version. In Kotlin, brackets must be supplied when calling functions, and strings are always defined with double quotes. Kotlin is a statically typed language, which means that errors are caught earlier on during compilation rather than during execution. And Kotlin build scripts are easier to edit in IntelliJ IDEA thanks to the improved autocomplete integration. Maybe you're feeling overwhelmed at this point with lots of information about Kotlin and Groovy. Don't worry, because in the next lesson, you'll get some suggestions to help you decide which option is best for your project. See you in the next lesson. Now you've got an idea of the differences between the Gradle Groovy and Kotlin DSLs, maybe you already have a preference. If not, here are some things to consider to help you decide which option to go for on a new project. Note that it's only the build script that needs to be written in Groovy or Kotlin. Your actual application can be in whatever language you like. Also, as you'll see later, functionality can be extracted out of the build script. The extracted logic can remain in Groovy or Kotlin, or can even be converted to Java if you prefer. All this means that the scope of what needs to be written in Groovy or Kotlin might be smaller than you think. The other big thing to realize is that you can migrate your build script between Groovy and Kotlin. If you choose one language and later realize you'd prefer the other, that's not necessarily a problem. As you've seen, there are many similarities between the two Gradle DSLs. Gradle even has helpful documentation on how to migrate from Groovy to Kotlin, and I'll include a link in the notes below. One consideration might be the language that you're writing your actual application in. If it's written in Kotlin, then it probably makes sense to write the build script in Kotlin too. In general, having consistency across a project helps a lot. Consider what skill set your team currently has. Find out whether the people who will be maintaining the build scripts already have experience in Groovy or Kotlin. You might want to decide based on wanting to improve knowledge in that area. For example, if you know you want to get into mobile development in the future, then maybe Kotlin is the right choice since you can write Android apps with it. Hopefully that's given you some ideas. If you still don't have a preference, don't worry, because in the rest of this course, you'll see many of the examples in both Groovy and Kotlin. Having knowledge of how both Gradle DSLs work will be valuable for you, especially if you work with many different Gradle projects. Finally, don't feel as though you need to be an expert in Groovy or Kotlin to be an effective Gradle engineer. Working with the Gradle DSL requires only a limited knowledge of these languages, which you now have based on what you've learnt in this chapter so far. Let's move back to learning more about the Gradle build script, so see you in the next lesson. In the next few lessons, we're going to look at all the different ways you can configure a project within the build.gradle or build.gradle.kts. To start with, there are several important properties of a project that can be useful to set up depending on what you're going to be doing with your Gradle build. One way to browse these properties is through the Gradle API documentation for the project class, which I'll include a link for in the notes below. Any methods starting with set are properties we can configure. In this lesson, you'll learn how to set the project description, group, and version, and understand what they're for. Right here, I've got a brand new Gradle project. It's using the Groovy DSL. And over here, I've got another Gradle project. It's using Kotlin. Now, before we look at how to set these project properties, one thing to note that there's another way to browse the project, and you can do that from the build script itself. So if we just type project, the IDE has recognized this, and I can control click on project, and it takes me through to the class. Now in IntelliJ IDEA, you can press Ctrl F12 to see all the methods. And if I type set, I can see all the set methods available here. So this is another option from within the IDE instead of having to browse to the documentation online. The project description provides a description used when you execute the project's task. In the Groovy DSL, we set it like this. And now if we re-import this project by clicking this button, we can go to Help Tasks, double-click Projects, scroll up, and here we've got the description. So it says root project buildscript demo - just a demo. In the Kotlin project, we use a different syntax. We have to use equals. And of course, double quotes. Let's re-import the project and run the project's task. There we go, just a demo. And this might not be that useful for a single project, but when you've got a multi-project build, so you've got a root project with many sub-projects, this can become very useful to be able to see what those different projects do. One other thing I want to stress here is that anything you do within the build.gradle is operating on the project class that we just saw. So here we're calling description, and by default that's operating on the project class. So if I control click on this, we can see it's calling setDescription. This is the equivalent of us typing project.description. So that's actually what's happening, but within the Gradle build script, you can use the shorthand format that always operates on the project. Next property is the group that the project belongs to. This should be unique, and you normally use something describing your organization, like com.tomgregory. It's used as an identifier when publishing artifacts. So let's set that in the Groovy DSL. And in the Kotlin DSL. Now in the next chapter, you'll learn about publishing Java projects with Gradle, and the group gets used during that process. For example, it's used in the POM XML file you can see here. And finally, we can set a project version. You may have noticed that when you create a new Gradle project with IntelliJ IDEA, it already does this and sets the version to 1.0-snapshot. And the version of the project is also used when publishing artifacts. So in the Groovy DSL, we just say version 1.0-snapshot. And here's how that looks in the Kotlin DSL. And in the POM XML file, the version also gets used, and here's how that looks. And you'll also see in the next chapter with the Java project how the version is also used in the artifact file name. So you've just seen how to set the description, group, and version for a Gradle project in both Groovy and Kotlin, and you've got an idea of what they're used for. See you in the next lesson. In Chapter 1, you were introduced to tasks. You learned that they perform some action within your build and are executed by passing their name on the command line. You also got practical experience defining a copy task to copy files from one location to another. Now we'll explore in much more detail the task APIs to help you effectively define and configure tasks in your project. At this point, it's important we make a distinction between a task class and a task definition. A task class is a blueprint for a task. For example, the copy task, which comes pre-packaged with Gradle, contains all the code logic required to copy files from one place to another. The task class itself might live in the Gradle source code, your own project, or a third-party plugin. It depends on the task. To actually use the copy task within a project, we have to do two things. First is to define an instance of that task class with a task name. The second is to configure that task instance in such a way that it does what we need it to do in our project. In the case of copy, that means telling the task where to copy files from and into. To be as concise as possible with these concepts, I'm going to explain some task-related vocabulary here, which will be used consistently throughout this course. A task class is a blueprint for a task containing the actual code to do the things that the task needs to do. Pre-packaged tasks are task classes that come with Gradle by default, like the copy task. You may see these called built-in tasks in Gradle documentation, but in this course we'll say pre-packaged tasks. When we define a task in our build, we're creating an instance of that task, or in other words, a task definition. And not every task definition needs to be based on a task class. You can define a task and specify what it does at the same point. These types of tasks are called ad hoc tasks. And in contrast to ad hoc tasks, task definitions based on a task class we'll call, rather unimaginatively, class-based tasks. As we run through some examples in the rest of this lesson, these terms will start to make more sense. Let's now explore how to define a task in a Gradle project. There are two main approaches which you'll see. We can use the tasks.register syntax you've already seen and used. This is the recommended approach for the best performance since it avoids unnecessary configuration. And you've already seen and used this syntax in the Groovy DSL in the theme park rides project to create the generate descriptions task. And likewise in Kotlin, you're now familiar with this syntax. In Kotlin, there is an alternative syntax we can use. And this registers the task in much the same way, but if you need to refer to this task later on, you can use the generate descriptions variable that's been created. Another way to create a task is by calling the task method on the project class. This was the original approach to define tasks in Gradle, but it has now been replaced with tasks.register. It's best to avoid this as it's not as performant, and you'll see exactly why in the next lesson. But it's good to understand this approach since many builds still use it. So in the Groovy DSL, let's change generate descriptions to use this second approach. And when I reload this project, we still have the generate descriptions task here. And that's still working as expected. And here's how that looks in the Kotlin DSL. And once again, let's reload this project. And generate descriptions is still here and it's working. For both of these approaches to defining tasks, we can create class-based or ad hoc tasks. So let's create an ad hoc task using the tasks.register syntax in the Groovy DSL. So the syntax is very similar, we just leave out the task class. And within this configuration closure, we can configure the doLast closure. And let's print hello with an exclamation mark for effect. Reload the project. And there's our ad hoc task. Let's do the same thing in the Kotlin DSL. Same syntax, no task class. And then the same as Groovy, doLast and println hello. And that works as expected. So just to reiterate, at the top we've got a class-based task, generate descriptions, and at the bottom we've got an ad hoc task, say hello. The first one is using the legacy project.task syntax, and the second one is using tasks.register. So let's change this one back, and now they're both using the recommended tasks.register syntax. For a task to do anything useful, it needs to be configured. We do this by passing a closure which calls methods or sets properties on the task. You don't have to do this at the same time as you define the task, as you'll see in the next lesson. What you put inside the task configuration closure depends on the type of task you're defining. For example, you already saw that when we configure a copy task, we can set the from location, into location, and set up filtering, all within the configuration closure. Whatever type of task you create though, there are some common properties you can always configure. Let's run through the most important right now, ignoring depends on, which has its own specific lesson coming up shortly. Group and description you should be somewhat familiar with from chapter 2, but let's just recap. So here's the generate descriptions task in the Groovy DSL, and within the configuration closure we can set a group and description. So let's say theme park group. and an appropriate description. Now when we run the tasks task, we have a new group here, theme park tasks, and generate descriptions has a description. There's not much more to say about it than this. And in Kotlin, this looks very similar. The main difference being we're using equals here. And here's our new task group for Kotlin. Setting a do first or do last closure allows you to add extra functionality for your task to execute either before or after the main task action. For example, if we add a do first and do last closure to the copy task, the contents of the do first closure will get executed, then the actual copy will happen, and then the contents of the do last closure will be executed. When defining an ad hoc task, we normally need to specify inline what the task actually does. And by convention in Gradle, we normally do that using do last. So let's create an ad hoc task. Load the project. Let's run this new task. There we go. And whether you use do first or do last for an ad hoc task doesn't really matter. But generally in Gradle, we use do last as the convention. And let's do this in the Kotlin DSL. Reload the project. And we can run the task. Enabled is another property you can set. By default, it's true. But if you set it to false, it means that even if you execute the task, it won't be executed. So let's set that in this say by task in the Groovy DSL. And now when we try to execute this task, we can see it says skipped. It hasn't been executed. You'll see that if we set this to true, now that's gone ahead and executed the task. In Kotlin, it's very similar. We just use equals. That's been skipped. And now that's been executed. And finally here we have only if, which is similar to enabled. It allows you to skip a task, but this time you pass a closure, which needs to evaluate to true or false. So in the Groovy DSL, let's replace enabled with only if. And it takes a closure, and we could write an expression that returns false. And in Groovy, we can leave out the return keyword. So let's execute this. We see that the task has been skipped. Let's change this to a true expression. And now the task is executed. In the Kotlin DSL, very similar again. Well, in this case, it's actually exactly the same syntax. Let's execute this task. It's skipped because the only if closure has returned false. Let's make this true. Let's do something a bit more interesting. And now that's executed as expected. You can see a complete list of what you can configure on all tasks in the documentation linked in the notes below. And when it comes to class-based tasks, you can configure everything we've just discussed, plus any properties exposed by the task itself. So here's the Gradle documentation, and if we scroll down here, we have task types. These are all the prepackaged built-in tasks available with Gradle. Let's try out one of these that we haven't tried before, for example, delete. This deletes files or directories, and we can see here it's got a custom property that we set, and we need to set delete and pass the name of the folder or file we want to delete. So let's try this out. First off, let's create a directory which we're going to delete. And now let's define this new task. And as we saw, we say delete, and we pass the name of a folder. Let's load the project and run the task. And that directory's been deleted. Over in the Kotlin DSL, let's also create a new directory. Very similar syntax again. Let's run this task. Success. And that directory is now being deleted. So I just wanted to show you how you can browse the tasks in the documentation and use the information there to define the task in your own build. And I'll provide a link to the documentation of all these prepackaged Gradle tasks in the notes below. The key takeaways from this lesson are that you can define class-based tasks or ad hoc tasks where functionality is defined in line. There are two main approaches to defining tasks, but always try to use tasks.register for performance reasons we'll explore in the next lesson. Pass a closure during task definition to configure the task, and you can use do last and do first in the task configuration closure to get it to do any additional actions. See you in the next lesson. In the previous lesson, you saw how to define a task in a build script, including configuring it at the same time. In some cases, you may want to configure the task later on. For example, the Java plugin you'll learn about in the next chapter automatically creates a jar task, which you can configure to change the way the jar file is generated. In this case, you need to get a reference to the task by locating it. Sounds simple, but there's a bit more to it. That's what this lesson is all about. By the end of this lesson, you'll have learned why it's important to avoid configuring tasks unnecessarily and why we need to take that into account when locating tasks. 4 ways to locate tasks in your build script, including when to use each one, what the task provider is and how it helps improve your build performance, and how to configure a task once you've located it. If you've completed the previous chapter, you know the Gradle build lifecycle and its 3 phases of initialization, configuration, and execution. You saw that the configuration phase is where your build script is executed and the model of your project is created. Let's imagine a scenario where we have a Gradle project and it has many tasks defined. Each task is configured in the build script, but we want to execute just one of those tasks. Here's one approach you can use in Gradle, including how it relates to the configuration and execution phases of the build lifecycle. The initialization phase is left out as it's not relevant here. In the configuration phase, Gradle creates all the tasks defined in the build script. It also configures all those tasks based on the configuration closures. In the execution phase, Gradle figures out what task to execute. Since only one task name has been passed on the command line, it only needs to execute one task. So it goes ahead and does that. It turns out that the task configuration can sometimes be an expensive operation. For example, configuration could involve reading files. Also, as the number of tasks defined in the build increases, the configuration time also goes up. In the case where you only want to execute one task, it's unnecessary to configure all of these additional tasks. Here's another more up-to-date approach you can use in Gradle. In the configuration phase, Gradle does something slightly different. It registers the tasks, which means Gradle knows about them, but they haven't yet been created or configured. Gradle moves on to the execution phase, where it figures out what tasks need to take part in the build. Again, just the one task. Only at this point does Gradle create and configure the task by executing the configuration closure. Then the task is executed. The advantage of this approach, then, is that we've avoided unnecessary configuration of tasks. This is the task configuration avoidance feature, and using it is a best practice we'll follow for the rest of this course. You already saw in the previous lesson the recommended approach for registering tasks, using tasks.register. By doing this, it means your task won't be created and configured unless it's actually going to take part in the build, thereby following the configuration avoidance best practice. Let's run through a quick example showing the problem that configuration avoidance solves. So here we have the generate descriptions task, and let's switch this syntax back to the legacy syntax which you learnt about in the last lesson. So now we can still run generate descriptions. But let's imagine that we wanted to run the clean task. Let's run that. And we can run that as many times as we like, and it roughly takes 50 milliseconds to complete. But imagine a scenario where generate descriptions has a configuration that takes a little bit of time. And we're going to exaggerate this a bit. But in this configuration closure, let's add a sleep of 5 seconds. And can you guess now what's going to happen if we run the clean task? That's right, the clean task took 5 seconds to execute. So even though clean is in no way related to generate descriptions, because generate descriptions has an expensive configuration, it still takes 5 seconds to run that configuration, even if we're just executing the clean task. This is the problem that configuration avoidance solves. And the solution is quite straightforward. It's just to use the tasks.register syntax we've been using up to this point. So now we've put that back, we can run clean again, and it's quick. We've successfully avoided the configuration of generate descriptions when it's not required. Of course, if we run generate descriptions, that's still slow, but that's fine because that's its own configuration that's slow, and it's not affecting other tasks now. You might be wondering why you're learning about configuration avoidance in a lesson on locating tasks. Well, it's actually quite relevant. There are different ways to locate a task, some of which result in the task being automatically configured, which we might want to avoid. Here are 4 different approaches. The best approach is to use tasks.named to locate a task. It returns a task provider. And a task provider is a class which represents a reference to a task that has been registered but not created. It's a way to refer to a task without causing the task to be created, which could result in unnecessary configuration. Once we have a task provider, we can configure the task it represents. So back in our build script, we could locate the generate descriptions task. And we can pass a closure and configure anything we want. So at this point, we could override some of the configuration. So let's change the into directory. And we'll call it descriptions renamed. Now, if we run generate descriptions again, in the build directory, we also have descriptions renamed. So we've successfully located a task that's already been registered and we've configured it. Let's do the same in Kotlin. So in Kotlin, we need to pass the type here, that's copy. And that's also created the new directory. The task provider has other uses too, like using it to set up dependencies between tasks, which we'll learn about in the next lesson. The second approach is to use tasks.getByName. This returns the task class itself, not a task provider, and results in the task getting immediately created and configured. So generally, this approach is best avoided. So all we need to do to use this approach is to change named to getByName. And that runs fine. And to demonstrate that this immediately configures the task, let's add a sleep of 5 seconds in here. And now if we run clean, this is slow again. So we can contrast that to the named syntax. So just change that to named, and now when we run clean, it's immediate. It's using the configuration avoidance APIs. In Kotlin, we also just need to change named to getByName. And that works fine. For some tasks, you can use the syntax tasks.taskName to access the task. This works for default tasks that come with every Gradle project, like help, and also tasks added by core Gradle plugins, like the clean task added by the base plugin. So for example, we could locate the clean task with tasks.clean, and then we could configure that and set a do last. Now, if we run the clean task, that's been successfully configured. And in Kotlin, there is a difference in behavior between Groovy and Kotlin with this approach. With Groovy, the task gets created immediately, but with Kotlin, a task provider is returned. To avoid confusion in the rest of this course, we'll prefer using approach 1 tasks.named instead. And the final approach only works in the Groovy DSL. You can access a task by using its name directly in the build script. Once again, this approach doesn't return a task provider, so will result in the task getting immediately created and configured, so it's best avoided. So in this build script, we could just remove the tasks from the front here. And because of the dynamic nature of Groovy, Gradle is able to locate this task just by calling clean here. And that works fine. And this also works for tasks that you've defined yourself. So for example, generate descriptions. Let's change the message. But likewise, you can locate the task in the same way. The key points to take away from this lesson: task creation can happen during the configuration or execution phases. It's best to register tasks and use the configuration avoidance APIs so that tasks only get created if they need to be executed. The task provider class allows you to refer to and configure a task without it being created. And there are 4 common approaches to locating tasks, but tasks.named is the best one to use since it avoids the tasks getting unnecessarily created. See you in the next lesson. Task dependencies are a way for us to tell Gradle when running task A, task B has to run first. Another way to think of it is via a producer and consumer relationship. When running the consumer task, the producer task must run first. If you think back to the generate descriptions and zip descriptions tasks within the theme park rides with zip project, can you identify which of these is the producer and which is the consumer in their relationship? That's right, generate descriptions produces a directory containing the copied ride descriptions, which zip descriptions consumes in order to create a zip file. This relationship can be modeled in Gradle as a task dependency from zip descriptions to generate descriptions. Remember when you executed these tasks before, you ran 2 separate Gradle commands, one for each task. The other option you know about now, of course, is to run a single command but list both tasks. But wouldn't it be nice if Gradle knew automatically that to run zip descriptions, it first has to run generate descriptions? Well, that's exactly what we can do with task dependencies. So here we are in the theme park rides with zip project, and we've got the zip descriptions task. If we run that task, then you'll see that it's only running the single task zip descriptions, and we have to manually remember to run generate descriptions first. To fix that, the syntax is very straightforward. We just call the depends on method, and then we have to pass a reference to generate descriptions. One way to do that is to use approach 1 from the previous lesson on locating tasks. That's tasks.named. So now when we run zip descriptions, we can see that Gradle knows that both tasks are taking part in the build now. Another way to reference this task would just be by using its name. And that was approach 4 in the previous lesson, and it only works in Groovy. And even though this way of locating generate descriptions requires that it gets immediately created, it doesn't matter in this scenario because we're referencing generate descriptions from a configuration block that's going to get lazily evaluated. One other approach you can use, especially if you're referencing a task in multiple places in a build script, is to define a variable. So tasks.register returns a task provider. And we can pass that variable to depends on. And that has the same effect. And this is how that looks in Kotlin. We've also defined a generate descriptions task variable, and likewise we just pass it to the depends on method. Bear in mind that you can pass multiple tasks to depends on, so let's try that out by creating a similar task. So we'll call this task A, and the directory will be descriptions A. And this is generate descriptions B. So we need to rename this directory to descriptions A. Create a new directory, descriptions B, and we'll move teacups from A to B. Let's clean first, then run generate descriptions A followed by B. And now in our build directory, we've got the two directories, and we can take the generate descriptions B reference and pass it on the end here. So when we run zip descriptions, it's going to run generate descriptions A and B first. So let's run that. I forgot to update the from for the zip descriptions. Let's add A here. And we can also pass B as well. Let's run that again. That looks better. We can inspect the contents of the zip file. That looks fine. When you have multiple task dependencies, in some situations you may need to enforce execution order between those dependent tasks. To do that, we use the must run after syntax, which means that if both tasks are executed, task A always runs after task B. So right now in this project, when we run zip descriptions, that's running generate descriptions A followed by B. Let's set up the order so it's B followed by A. Within the configuration closure for generate descriptions A, we just say must run after generate descriptions B. Let's run this task again. And there we go, the order's been switched. An important thing to note is that must run after only works if the tasks are actually going to be executed. So if Gradle actually decides that they're going to take part in the build. To show this, I can remove generate descriptions B from the depends on of zip descriptions. And now when we run zip descriptions, we see that generate descriptions B is missing. So must run after only forces the order if both tasks are going to be executed anyway. Another option we have in Gradle is to define a relationship between task A and task B, which means that task B is always executed after task A. We do that by setting up a finalized by relationship. The important difference here is that task B will always get executed, even if task A fails. If you're familiar with Java, you can think of this a bit like the finally section from a try-catch finally block. The finalized task always gets executed. Let's illustrate that by adding a new task, confirm finished, and we'll get that to run after zip descriptions. And we'll use do last closure and print a string. So just to check, if we run zip descriptions now, it's only running these three tasks. Let's call the finalized by method, and we can just say confirm finished. Now let's run zip descriptions, and there we go. Confirm finished ran at the end. To show that this is going to be run even if there's an error, let's throw an exception. So in zip descriptions, we can add a do last block, and within that we'll throw an exception to cause this task to fail. Let's run again. In IntelliJ, if I click on the top level here, we'll see all the output. Scroll up, and it says zip descriptions failed, and then we can see it's still run confirm finished. And here's how you can do this in Kotlin. We've got a confirm finished task, and within zip descriptions, in a similar way, we can say finalize by, and we could access that task with tasks.named confirm finished. Now, if we run zip descriptions, it also runs the finalized by task. Key takeaways from this lesson are that we can use task dependencies to ensure task B always runs before task A. We can use must run after to force ordering between executed tasks. And finalize by can be used to always run task B after task A, whether or not task A fails. See you in the next lesson. In the previous lesson, you learned how to use task dependencies to make sure that in our example project, the generate descriptions task gets executed before zip descriptions. This now works much better than having to execute 2 tasks manually, but it's still not the optimal solution. Let's revisit both tasks. Can you identify some duplication between these tasks? Well, the into in generate descriptions and the from in zip descriptions are the same. Wouldn't it be nice if we could just tell zip descriptions to use whatever is created by generate descriptions? Well, that's totally possible in Gradle using task inputs and outputs. If we think about it in simple terms, a task takes some input, does some action based on that input, which creates an output. In the case of generate descriptions, the input is the descriptions directory, and the output the new descriptions directory generated in the build directory. The fact that tasks in Gradle have inputs and outputs paves the way to several useful features. For example, the incremental build feature I mentioned in the previous chapter works using inputs and outputs. When you try to execute a task, if Gradle sees that neither the inputs or outputs have changed since the previous execution, Gradle won't execute the task and will mark it as up to date. This feature saves a huge amount of time for developers. The other feature is that we can link tasks via their inputs and outputs. The output of a producer task becomes the input of a consumer task. In our example, the output of generate descriptions would become the input of zip descriptions. The way to achieve that with the zip task is very simple. We just pass the task whose outputs we want to use to the from method. Then those outputs get used as the inputs to the zip task. Something else that happens when you do this is that Gradle automatically adds the task dependency, since it knows we're linking outputs to inputs. So let's try this out in the build script. And right now, if we run zip descriptions, everything's working as expected. It's running both tasks. So let's change the from of zip descriptions. Rather than hard coding the descriptions directory, we'll just reference generate descriptions. And that means that whatever generate descriptions creates, wherever its outputs are, zip descriptions is going to use those and zip them up. They become the inputs of zip descriptions. And we no longer need to add the depends on. That's added automatically by Gradle now. So let's run clean first, then zip descriptions. It's run both tasks for us. Let's just double check the zip file. And that all looks good. The 3 main benefits of linking inputs and outputs like this are that we reduce duplication, as now we're only defining the build/descriptions directory once. It improves maintainability, since if we ever need to update the directory name, we only have to change one place now. And it makes the build script more concise, since we no longer need to add the task dependency, as Gradle adds it automatically. And you can find a link to this sample project in the notes below. The key things to take away from this lesson are that most tasks have inputs and outputs. These are used to determine if a task is up to date. If it is, then Gradle won't execute the task. This is the incremental build feature. And we can link outputs from one task to inputs to another. When we do this, Gradle adds the task dependency automatically. See you in the next lesson. You learned in Chapter 1 that plugins can add rich functionality to a build by adding extra tasks. You saw how to apply a plugin, the base plugin, simply by specifying the plugin ID. This syntax works for any core plugins bundled with Gradle. When we're applying non-core plugins, or in other words, plugins published by third parties, we must also provide the plugin version. To find the latest plugin version, you can go to plugins.gradle.org and search for the plugin by name. So let's say I'm interested in a plugin called Task Info. Click on the result, and it says latest version 1.3.0, and it even tells you the plugin syntax for both Groovy and Kotlin. So let's copy this. And here's the theme park rides with zip project, and we're going to include this plugin as well, so we'll just add it at the top here. We can load the project in IntelliJ with Control-Shift-O. And if there's no problems, that means this plugin has been applied properly. Now back on the plugin page, we can click on Kotlin, and here's the Kotlin syntax. Paste it in here, and once again I'll do Control-Shift-O to load this project again in IntelliJ. And that plugin has been applied fine. Now there is another syntax for applying plugins which should be avoided, but which you may see in existing projects. And this is how it looks for core plugins. And for third-party plugins, it's a lot more complex. You can see why the other approach is preferred. But also, using this syntax misses out on some important optimizations and means Gradle's IDE integration won't work properly. And you may have noticed that on the plugin page, it also includes this legacy syntax. And like I said, it's always best to use the plugin DSL syntax where possible. Finally, plugins can often be configured in the build script. How you do that depends on the plugin. For example, the base plugin has a configuration called base, where you can set, amongst other things, the default archive name. So let's see what happens if we remove the archive file name configuration from zip descriptions. Just delete this line, and we'll run clean, and then zip descriptions. Let's see what's in the build directory. So we've got a file called theme park rides with zip fixed, which happens to be the name of this project. So by default, it's using an archive name of the project name. Sounds fairly sensible. But we can override that with a configuration of the base plugin. So we just say base, and then archives name equals, and then whatever we want, stuff. Now when we run zip descriptions, we've got a file stuff.zip. And to know what configuration you can apply for a specific plugin, you can check out the plugin documentation on the Gradle website for core plugins. So here's the documentation for the base plugin. And it's showing us what options we have for configuring it. And for third-party plugins, you can normally find a link to documentation from the Gradle plugin page. So plugins.gradle.org, this is the task info plugin page. Here's the link. And here's all the information about how to use the plugin. See you in the next lesson. Well done for getting to this point in the chapter. There's been a lot of theory and fundamentals which will set you up well for the rest of the course. The final components of the build script to cover now are repositories and dependencies. When you're building an application, you normally rely on external artifacts rather than writing everything from scratch. Think Spring Boot, Apache Commons, or Guava in the Java world. These could be published by a third party or your own company. In Gradle, you refer to these artifacts by declaring dependencies in your project's build script. A dependency is just a way for you to tell Gradle that you need these artifacts to build the project. By the way, it's important not to confuse these artifact dependencies with task dependencies discussed earlier. That's an entirely different topic. So if dependencies are pointers to artifacts required to build an application, then where do we get these artifacts from? Well, they're often hosted online in services such as Maven Central and Google Maven. These services are called repositories. If your company has artifacts it wants to share privately, you can of course host your own repository, and Gradle supports that too. So Gradle looks at dependencies defined in build scripts, then, to use the technical lingo, it resolves those dependencies to artifacts it fetches from declared repositories. In the rest of this chapter, you'll learn how to declare repositories and dependencies in a build script, what repository choices you have, as well as some more advanced features like excluding dependencies. Gradle supports 3 different repository formats. Maven is the most popular and the one you'll already be somewhat familiar with. Another format is Ivy, and there's also a flat directory format where Gradle looks for dependencies in local storage. Since Maven is by far the most popular format, we'll focus on it exclusively in this course. When someone publishes an artifact to a Maven repository, it includes not only the artifact, for example a Java jar file, but several metadata files containing more information. One such file is a .pom XML file, which describes the project group ID, artifact ID, and version. You'll see later that these are the three identifiers needed for Gradle to locate a dependency. The POM XML file also describes any transitive dependencies. These are additional artifacts that the artifact itself depends on, and Gradle knows how to fetch these too. Gradle has built-in support for using the Maven Central and Google Maven repositories. Built-in support just means that you can use these repositories in Gradle without having to configure any URLs yourself. You can browse the Maven Central repository at mvmrepository.com. Let's search for the Apache Library Commons binutils, select the artifact, and pick the latest version. Here we have links to download the jar file itself and view related files like the POM file. And it almost feels like cheating, but we can grab the actual Gradle code to include in our build script to add this dependency. More on this shortly. So before we get into declaring dependencies, we need to tell Gradle where to pull them from. If we don't do that, there's no way that Gradle will be able to resolve any dependencies at all. So let's give it a fair chance. Here we are in a brand new Gradle project. The build script here is empty, ready for us to declare some repositories. Much like many other configurations in the build script, we have to call a method on the project object to configure these repositories. And we pass a closure. At this point, we can configure as many repositories as we like. Let's add Maven Central by calling this method, Google Maven by calling this method, and a custom Maven repository with this syntax. Yes, I'm that cool that I've got my own Maven repository. With these three repositories declared, Gradle will consult them in order when resolving dependencies. It will first look in Maven Central, then Google Maven, then the world's most unhelpful repository, my custom repository. A good practice when declaring these is to order them so that the one that contains the most dependencies relevant to your project appears at the top, and the one that contains the least at the bottom. This way, you'll reduce unnecessary network traffic, leading to potential performance gains. Now that Gradle knows where to look for dependencies, it's time to declare them in our build script. Declaring dependencies is our way to tell Gradle that in order for you to build this thing, you need these artifacts. But there is a bit more to it than that, because the term build may involve multiple different stages. For example, compiling your application code could be one stage, while testing and running the application might be their own separate stages. The dependencies required for all these stages might be different, and Gradle lets us be specific about that. Let's take a Java application, for example. The Java class path is a list of files passed to Java when it compiles or executes the code. These are the compile and runtime class paths, respectively. Imagine we have three different dependencies, some of which are required for compiling the application and some for running it. Gradle gives us a way to specify dependencies for the compile class path, runtime class path, or for both. The way it does this is through dependency configurations, which are a way of grouping dependencies. Some dependency configurations end up on the compile class path, and some on the runtime class path. Let's try a quick example to learn more. We'll first apply the Java plugin, which will allow us to assign dependencies to different dependency configurations. Let's use the plugin's DSL syntax. With ID Java, plugins have to appear at the top of the build script, so I've added it before repositories. Now we can start applying dependencies. We call the dependencies method and pass a closure. Now we can cheat by grabbing the code from mavenrepository.com to declare the Apache Commons beanutils dependency. Note that this syntax contains the group, name and version, which is all that's required for Gradle to resolve this Maven dependency. Implementation is the name of a dependency configuration. When you say that a dependency is part of implementation, it means it will appear on both the compile and runtime class paths. Other configurations include compile only and runtime only. Don't worry about these details for now though, as we'll explore it all in full in the next chapter. Let's reload the Gradle project with Ctrl-Shift-O, which shows that our project is valid. You've just seen one format for declaring dependencies, which actually uses a map of key-value pairs for group, name and version. This is rather imaginatively called the map notation. But there's another notation called the string notation, which looks like this. It's just a string with the group, name and version separated by colons. Whether you use one notation or the other doesn't really matter, but personally I prefer the map notation as it's more explicit. What's more important is that you pick one and stick with it consistently in your project. Remember earlier I mentioned how Gradle fetches transitive dependencies of dependencies declared in your build script? Well, if we browse the pom.xml file for Commons beanutils, we can see that we have 4 transitive dependencies. Sometimes we need to exclude transitive dependencies if they're causing a problem in our project. Be careful though, because if you exclude a transitive dependency that's genuinely required, it may lead to runtime errors. Let's try excluding this Commons Collections transitive dependency. We do that by passing an additional closure, but we'll first have to wrap these method arguments in brackets, and then pass a closure. And in here we call the exclude method, which takes another map. That map contains the group and module of the transitive dependency to exclude, and the module is equivalent to the name of the dependency. Note that if you have other dependencies that also bring in this transitive dependency, you'll have to configure the exclude there too. And here's the same Gradle project written in Kotlin. And the main differences are that when we define the Java plugin, we just say Java. When we define a custom Maven repository, the syntax to define the URL is slightly different. When we define the dependencies, we say group, name and version using the equals syntax. And in a similar way, when we define the exclude, we specify a group and module using the equals syntax. Key takeaways from this lesson are that in the build script, we have to declare repositories from which dependencies are fetched. Normally this would be Maven Central, Google Maven, or your own custom Maven repository. The order in which repositories are declared is important. Put the most used repository at the top for the best performance. Dependency configurations are a way to group dependencies for use by different stages of your build. For example, the implementation configuration is used to generate the compile and runtime Java class paths. Dependencies are declared by specifying their group, name and version against a dependency configuration, and you can use the map or string notation. Transitive dependencies can be excluded using the exclude syntax and passing a group and module. This lesson was a bit of a taster of what's to come in the next chapter, where you'll learn all about building Java applications with Gradle, with practical examples for you to try out yourself. See you in the next lesson. Welcome to the next chapter, where you're going to become proficient at building, testing, and running Java applications using Gradle. This is where things get exciting because Gradle offers many extra features above and beyond other build tools like Maven that help developers work more effectively. Before we get too carried away though and start diving into Gradle features such as the Java plugin, let's take a step back and think from first principles what we need from our build tool when developing Java applications. If you're not familiar with Java, don't worry, as I'll be explaining the relevant Java concepts along the way. We'll begin by creating a shopping list of essential features in our build tool to build a Java application. First off, and perhaps the most obvious, is that the build tool needs to compile Java classes. In Java, developers write source files, files ending in .java, which contain code that looks like this. The Java tool then compiles these source files into class files, files ending in .class. Class files are bytecode, or in other words, optimized code that's ready to run on the Java virtual machine, the JVM. One other important input during compilation, other than the source files themselves, is the Java class path. As you learned in the last chapter, this is just a list of files containing more compiled Java code, normally libraries referenced by the source files. For example, if I'm developing a Java web application, I may decide to use the Spring Boot libraries. Java classes from these libraries would be referenced in my source code, and the compiler needs to know where they're located during compilation. That's what the class path helps with. So that's the first point. The build tool needs to handle compilation and any complexities around that, like generating the class path. Next, the build tool should manage resources. Resources are additional files that an application relies on. These aren't Java source files, but they are potentially referenced by Java code, so need to get packaged up with the code. Examples of resources could be images, HTML, text files, or anything else served up by the application. Next is handling dependencies. Any library referenced from your application code becomes a dependency of the application. It's needed to compile and run the application. Java doesn't have a way to manage dependencies itself, and it relies on the class path being correctly generated, referencing any libraries used in the code. We need the build tool to allow us to specify dependencies required for compilation, which it should use to generate the compile class path. The first 3 points get us to where we've got everything required for our Java application, so the next thing we need the build tool to do for us is package up the compiled classes and resources into a single artifact. In the Java world, this single file is normally a jar file, which is basically a zip file containing all the class files and resources, plus some extra metadata. Handling a single jar file makes things a lot easier when it comes to running, publishing, and deploying Java applications. The final core feature is to ensure the correctness of the application by running tests against it. The tests themselves need to be compiled and may need a different class path to that of the main application. Importantly, the test classes shouldn't end up in the published artifact. The build tool should also be able to run those tests and show us the results, ideally in a pretty report. Those are all the core requirements of our build tool, quite a list, I know. You probably won't be surprised to hear that Gradle meets all these requirements and then some. But in the interests of making developers' lives as pleasant as possible, there are some additional requirements that would help and make developers even more effective. So let's take a step back again and think about how we could put a smile on those developers' faces. It would be great for the build tool to also be able to run the application. It's true that once we have a jar file, we can run it with Java directly, but it would be better done in the build tool as it could generate the runtime class path automatically for us. New Java versions are frequently released, so it would be good to have an easy way to manage this in our build, ideally by changing a single line of code. The version of Java used to run Gradle should be decoupled from the version of Java used to compile or run our application, keeping everything nice and separate. For teams relying heavily on automated testing, there will often be different suites of tests. At a minimum, this would be unit tests and integration tests. The build tool should allow these suites to be run separately or together. The unit tests are quick and can therefore provide fast feedback to developers, while the slower integration tests might be run less frequently, for example before committing code. Next, now we have an application artifact and we've tested it, we need to publish that artifact somewhere for it to be used. Normally this would be a Maven repository, whether public or private. Once it's safely stored there, if it's an application it can be deployed, or if it's a library it can be referenced by some other project. Once again, and no surprises here, but Gradle ticks all these boxes. In the rest of this chapter, we'll explore exactly how Gradle meets all these requirements to successfully build, test, and run Java applications. See you in the next lesson. In the last lesson, we created a shopping list of all the requirements of our build tool. Now you'll see how we can achieve all of the essential requirements by applying a single Gradle plugin to a project, the Java plugin. The Java plugin is a core plugin, which means that it comes by default with Gradle, and you can apply it by just specifying its ID in the plugin DSL like this. You already know that plugins add extra functionality to a project, normally through additional Gradle tasks. The same thing applies with the Java plugin, with tasks for compiling code, processing resources, producing a jar file, and running tests. As well as adding tasks, plugins can also configure our project in interesting ways. The Java plugin adds several dependency configurations, which we can declare dependencies against to control the generation of class paths so they're as efficient as possible. In the rest of this lesson, we're going to look at what functionality the Java plugin brings to a project and what specific structure it expects a project to have. Our first requirement for a Java project was to compile classes. The Java plugin allows us to do this through a task called compile Java. You can run this like you would any Gradle task with Gradle w compile Java. This task will use whatever Java version you're using to run Gradle to compile your project's .java files into .class files. By default, the Java version is found from the Java home or path environment variables. These .class files get output into the Gradle build directory. Here's an example showing that if I had a Java class myFirstClass in a package called com.tomgregory, then the compiled class would get output into the build directory with this specific directory structure. Don't worry about the details of the directories for now, because I'll explain the structure in full later in this lesson. What's important to remember is just that the compiled classes go into the build directory. The next requirement for a Java project was to manage resources. You guessed it, the Java plugin also allows us to do this through another task. This task is called Process Resources, and you run it using Gradle w process resources. And the task will look in specific directories in your project and copy the contents into the build directory. The reason it's called Process Resources is that it can do some additional processing along the way, such as string token replacement. Here's an example showing that if I had a text file called superimportant.txt in a resources directory, when I run the Process Resources task, the text file would get copied into the build directory with this specific directory structure. I'll go over the directory structure in more detail later, but just know for now that Process Resources copies resources into the build directory. The next requirement we had was to easily define dependencies. The way dependencies are defined in Gradle is in the Dependencies section of build.gradle, which you learnt about in the last chapter. As a reminder, the dependency configuration looks like this. Here we have a single dependency defined for Apache Commons Lang 3. Importantly, when you define dependencies, you must specify the group, name and version, separated by a colon if you're using the string notation shown here. This gives Gradle enough information to be able to find the dependency in whatever repositories you've configured and download it. When you declare the dependency, it goes into a specific dependency configuration. For example, implementation is for any dependencies required during compilation or execution of your code. We'll explore other dependency configurations in full later in the chapter. Remember, it's important you pick the correct dependency configuration because they're used to generate the Java class path. When the compile Java task uses Java to compile your classes, the class path will need to include all the dependencies required for compilation. More on this later. The next requirement for a Java project was to package our compiled classes and resources into a jar file. Unsurprisingly, there's another Gradle task for this. Can you guess what it's called? That's right, the Java plugin adds a jar task, and you run it using Gradle w jar. The jar task takes all the compiled classes and resources from the build directory and adds them to a jar file. The name of the jar file is the project name -version.jar, by default using the project version defined in the build script. Here's an example that shows that if we had a project with classes and resources, the jar task would package them up into a jar file in the build/libs directory. You'll be able to try out building a jar file yourself in the next lesson, which is a practical all about creating a Java project in Gradle. The final requirement we had was to easily run tests. That's achieved with a task called test, which you run using Gradle wtest. And what this does is to compile your test code, process any test resources you might have, then run your tests. The other nice thing it does is to produce a pretty test report in the build directory. Here's an example, and the report tells us what's passed and what's failed. So far in this lesson, we've talked about how the Java plugin takes classes and resources, processes them in some way, and outputs generated files into the build directory. The last topic to cover right now is the default project layout that the Java plugin expects. Using this standard layout means it knows where to find things. Source main Java is where the Java plugin expects to find classes. Within here, you'd have packages and Java classes. Source main resources is where it expects to find resources such as text files or images. Source test Java is where it expects to find test classes. And lastly, source test resources is where it expects to find test resources. And as is normally the case with Gradle, these locations are configurable, but it's almost always best to go with a default layout if you can, because it's the standard that people expect to see. It's also the same layout that the popular build tool Maven uses. On the right-hand side, we'll explore where the classes or resources on the left end up in the build directory. Remember that the build directory contains all the Gradle build outputs, and importantly, doesn't get committed into version control. So classes go into build classes Java main, resources go into build resources main, tests go into build classes Java test, and test resources go into build resources test. You don't need to remember all these destination details, but it should help you navigate your way around the build directory if you ever need to. The key points to take away from this lesson are that the Java plugin initializes a project as a Java project, which means it adds tasks for compile Java, process resources, jar, and test. Dependencies get defined in different dependency configurations, which determines how they end up on the generated Java class path. And always use the standard project layout so the Java plugin knows where to find files. Hopefully you found this useful. I know it's very theoretical at this point, which is why in the next lesson we're going to jump straight into a practical where you'll create a Java project with Gradle. See you in the next lesson. It's time to jump in with a practical lesson to get familiar with the high-level concepts we've just discussed on Java projects in Gradle. Please follow along with this lesson as you watch it, or you can find the step-by-step instructions in the notes below. We've got another important assignment from Theme Park HQ. This time they want us to build an application which reports the current status of one of the 3 theme park rides. In the first iteration, they just need a jar file which when executed will print the ride status. Once the concept has been proved, they're hoping that in the future this application can be used over an API, linking to digital displays to show the poor customers waiting in the queue what's going on. That way, they'll at least have something to look at to pass the time. It's worth noting that in Gradle you can create Java projects which produce standalone applications, or Java projects which produce libraries. An application is what we're creating here, as right now it needs to run standalone. We'll talk more about libraries later in the chapter, but in summary they get consumed by other libraries and applications rather than running on their own. Practically speaking, we need a jar file which when run with the java-jar jar file location and the ride name prints the ride status. So if we pass roller coaster, the output might be at the station. You don't need any in-depth Java knowledge to complete this task, as any code is provided in the notes below for you to copy and paste. What's important is that you get an understanding of the Java project setup in Gradle and how to build and test it. Unfortunately, unless you've got a real theme park in your back garden, we're going to have to use dummy data. We'll create 3 text files, 1 for each ride, containing a list of possible statuses for that ride. These will be packaged as resources with the application. We'll then have a Java class which reads these text files and picks a ride status at random when requested. The entry point to the application will be a public static void main method in the same class, which we'll set up to be called when the jar file is executed. Those ride queues aren't getting any shorter, so let's get started. So you can properly understand the fundamentals, we're going to create this project as a basic Gradle project with Gradle init, then add to it. So create a new directory, theme park rides status, cd into that directory, and run Gradle init. Choose Basic Project, choose the Groovy DSL, accept the default project name. Now I suggest you open this project in your IDE of choice. I'm going to be using IntelliJ IDEA. And here's our empty project. First off, we're going to add all the Java code for this application. We've got some production application code to add, and also some test code. Let's add the production code first. Remember, this goes into a directory called source/main/java. So go ahead and create source main java. This is where Gradle will look for Java classes when we run the compile Java task. Let's create a package in here ready for our code. Create another directory, com/Gradle Hero/theme park. Inside that new directory, we'll create a Java class, so create a file and call it ride_status_service.java. And open it for editing. Now please go to the notes below this video and copy the whole contents of the ride_status_service.java class and paste it into the file in your project. This is all the code needed for the actual application. We're not going to go into all the details of how it works because this isn't a Java course after all. But as a quick overview, we've got a class which has a main method, which is the entry point to the application. The main method takes in some arguments, and the first argument, the one with index 0, we expect to be the requested ride name. We call the getRideStatus method, which takes the ride name. In that method, it adds a .txt to the name, then calls the readFile method, which looks for that file in resources on the Java class path. Once the statuses have been read, a random status is selected from the list and returned from the method. Back in the main method, this status is then printed to standard out. This means that you can request a ride status, and if there's a file present in the resources, the application will print it out. Speaking of which, we should go and create some files now for those 3 rides. Remember that resources go into source/main/resources. So we just need to create a new directory under source/main called resources. So do that now. Let's create some files for the different rides. Create a file rollercoaster.txt. And in the file, we'll add some highly amusing ride statuses. You can make up your own or copy them from the notes. Then we'll do the same for logflume.txt. And teacups.txt. Ensuring we add some highly relevant ride statuses as we go. This is all the code and resources we need for a runnable application. Now we just need to get this thing built. We'll do that by adding the Java plugin and a few other configurations to get to the point where we can compile the code, generate a jar file, and execute the application from that jar file. Go into the build.gradle and remove the comment. Now let's add the plugins closure, which is the word plugins with curly brackets. Inside that, we'll apply the Java plugin, so add ID, space, then Java in single quotes. Now reload the project in your IDE. In IntelliJ, it's Ctrl-Shift-O. With just this one change, we've now got a whole load of new functionality in our Gradle build. You can see that IntelliJ has recognized the Java and resources directories. Let's go to the command line and type Gradle W tasks to see what we have available now. All the tasks listed under Build Tasks have been added to the project by the Java plugin. In the previous lesson, we were talking about the compile Java and process resources tasks. You don't see them here because actually they get run automatically when you run the classes task. Or to put it in Gradle terminology, the classes task depends on compile Java and process resources. Gradle only shows you the high-level tasks by default. But if you want to see all of them, you can run Gradle W tasks --all. Under Other Tasks, we can now see Compile Java and Process Resources. Let's see what happens if we run Compile Java. So run Gradle W Compile Java. That's successful. And you should notice now that a build directory has been created. Inside there should be a build/classes/java/main directory. And in there gets generated compiled java.class files in the correct package structure. If you can see rideStatusService.class, then everything's working properly. Let's do the same for process resources, so run Gradle W process resources. You'll have a new directory, build/resources/main. And in there should be the text files we created earlier for the 3 different rides. That's great. Now let's try to generate a jar file, so run Gradle W jar. It should be successful, and you should now have a jar file in builds/libs, and it should be called themeparkridesstatus.jar. Notice that there's no version included. That's because we haven't specified a version in our build.gradle. We're going to try to run the application now using the jar file we've just created. Type or copy from the notes the command java-jar build/libs/themeparkridesstatus.jar and then a ride name. So this will run Java using the jar file in build/libs and passing a command line argument of rollercoaster to get the rollercoaster status. Hit enter. You'll see an error which says no main manifest attribute. This means that Java doesn't know what class within the jar file to run. Even though there's only one class, we have to add what's called a manifest file specifying that rideStatusService is the main class. Fortunately, that's really easy with the Gradle Java plugin. We can configure the jar file in the build.gradle with this snippet of code, paste or type it in below plugins, making sure that the class's package and name match the main class you created. This configuration tells the Gradle jar task to additionally create a manifest file with this main class attribute, so that Java knows that rideStatusService is our main class. We need to build the jar file again, so run Gradle W jar. Now rerun the Java command that failed earlier, and you should see the text current status of rollercoaster is, followed by an amusing status. Just to prove that this is all working correctly, run the same Java command but replace rollercoaster with either log flume or teacups. You should now get a message specific to that ride. Awesome, you've just built and run a Java application with Gradle. We're not quite done yet though, as we need to add a test to make sure that this powerful application behaves as expected. Tests live in source/test/java, so under source create a new directory test/java. We're going to create a test for rideStatusService.java, so within this directory create the same package structure com.gradlehero.themepark. Now add a class rideStatusServiceTest. In IntelliJ IDEA, it doesn't show the file suffix, but the file does end in .java. Copy the ride status service test.java class contents from the notes below and paste it into the new file. This test class uses the JUnit 5 testing framework to run two simple tests. The first test just makes sure that the ride status service generates a non-null ride status for each ride name. Technically, it actually counts as 3 tests as it's parameterized for each ride name. And the second test checks that an illegal argument exception is thrown if an invalid ride is passed. Right now we've got lots of errors here saying it can't find org.junit.jupyter packages, which is the JUnit code we need to run the tests. This has happened because we haven't declared any dependencies on this library, so our test class can't be compiled. Or in other words, JUnit is missing from the test compile class path. Let's fix this by adding a dependencies configuration to our build script after the plugins. Type or copy the dependencies from the notes. This adds 2 dependencies to the test implementation dependency configuration, which means these dependencies will end up on the test compile and test runtime class paths. We also have a dependency for the JUnit Jupyter engine, which is only needed at runtime, so it belongs to the test runtime only dependency configuration. This means it will only be included in the test runtime class path. We also need to add a repositories configuration so Gradle knows where to download these dependencies from. They can all be found in Maven Central, so type or copy the repositories configuration block from the notes, putting it just before the dependencies. Let's try running the test now with the test Gradle task. This will compile the test code, process any resources, then run the tests themselves. Type or paste the command Gradle wtest and hit enter. You should see a successful build. Let's double check the test report, which is located in build/reports/tests/test/index.html. Open the file in a browser. Sadly, you'll see that 0 tests have been run. So what's going on here? Well, since JUnit version 5 is still in the process of being adopted from JUnit 4, an additional configuration is required to enable it. Type or paste the test configuration block below the dependencies. This configures tests to use the JUnit 5 platform. Run Gradle wtest again, and refresh the page in your browser. You should now see that 4 tests were run and we have a 100% success rate. It looks like everything is working correctly. All that's left for us to do now is commit this project, run git init. If you're using IntelliJ IDEA like me, you might want to add the .idea directory to the .gitignore file so it doesn't get committed. Then run git add dot, which gets everything ready to commit. Then type git status. You should see all the files you've just added, so commit these by running git commit-m with a message, create Java project for ride status service. Well done for completing this lesson. Hopefully you've now got a good general feel for how to create, build and test a Java project with Gradle. There is still a lot to learn, so in the rest of this chapter we'll be exploring other topics while building on top of this initial application. See you in the next lesson. You learned in the previous chapter that tasks can have dependencies on other tasks, and a dependency on another task means the other task gets run first. Let's use as an example some of the tasks added by the Java plugin. The build task depends on the assemble and check tasks. This means that when you run Gradle wbuild, assemble and check get run first. I know we haven't used any of these tasks yet in this course, but don't worry because in a moment you'll see them in action. Now the interesting thing here is that the build task itself doesn't do anything when it's run, or in Gradle terminology, it doesn't have any actions. It's only there to aggregate both the assemble and check tasks together. Assemble handles building your project, including creating artifacts, such as jar files, and check handles testing your project. the build task using task dependencies makes sure that both the assemble and check tasks get run. That's really nice, as it means if you ever need to build and test a whole project, you can just run a single task, build, to do everything. So that was just 3 of the tasks added by the Java plugin. There are lots more, so let's look at the complete task graph of those tasks. Here it is, and I know there's quite a lot to look at here, but don't worry as we're going to step through this bit by bit. The lines that you see connecting a task to the left to tasks to the right imply a dependency on the task to the right. So for example, build depends on check. You've already got practical experience of some of these tasks, which I'm highlighting with a rectangle to the left of the task name. This includes jar, compile Java, process resources, and test. These tasks are highlighted in green, which I'm using to show tasks which actually perform an action when they're run. For example, jar creates a jar file, compile Java compiles classes, process resources, processes resources, and tests runs tests. Let's take a look at the classes task, which I'm highlighting in blue. Now this task doesn't perform any action itself when it's run, it merely aggregates compile Java and process resources using task dependencies. So I'll use blue to highlight any aggregate tasks. Moving up the tree, assemble is another aggregate task, which when run causes the jar task to run, which in turn runs classes, which runs compile Java and process resources. You get the idea. Let's focus now on the tasks under the test task. You'll notice we have the same compile Java, process resources and classes tasks. The reason for this is to ensure that when we run the test task, our main production application code has been properly compiled and resources processed. Moving down again, these 3 tasks are duplicated again under compile test Java. Compile test Java itself is the task which when run compiles all your test code. And similarly, process test resources processes all your test resources. Above all these we have test classes, which is another aggregate task which depends on compile test Java and process test resources. And above this is the test task, which when run first ensures that both the main code and test code are built before running the tests themselves. Above this is check, another aggregate task which just depends on test. And at the very top level is build, another aggregate task which, as I mentioned before, can be used to build and test everything in your project. Now this was a lot of information, which thankfully you don't need to remember in its entirety. I'm going to highlight 5 key Gradle tasks for you to remember which will help when using Gradle in your day-to-day work. Build, as mentioned, can be used when you just need to build and test the whole project. Assemble and jar, which you can think of as equivalent for now, can be used when you only need to assemble the project without testing it. Finally, check and test, which you can think of as equivalent, can be used to test your code without assembling it. You might be wondering at this point why you wouldn't just run build all the time. Well, for medium to large projects, they can take some time to build, so picking the specific Gradle task for what you need to accomplish can save some time. For example, if you just need to test your code changes, then you could just run check rather than build. This may save you time, as check doesn't depend on the jar task, so no jar file will be created. Likewise, if you just need to build your project including the jar file without testing your changes, you could just run the assemble task. Now we're going to jump back into the theme park rides status project as we left it in the previous practical lesson to demonstrate a few of these important Gradle tasks. We'll first run clean. Normally you won't need to run this very often, but I want to run it now to ensure we start in a fresh state and can see what each of the tasks we're going to run does. You can see now that clean has deleted the build directory. The first important task to run is assemble, which from the previous slide you learnt will compile your code, process resources, and build a jar file. So let's run Gradle assemble. Taking a look in the newly generated build directory, we can see we have compiled classes in the classes Java main directory, resources in the resources main directory, and also a jar file in the libs directory. Notice that we don't have any test reports generated as assemble doesn't run the tests. So assemble is great for generating all your build artifacts in one go. If you ever need to build anything in addition to the jar file, you can make assemble depend on other tasks too. Now let's delete the build directory again by running Gradle wclean. The next important task to run is check. From the previous slide, you know that this task compiles the main code, processes the main resources, compiles test code, processes test resources, and actually runs the tests too. Let's run Gradle wcheck. In the build directory, we have both classes Java main and also classes Java test, because Gradle has compiled main and test classes. In the resources directory, we still only have the main resources, but if we had any test resources, they would also appear here. We also have a reports directory containing a test report, since our tests were also executed. Notice that importantly, we don't have any libs directory or any jar file, as the check task doesn't depend on the jar task. So check is the task to run when you just need to run the tests without assembling everything in your project. You'll see later in the chapter how check can be made to depend on other tasks, for example integration test. I'm going to delete the build directory once more with Gradle wclean. The final important task to try out is build, which as you know from the previous slide depends on the two tasks we've just run, assemble and check. So let's run Gradle wbuild. In the build directory, we can see we have compiled main and test code. We have the processed resources. We have a jar file in the libs directory. And we have test reports showing that the tests ran. So build is the task to run when you just need to assemble your whole project and run all the tests. That was quite a lot of information, so here are the key takeaways. First, remember that some tasks actually perform actions and some are just aggregate tasks. Aggregate tasks are helpful to combine multiple tasks together using task dependencies. The Java plugin adds many Gradle tasks, but we really only need to remember the high-level tasks such as assemble and jar, which both do the same thing of compiling your code and building a jar file, check and test, which both do the same thing of testing your code, and lastly build, which does both an assemble and a check. Hopefully now you've got a better understanding of all the different tasks used in a Java project in Gradle and how they fit together. See you in the next lesson. At this point, you've already seen 3 of the dependency configurations added by the Java plugin: implementation in the last chapter, test implementation and test runtime only in this chapter. And you probably have a rough idea that these are used to generate Java class paths. In this lesson, you'll learn about 3 more dependency configurations you can declare dependencies against, as well as exactly how all 6 are used to generate the 4 Java class paths. This will help you more effectively manage dependencies in your project. A quick note on terminology: the terms dependency, library and artifact are used somewhat interchangeably in this course and also in general in the industry. However, I think they each have a slight nuance that's worth noting. A dependency is what you define in your project to say that it needs some other resource to build or run. For example, we may declare a dependency in our project on a JUnit library. A library is how we refer to that resource from the perspective of the code. For example, our code might reference code from a JUnit library. And an artifact is the physical resource, generally a jar file, sitting in some repository somewhere. For example, the JUnit artifact lives on a remote repository, but also locally on our machine once Gradle downloads and caches it. With that out the way, let's move on to talk about production class paths. Here are the class paths required to compile and run a Java application, and we're specifically talking about the non-test code, which we call production code. To compile it, it needs a compile class path. This is a list of all the libraries referenced by the code to be compiled, which looks a bit like this. To run the compiled code, we need a runtime class path, which may or may not be the same as the compile class path. But why not make life easier for ourselves and use the same class path for compiling and running? Well, there are advantages to keeping the class path as clean as possible, by which I mean specifying only the minimal set of libraries required for compiling or running the application. For example, keeping the compile class path clean makes compilation more efficient, since Java doesn't have to load unnecessary libraries. Keeping the runtime class path clean reduces the size of our deployable, since we don't need to include unnecessary libraries. These are a few of the reasons that Gradle gives us fine-grained control of class paths through dependency configurations. Before we get on to how Gradle lets us control the class paths, though, there are two more things you need to know about dependency configurations. First, one dependency configuration can inherit from another, meaning that it inherits all the dependencies declared on the parent. You'll see an example of this shortly. Second, there are actually two types of dependency configuration. There are those which are used for declaring dependencies only, like when we declared a JUnit dependency against test implementation. The other type are dependency configurations which you can't declare dependencies against, but which are used by Gradle to calculate things like the compile class path, or in Gradle terminology, the dependency configuration can be resolved. We'll refer to these types of dependency configuration as unresolvable and resolvable. If this is a bit confusing at this point, don't worry, as it will soon make sense as we run through how it all works with the production class paths. Still thinking about the compile and runtime class paths, let's explore how Gradle lets us control them. The compile class path is generated by combining dependencies listed against the compile-only and implementation dependency configurations, whereas the runtime class path is a combination of the implementation and runtime-only dependencies. Note that compile class path and runtime class path in grey are themselves dependency configurations. They are resolvable, meaning class paths can be generated from them. However, you can't declare dependencies against them like you can with the unresolvable dependency configurations in green. An example of using compile-only might be if you're building an application which will be deployed in an environment where that library is already provided. For example, at compile time, you might include the Servlet API library, but since your application will be deployed into a Tomcat instance which provides its own Servlet API implementation, the library isn't required at runtime. Implementation is by far the most used dependency configuration. If your application's code interacts directly with the code from a library, that library will most likely have to be an implementation dependency. For example, if an application uses the stringutils class from Apache Commons Lang 3, the library needs to be on the compile and runtime class path, so it needs to be declared against implementation. An example of using the runtime-only dependency configuration would be when your application needs to connect to a database. From a code perspective, you interact with the database-agnostic JPA or JDBC libraries, which don't need to know what database it's connecting to. Only at runtime do you include the library for the specific database implementation, like MySQL or Postgres. And at the bottom here, compile class path is used by the compile Java task. The task resolves the compile class path dependency configuration to generate the class path. The Java plugin itself doesn't have a task that uses runtime class path, but we'll go into how that's used by the application plugin later in this chapter. Now we've got the compile and runtime class paths sorted for production code, let's think about testing. Tests themselves are Java code that equally need to be compiled and run, so they have their own test compile class path and test runtime class path resolvable dependency configurations. Similarly, they also have their own test compile only, test implementation, and test runtime only unresolvable dependency configurations, which you can declare dependencies against. One interesting feature of tests is that, unsurprisingly I guess, they need to access the thing that they're testing. For example, our ride status service test accesses directly the ride status service. The fact that the tests rely on the production code also means that they need the dependencies of that production code. As I mentioned a moment ago, in Gradle, a dependency configuration can extend another. The Java plugin sets this up so that test implementation extends the implementation configuration, meaning it inherits all the declared dependencies. And likewise, test runtime only extends the runtime only configuration. As an example, if we have Apache Commons lang3 declared as an implementation dependency, since test implementation extends implementation, the same library will be available on the test compile class path. The compile test Java task resolves the test compile class path dependency configuration to generate the test compile class path. And the test task resolves the test runtime class path dependency configuration to generate the test runtime class path, which is used when actually running tests. The last dependency configuration you need to know about added by the Java plugin is a bit different. It's Annotation Processor. When Java code is compiled, it has a nice feature whereby additional source files can be generated by so-called annotation processors. The Java compiler accepts a processor path option on the command line, which is a list of all the annotation processor libraries. The annotation processor dependency configuration is used to control this processor path. One example of this is the mapstruct library, which generates mappers, classes which map one data representation to another. Another example is when you're using the lombok library, which at compile time can generate boilerplate code like equals, hashcode, and toString methods. And now for a helpful tip related to versions. Sometimes we have multiple dependencies to add to our project that are in some way related, and they may share the same version. JUnit Jupyter is a good example of this, which you've already seen in the theme park ride status project you created earlier. We had 3 related dependencies, each of which had the same version 5.7.2. This is duplication, and it means when we update the version we have to remember to update 3 places at the same time. One approach to solve this is to use Gradle's Extra Properties feature. This lets you define custom properties against the project object to be accessed at a later point. Let's define an extra property for the JUnit Jupyter version like this. We can then use the same version for each JUnit Jupyter dependency by referencing the property name. In this case, we need to replace single quotes with double quotes. Then when we include the JUnit Jupyter version, it gets interpolated by Groovy. The key takeaways from this lesson are that there are 2 types of dependency configuration, resolvable and unresolvable. The ones you interact with most frequently are the unresolvable ones, which you can declare dependencies against in the build script. Runtime only, implementation, and compile only control which dependencies end up on the production class paths. Test runtime only, test implementation, and test compile only control which dependencies end up on the test class paths. And remember that the test dependency configurations extend the production ones, meaning we can make use of the same libraries in our tests. The annotation processor dependency configuration is used to generate the processor path, which enables code generation at compile time. And we can use extra properties to centralize the version of dependencies that all share the same version. See you in the next lesson. Gradle offers many options when it comes to customizing how a Java application is built and packaged. In this lesson, you'll learn how to customize the 2 compilation tasks, the 2 process resources tasks, and the jar task. Compile Java and Compile Test Java are tasks added by the Java plugin to compile production and test code. They both use the Java compile task class. To know how to configure them, we just need to know how to configure Java compile. Here's the documentation which I'll link to in the notes, which shows properties you can set and methods you can call to configure this task. One interesting property is options, which is of type compile options. If we drill into it, we can see many options to configure Java compilation. Let's try setting the verbose option. Back in the Theme Park Rides status project, we'll try two different ways to configure the task. First off, imagine we only want verbose output during compilation of the production classes, not test classes. In that case, we can use the tasks.named syntax to locate compile Java and configure it with a closure. In the closure, we use dot notation to reference options.verbose, then the equals syntax to set the property value. Let's run this task. Note that I'll run clean too, so Gradle compiles the code again and doesn't rely on the incremental build feature. And we see more detailed information about what the compiler is doing. Now imagine we want to configure both compile Java and compile test Java in the same way. Rather than configuring each task separately, there's a way you can locate tasks by class type, which you might have spotted earlier when we configured the test task. So we just say tasks.withType Java compile.configureEach and pass the closure like before. Now whether we run compile Java or compile test Java, we see verbose compiler output. You can use this same mechanism to configure compilation of your own project exactly how you need it. You saw in the earlier practical lesson that process resources copies resources from source main resources into the build directory. Process test resources does a similar job for source test resources. Both of these tasks actually use the copy task, which you'll be somewhat familiar with from Chapter 1. That's great because it means we can use many different options provided by the copy task class, as we'll see in the documentation. Since you've already seen token replacement, let's try out the include feature, which lets us filter the files to be copied by matching on their file name. In our project, we'll make sure only text files are copied into the build directory. Imagine in source main resources we have a readme.md file with instructions about what to place in this directory. Let's run process resources. And we see that the readme2 has been copied into the build directory. But that shouldn't happen because we don't want it to end up in the final jar file. Let's locate the process resources task using tasks.named syntax and configure it by calling the include method. The string matches only file names ending in .txt. Now when we run process resources, the readme file has been removed because of the filter. Note how Gradle automatically removed the file from the build directory without us having to run clean. It's clever like that, as it automatically knows to delete stale task outputs. The last task to talk about in this lesson is jar, and it uses the jar task type. In the practical, you got experience configuring the jar task to include the main class manifest attribute so that Java knew which class in the jar file to execute by default. Let's explore in the documentation how the jar file name is chosen. In the practical, the generated jar file was called themeparkridesstatus.jar, which is the project name followed by .jar. The full file name actually consists of these parts. The archive base name defaults to the project name, which is why our jar file was named like that. If we set a version in our build script, then the generated jar file also includes that version. The extension by default is jar, and you can also set an optional appendix and classifier. All of these components are configurable, including the archive file name itself. Let's see if we can override the full name by configuring the jar task. We'll locate it using the tasks.named syntax and configure the archive file name using equals. Let's run the jar task. In build/libs, we now have a jar file with the specified name. Of course, using the default name is normally the sensible course of action, but you can at least see now that configuring the jar file as per the documentation allows you to control the build process in detail. The key takeaways from this lesson are that the compile Java and compile test Java tasks are of type Java compile and can be configured according to the Java compile documentation. Process resources and process test resources are just copy tasks. Anything copy can do, we can also do in process resources. A jar task is of type jar and can be configured according to the jar documentation. The jar file name is generated from multiple components, including the project name and version. Tasks of a particular type, such as Java compile, can be located together and configured at the same time. This might be useful if you want to configure compile Java and compile test Java in the same way. See you in the next lesson. Assuming you've now built your Java application, it's time to see how to run it using Gradle. To be clear, this lesson is all about how to do that in a local development environment. Running an application in a production environment is another topic outside the scope of this course. You saw in the practical lesson that it's entirely possible to run the jar file outside of Gradle, but there are good reasons to use the build tool for this instead. Firstly, the build tool is where you describe all your dependencies, so it would be best placed for generating the runtime class path automatically. And the build script is a convenient, version-controlled file in which to store any run configurations, such as JVM settings or program arguments. The core application plugin is Gradle's answer to this. It adds a run task to a project, so when you run Gradle wrun, it executes the provided main class. The application plugin automatically applies the Java plugin, so we don't need both. The class path it uses is generated from the resolvable runtime class path dependency configuration. If you remember the diagram from the earlier lesson, runtime class path is based on any implementation and runtime-only dependencies. Let's see it in action. We just need to apply the application plugin by replacing the ID Java with application. Now in our list of tasks, we have a new group, application, containing the run task. Let's run it. We get an error because it doesn't know what the main class is to execute. We fix that by configuring the application plugin with this closure. Inside it, we specify the main class property. And now we've got a failure because we haven't passed a ride name argument. With the application plugin, you can pass an extra command line option, --args, to pass arguments to the Java application. Let's edit the run configuration for the run task in IntelliJ to add that option with the log flume ride name. Now the task is working as we want it to. One thing to note is that the class path used by the run task references the compiled Java class files and not the jar file. This is validated by the task dependency graph for run, which only compiles the code and processes the resources, but doesn't create a jar file. Another option we have to run the application is to run the jar file itself, but from Gradle. The advantage to this is it's more similar to how the application runs in production, which might help us spot issues with the jar file generation. The application plugin's run task is based on the task class Java exec, which handles running a Java process. We can define our own task using that same task class, but this time instead add the jar file to the class path. If we look at the Java exec task docs, there are two configurations that will be helpful to us. To add the jar to the class path, we'll call the classPath method. To pass the ridename argument to the Java command, we'll call args. So let's register a new task called runJar of type javaexec. In the configuration closure, we call classPath and need to get a reference to the jar file created by the jar task. One way to do this is to use this code, which locates the jar task. Then call the map method on the returned task provider. This takes a closure from which we can return anything we want from the underlying task. In this case, it's the outputs. The outputs of the jar task are the jar file, so the jar file gets added to the class path of the runJar task. Then we just have to call the args method to provide a ridename. This time I'll pass teacups. Then we'll reload the project and take this task for a spin. We've got the correct output showing the status of the teacups ride. At this point, we're going to extend the example project in a small way to provide better input parsing. Right now, if I pass a ridename argument with a space in front of it, it fails with a ride not found error. It would be nicer if the application could ignore spaces. To do that, we'll add a new dependency on the Apache Commons lang3 library, which provides, amongst other things, a string utility class. Let's add that dependency as part of implementation, since we'll need it during compilation and runtime. Let's reload the Gradle project. Now, in the ride status service, we can call stringutils.trim before passing the ridename to the readFile method. If we run the application again with the run task, it still works fine. If we use the runJar task, though, we get an error saying it couldn't find the class stringutils. Any ideas why? When we configured runJar, we only added the jar file to the class path. That jar file only contains our application code, but not the implementation dependency commons lang3. Let's fix that by updating the class path to include the runtime dependencies. We just need to call the classPath method again, this time passing the runtime class path configuration, which, if you remember back to the diagram, is composed of the implementation and runtime only dependencies. Now when we run the task, we get a new error saying that we need to specify a main class. We do that by setting the main class property using the equals syntax, just like in the application plugin configuration. Now everything's working as expected again, this time with our runtime dependencies on the class path too, and the ridename argument has been correctly trimmed using the Apache Commons lang3 library. Before we wrap up this lesson, let's make sure you know what to do if you're ever in a sticky situation that requires step-by-step debugging of code. There are two main options. The first option is IDE agnostic and works from the command line. When executing any task of type javaexec on the command line, we can pass an option --debug JVM. This starts the JVM in debug mode and suspends execution until you connect a remote debug session. Let's try it out with the runJar task. We get a message saying listening on port 5005. In IntelliJ IDEA, we can edit the run configurations and add a new configuration for remote JVM debug. Let's give it a name of remote, and all the other settings can stay the same. Click OK. Before we run this, let's add a breakpoint in the ride status service, which in IntelliJ you do by clicking on the left-hand gutter. Now we'll hit the debug option to start the remote session. The IDE immediately pauses at the breakpoint, and now you have all the standard debug tools available, like stepping over line by line. Let's hit the green arrow to resume and complete execution. Back on the command line, you can see the application has completed successfully. The second debug option is specific to IntelliJ IDEA, and you probably won't be surprised to hear it's a lot simpler. Find the javaexec task you want to debug in the list of tasks, in this case runJar, right-click, and select Debug. This runs the task in debug mode and will pause at any breakpoints. We've covered a lot in this lesson, but here are the key takeaways. The application plugin adds a run task to our project. When we configure the main class, it will run our application. The application plugin also applies the Java plugin automatically, so there's no need to apply both in the plugin DSL. The run task uses the Java exec task class, which we can use to create our own tasks to execute a jar file. In the Java exec task, you can configure the class path, main class, and arguments. To debug the application on the command line, pass the --debug JVM option and connect a remote debug session to the Java process. Or if you're using IntelliJ IDEA, select the debug option in the task context menu. See you in the next lesson. In the earlier practical lesson, you got some experience with running the test task added by the Java plugin. This task supports the JUnit 4, 5, and also test-ng platforms. In this lesson, we'll explore how to use these platforms, how to be specific about what tests you want to run, and how to make the most of IDE integration. If you're a developer who regularly runs tests, this will help you spend less time waiting around for them. In the Theme Park Rides Status project, we're currently using the JUnit 5 platform, indicated by the fact we've got JUnit Jupyter dependencies in the build script, as well as configuring that platform for the test task. Let's downgrade our test to the JUnit 4 platform to see how that works. We can replace all the JUnit Jupyter dependencies with a single JUnit 4 dependency. Reload the project. Now, in the test class, we have to make some changes to make this compatible with JUnit 4. To keep this brief, I'll remove one test and simplify the other, changing the JUnit 5 imports to the JUnit 4 equivalent. Now, when we run the test task on the command line, we see that there's a failure. The test report indicates a problem with our test setup. It's because Gradle is trying to execute the test as a JUnit 5 test. To fix that, we need to remove the Use JUnit platform configuration from the test task. Now the test passes OK. Let's switch out the JUnit 4 dependency for test-ng and reload the project. We've got some errors again, but we can change the test class to use the test-ng import equivalents. Running the tests now gives no error, but the test report shows no test was run. We'll fix this by specifying use test-ng in the test task configuration. Now it's all working fine again. There are many other interesting ways you can configure the test task. Here are the docs, and we've already used the first two options here. Another option you might consider if your application uses a lot of memory is max heap size, which defaults to 512 megabytes. Moving on to discussing running tests, there are a few different options which tell Gradle which tests specifically you want to run. I've reset the project back to JUnit 5, and we've now got both test cases again. Let's make things more interesting by splitting the existing test class in two, moving the failure test to Ride Status Service Failure Test. We now have two test classes. If we run Gradle wtest on the command line, the test report correctly shows 4 tests have been run from 2 test classes. The test task itself has include and exclude methods you can call to configure what tests to run. We'll specify an include to match the Ride Status Service Failure Test. If we run the test task, the test report now shows only one test has run from one class. If we replace include with exclude, we'll see the other test class gets run. One benefit of using this approach rather than an ignore annotation on the test itself is if you want to exclude whole packages of tests at once. I'll remove the exclude, and we'll go back to the command line to explore another approach. Here we can pass the --tests option and specify a test class we want to run using its simple name. Try that with ride status service test. And the test task executes only that one class. There are other ways to run tests, like running a specific test method or all tests in a particular package. You'll find a link to all the options in the notes below. When you run the same tests again and again without changing anything, the tests will be skipped as Gradle already knows they've passed. You can see this at the bottom of the build output where it says 4 actionable tasks, 4 up to date. This is the incremental build feature again. You can also run with the -- console equals verbose option to see specifically that the test task is up to date. Only when an input or output of the test task changes will the tests rerun. The most common example of this would be changing some production or test code. If I make a trivial change to ride status service, like adding a new line, the code will be compiled again and the tests will get rerun. If you want to force the tests to rerun, you can also run the clean test task. This first cleans the test outputs, forcing the tests to rerun every time. This is infinitely better than running the clean task, which will force recompilation of all the code again. Normally, we can leave deciding whether or not to run tests up to Gradle. Clean test could be a useful option though in situations where you're investigating flaky tests that don't always fail. So far in this lesson, we've been using the command line to run tests, but running them is made quite a bit easier by using an IDE like IntelliJ IDEA. It's as simple as right-clicking on a test class or method and selecting Run, or use the shortcut Ctrl-Shift-F10. In my opinion, this provides nicer output than we saw before with the Gradle test report. Let's add another test to ride status service failure test that always fails. When we run all tests in this class, we can see the failure. And we can even right-click and run only that test case. Finally, you can override the default behavior of using Gradle to run the tests and use IntelliJ IDEA instead. It's in Settings, under Build Execution Deployment, Build Tools, Gradle. Where it says Run Tests Using, you can pick IntelliJ IDEA. The only time to consider this option is if you're having performance issues in running your Gradle tests, in which case you could use this temporarily until the issue is fixed. The key takeaways from this lesson are that you can configure the Gradle test task for JUnit 4, 5 or testng. You can use includes, excludes or -- tests to run specific tests you're interested in. Run clean test if you want the test task to rerun instead of being marked as up to date. And make sure to use IntelliJ IDEA test integration to save time running and rerunning tests. See you in the next lesson. You may be familiar with the idea of having different test layers, such as unit tests and integration tests. One popular way to model this is with a test pyramid, where as we go up the pyramid, tests cover broader functionality, but we have less of them. Unit tests are normally fast as they test a single class and don't rely on external resources. Integration tests are normally slower since they typically test several classes and may rely on external resources such as files or the network. It's helpful for developers to be able to treat these types of tests separately when interacting with the build. This means there should be a way to run unit tests separately from integration tests. This lets developers get fast feedback by executing unit tests more frequently than integration tests. To see how to implement this idea, we'll use the theme park ride status project. We'll create an integration test, which in our case will test the ride status service via the main method. In Gradle, we'll set things up to have a task to run unit tests, a task to run integration tests, and a task to run both. Let's create a class ride status service integration test.java in source test Java. And add one very simple test that just calls the main method with one ride name, making sure we don't get any errors. I'll run the test in IntelliJ IDEA to see that it passes. Now we need a way to separate integration tests into their own directory and add a specific task to run them. We could configure this manually in Gradle, but it's more efficient to use a plugin. The plugin you choose depends on the version of Gradle you're using. Gradle versions 7.3 and later include the awesome JVM Test Suite plugin. We'll run through this first, and then we'll look at the alternative third-party Test Sets plugin, which you can use in earlier Gradle versions. The JVM Test Suite plugin is applied automatically when you apply the Java plugin. It has the concept of test suites, each of which has its own test source directory and task. A default test suite called Test is automatically added for running unit tests. Just as you've seen already, unit tests live in source test Java, and you run them with the test task. For backwards compatibility reasons, this default test suite behaves a bit differently from others you configure, as you'll see shortly. So let's go ahead and configure the plugin to include an integration test suite. Inside Testing and Suites closures, we configure what additional test suites we require. For us, that's Integration Test, and within this closure, we can add more configuration, such as saying that we depend on the production code. Load Gradle changes, and you can see in the list of verification tasks a new integration test task. We'll run it, but it won't do anything yet as our integration test is in the wrong place. It needs to be moved to source integration test Java. Notice in IntelliJ IDEA how the directory is immediately recognized as a source directory. I'll move the ride status service integration test into the new directory and run the integration test task again. Now our test has run successfully. Notice that under verification we have a third task, check. This is an aggregate task which by default runs only unit tests. We can configure it to also run integration tests by locating the check task using tasks.named, then configuring a dependency on the integration test suite using testing.suites.integrationTest. Now when we run the check task, it runs unit and integration tests. Excellent! The check task would be perfect to use just before committing code or in your continuous integration pipeline. Note that the JVM Test Suite plugin automatically applies JUnit dependencies, so we don't have to declare individual group name and versions. For example, to use JUnit Jupyter for unit tests, we configure the test suite named Test like this. With this in place, we can remove any JUnit Jupyter dependencies and configuration, and the unit tests will still run fine. For any other test suites we declare like integration test, JUnit Jupyter dependencies are applied automatically. We can swap these out for JUnit 4 or testng dependencies by calling the corresponding methods. Now let's take a look at the Test Sets plugin, which I recommend using in Gradle projects prior to version 7.3. You apply the plugin using this ID, and it works by letting you configure what it calls test sets, which are conceptually the same as the test suites we've just discussed. These test sets have a separate source directory and test task. Having undone all the changes from earlier in this lesson, let's apply the plugin in our build script and configure what test sets we want, in our case integration test. And running the integration test task runs our tests as expected. We can configure check to depend on the new integration test task by locating it like this. You've now seen two different approaches to set up a clean and helpful integration test solution. These approaches could be used for other suites of tests, like performance or end-to-end tests. Here are the key takeaways from this lesson. In projects using Gradle 7.3 or later, use the JVM Test Suite plugin to configure suites of tests, like integration tests. For Gradle versions prior to 7.3, use the test sets plugin instead. In both cases, your integration tests live in a separate source directory, and they have a separate integration test task. Also remember to configure the check task to depend on integration test. See you in the next lesson. One thing we haven't talked about yet are Java versions. This is an important topic, especially given the fact that new versions are so frequently released these days. By default, when compiling and running Java applications, Gradle uses the same version of Java that you're using to run Gradle itself. And the Java version used to run Gradle is specified by the Java home and path environment variables. Gradle requires at least version 8 to run, so you can be sure that up to this point, in any practical lessons, you've been using this version of Java or later. You can check the Java version that Gradle's using by running Gradle w-version. On my machine right now, that's version 16, but if I set the Java home variable to the location of Java 11, for example, Gradle now runs with Java 11 and will use that version when compiling and running Java code. If any language features from versions greater than 11 were being used, compilation would fail. Right now, I can assemble the theme park rides status application with no problems. But if I add a theme park ride record class, which is a new feature of Java 16, now when I run assemble, we get a compilation error. The problem with compiling and running Java applications with Java version supplied by the environment is that it's not very deterministic. If a developer is running one version of Java locally, and the application in production uses another, it's possible to see inconsistencies in behavior. It would be much better to handle these versions separately like this. Fortunately, we can tell Gradle exactly what version of Java to use in the build script using a feature called Java toolchains. Right now, assemble is failing because we're using a language feature of Java 16, but Gradle is running with Java 11. We just have to pass a closure to the Java and toolchain methods, then set a language version inside the closure. Then run the same assemble task that failed earlier. That works no problem because it's using Java 16. This makes it very straightforward to upgrade your application to a new version of Java, since everything is under version control. The other good news is that Gradle will try to locate the Java installation on your local machine. If it doesn't find a compatible version, it will download one from the internet automatically. For example, if I delete the record class, then set the Java version to 15, which I know I don't have installed locally, we can see it's installing it. This feature is quite configurable, so you could, for example, use a different version of Java to compile, run or test your application. By default, all the Java tasks will use the version specified in the Java toolchain configuration, but the version can be overridden at the task level. For example, if we wanted to run our application with Java 16, we just need to configure the Java exec tasks and set the Java launcher like this. Let's make the application print the Java version and execute the run task. So now we're compiling with version 15 and running with version 16. And you can use a similar approach with the Java compile and test tasks. The key takeaways from this lesson are that the Java version for running Java processes started by Gradle is by default the same as the Java version used to run Gradle itself. You can set a specific Java version by setting a Java toolchain configuration. This will find a local version or download one from the internet. By default, tasks of class type Java exec, Java compile, and test will use this version, but you can override the Java version by configuring specific tasks. See you in the next lesson. Now that you know how to build, test, and package your Java application, let's move on to publishing it. This is where your application artifact is transferred from the build directory to a remote Maven repository, whether public or private. Whatever deployment mechanism you use can then pull that artifact from that repository. To do this, we need an additional core Gradle plugin called Maven Publish. This lets you configure what artifact to publish, as well as which Maven repositories to publish to, and you can publish to multiple repositories if you need to. It handles generating everything required to publish Maven, including the POM.xml file, much of which can be customized. To see how this works, we're going to add this plugin to the Theme Park Rides status project. We'll configure it to publish the jar file generated by the jar task to a remote Maven repository I own in AWS. Since my repository is private, lots of top-secret artifacts in there, we'll have to be careful to properly handle the credentials within our build script. Picking up from where we left the project in the last lesson, let's apply the Maven Publish plugin. Then, at the bottom of the build script, we'll call the Maven Publish plugin's configuration method publishing, passing a closure. We have to configure two things now. The first is the artifact we want to publish, and then the repository we want to publish it to. To specify the artifact, we have to define what's called a publication, which we do with this syntax, passing a closure. Within this closure, we say Maven publication, passing yet another closure. And within here, we need to specify what we're publishing, which we do using from components.java. In Gradle, components are defined by plugins and provide a simple way to define a publication for publishing. This Java component has been added by the Java plugin and represents the jar file created by the jar task. Now define the repositories where we'll publish the artifact. The syntax here is the same as the syntax we use to define repositories from which to pull dependencies. Since my repository is in AWS, I'm going to cheat by using the AWS console to generate the Gradle code snippet for me. I'll paste it in Repositories. The syntax should look somewhat familiar, except for the credentials configuration you haven't seen yet. It takes a closure with a username and password, with the password coming from an environment variable I set on the command line. Don't worry too much about this syntax for now, since we'll be exploring all the ways to pass project properties and credentials to your Gradle build in the next chapter, so consider this a sneak preview. That's everything we need to add to the build script to publish this artifact. Back on the command line, I'm going to set the code artifact auth token environment variable used by the build for access to my AWS repository. Now let's run Gradle wpublish. We get an error saying group ID cannot be empty. OK, so we need to set a group and version on our project which the publish plugin will use by default. Put that towards the top of the build file using a group of com.gradlehero and a version of 010 snapshot. Run publish again. And this time we have a success. Let's run it again with the -- console equals verbose option so we can see what tasks have been executed. So it's generated metadata, generated a POM file, and done the actual publish. I demand a bit more proof than this, so if we look in the AWS console for my repository, we can see that indeed the artifact has been published with version 010 snapshot. Very cool. Something else you can do with the Maven Publish plugin is publish to your local Maven repository, which lives in your home directory /.m2/repository. Just run the task publish to Maven local, and we see the artifact has been added. One use case for this is if you need to share a library between projects, but you don't want to publish to a remote repository, which could be when you're testing changes. If you've come from the Maven build tool welder tool, this feature is the same as running Maven install. The key takeaways from this lesson are that we can publish artifacts to Maven repositories using the Maven Publish plugin. To use the plugin, we need to specify a group and version, publications, and repositories. And you can publish to your local Maven repository using the Publish to Maven local task, which can be useful for sharing libraries between local projects without publishing remotely. See you in the next lesson. So far in this chapter, you've learnt a lot about the fundamentals of working with Java projects in Gradle without looking at any specific Java frameworks. One of the most popular Java application frameworks is Spring Boot, which comes with tight integration with Gradle, which is why it's relevant to this course. Spring Boot reduces the amount of boilerplate code developers have to write and lets them focus instead on business logic. So how can Gradle help us build Spring Boot applications? That's exactly what you'll learn in this practical lesson, but first up, a bit more on how Spring Boot works. It's the dependencies on the class path that enable Spring Boot functionality. Spring Boot detects them, automatically enabling certain features. The dependencies that you use in Spring Boot are called starters. For example, Spring Boot Starter Web creates a web application which responds to requests over the network. There are two Gradle plugins that make life quite a lot easier working with Spring Boot. One of them, the Spring Boot plugin, adds tasks to run a Spring Boot application and also generate an executable jar file. The other plugin, the Spring Dependency Management plugin, as you might have guessed, manages versions of Spring Boot dependencies, ensuring they stay consistent. One of the great things about creating web applications with Spring Boot is that they contain an embedded web server, by default Tomcat. This means you can just execute the jar file and Tomcat will start serving your application. We've been asked by Theme Park HQ to create a simple Spring Boot API application which, when sent a request to /rides, will return a JSON response containing all three theme park rides. This is an essential business-critical requirement, as this API will later be used across the park and also on the theme park's website to tempt customers to buy tickets in advance. This is a practical lesson, so please follow along with the steps in this video or complete them from the notes below. Only minimal Java knowledge is required since all the code can be copied and pasted from the notes. What's important is to get a feel for how Gradle makes life easier for Spring Boot development. Create a new directory called Theme Park API, cd into it, then using Gradle init, create a basic project in Groovy. We'll start with the most basic implementation of a Spring Boot application in Gradle without any special plugins, then build up from there. Open the project in your IDE of choice. In my case, that's IntelliJ IDEA. In the build script, delete the comments, apply the Java plugin, add the Maven central repository, and add an implementation dependency on Spring Boot Starter Web, which is in the group org.springframework.boot. I'm using version 2.5.3, but you can find the latest version at the time you're watching this from mvnrepository.com. We're going to make use of the Java 16 record feature in this example to model our theme park ride. To ensure we're using the right version of Java, we can configure the Java toolchain, which you now know how to use from the recent lesson on Java versions. So configure the Java toolchain with version 16 like this. That's all the changes to the build script we need, so if you're using IntelliJ, load the Gradle changes to check everything's okay. Notice that we haven't introduced any new concepts at this point, we're just using what you've already learned so far in this course. We need to add 3 classes to the project, create the directory source/main/java, and a package com.gradlehero.themepark. Create a theme park application class in the new package. Copy the code from the notes into the class. This class has a Spring Boot application annotation and main method, making it the entry point to the application. create a theme park ride record class, add the name and description like this, or you can copy it from the notes. This represents a single ride and uses Java 16 records, so is very concise. Finally, add a theme park ride controller class. Copy the class contents from the notes. This class gets called when a request is made to the application. It has an annotation to register it as a Spring controller. There's also an annotation which means when a request is made to /rides, the getRides method is called, returning our 3 theme park rides. That's everything you need to build a basic Spring Boot web application in Gradle. If you haven't used Spring Boot before, don't worry about the code details. What's important will be how you build and run it with Gradle. Now on to running your application. If you're using IntelliJ IDEA, you can open the theme park application class, right-click and select Run. You should get a message saying the application has started on port 8080. In a browser, go to localhost 8080/rides, and the response has the 3 rides in JSON format. Very nice. Another approach to run this application from the Gradle command line directly would be to swap the Java plugin for the application plugin. So do that now. Then provide an application plugin configuration specifying the main class. Stop any application you have running, then run it again, this time with Gradle wrun. And see that you can successfully make the same request. Different approach, same result. But rather than using the application plugin, a better approach is to apply Spring Boot's own Gradle plugin, which does 3 main things. It automatically discovers the Spring Boot application class based on the Spring Boot application annotation, so you don't have to configure a main class. It also adds a boot run task for running the application, and a boot jar task which creates an executable jar file containing all the dependencies. Revert the application plugin back to Java and remove the application plugin configuration. Add the Spring Boot plugin instead, with the version of the plugin being tied to the Spring Boot version. Run Gradle W tasks, and any tasks starting with boot have been added by the plugin. The ones you'll be using soon are boot run and boot jar. Run Gradle W boot run from the command line or your IDE, and you'll see the application start in the same way as before. This time though, we didn't have to specify any main class name. Note that the boot run task is of type Java exec, so you can configure it in the same ways as you saw in the earlier lesson on running Java applications. The task dependency graph for assemble now shows a new task dependency on boot jar. That means if we run assemble, the executable jar file will also get created. So run Gradle W assemble, then have a look in the build/libs directory. You'll see 2 jar files. What the Spring Boot plugin does is rename the non-executable standard jar to -plain and uses the default naming convention for the executable jar. So themeparkapi.jar is the executable version. You can run it with java-jar, then the file path, making sure you're using Java 16 or later. That should run, with the rides API still working properly. Having a single executable jar file is much more helpful, as it can be passed around and executed when needed very easily. The boot jar task is of type jar, which means that any of the configurations of jar work here too, like for example setting the archive file name, include and exclude. Looking at our build script now, there is some repetition in the Spring Boot version. That's not a massive problem at the moment because we've only got one Spring Boot dependency, but projects might have many more than this. You already saw that you can use the Extra Properties feature to specify a version variable once and reuse it in several dependencies. When working with Spring Boot, though, a better approach is to use the Dependency Management plugin. The great thing about this plugin is that when it's applied, it will set the version of Spring Boot dependencies automatically based on the version of the Spring Boot plugin. Apply the plugin to your build script like this. Now take out the version of Spring Boot Starter Web. Much nicer. Load Gradle changes if you're using IntelliJ IDEA. Run the application again with Gradle wboot run. And make sure you can still successfully make a request. Well done, you've just created an API application with Spring Boot following the best practices of using the Spring Boot and Spring Dependency Management plugins. Commit the changes, run git init to initialize a Git repository, add the .idea directory to the .gitignore file if you're using IntelliJ IDEA, run git add dot, then git status to check what's being committed. If you're happy, run git commit -m with the message initial commit of theme park API. We covered a lot in this lesson, but if you're developing Spring Boot applications, you should now have a good idea of how the related Gradle plugins work to make your day-to-day development simpler. Here are the key takeaways. Use Spring Boot Starter dependencies to automatically add Spring Boot functionality to your application, like the Spring Boot Starter Web dependency for web applications. The Spring Boot plugin conveniently adds the boot run task, which detects and runs the main Spring Boot class. It also adds boot jar, which creates an executable jar file containing all the required dependencies of your application. Use the Spring Dependency Management plugin to automatically apply versions to dependencies based on the version of the Spring Boot plugin you're using. See you in the next lesson. As mentioned earlier in this chapter, in Gradle you can create two types of Java projects: applications and libraries. An application is a project creating a standalone service which actually gets run, like a web application, a service serving up an API, or a desktop application. This is what we've been dealing with so far in this chapter, and is what you've just created in the practical lesson. On the other hand, a library is a project creating an artifact that isn't intended to be run standalone, but is instead consumed by other libraries or applications to create something else. For example, Spring Boot Starter Web is a library. It's consumed by web applications but can't be run on its own. Another way to think of these is using the consumer and producer model. An application is a consumer because it uses other libraries, while the library is a producer because it generates an artifact to be consumed by others. Why is this important? Well, as a producer of a library, you need to think about how your transitive dependencies affect your consumers. By default, any implementation dependencies of the library you're creating will end up on the runtime class path of any consumer, but not on the compile class path. To understand why this is important, we need to take a step back to learn about the Application Binary Interface, or ABI. Imagine a scenario where we have a theme park API application that has a dependency on a theme park rides status library. The intention here is that the application needs the library to get the ride status to serve on its API. Theme park ride status is the library. It's been slightly extended from the version used earlier in the chapter to depend on both the Commons Lang3 and Jackson Databind libraries. Jackson Databind is a library which makes it easier working with JSON. In ride status service, the first thing to note is that the main method has been removed to transform this project from an application to a library. It uses string utils from commons lang 3 to trim the ride name, as you saw earlier. Now though, getRideStatus returns ObjectNode, which is a class from the Jackson DataBind library. This just represents a JSON object with a key-value pair, in this case status and the actual ride status. Note how ObjectNode is contained in the method signature, whereas string utils is only used within the method body. We say that ObjectNode is on the application binary interface, or ABI, of the class, whereas string utils is not. This is significant since for anyone consuming this library, any classes or types on the ABI must be available at compile time, whereas non-ABI classes are only needed at runtime. The relationship between the four projects then looks like this. Theme Park API depends on Theme Park Ride Status, which itself depends on Jackson DataBind within the Ride Status Services method signature, and commons lang 3 within the method body. This will make more sense if we look at things from the perspective of the consumer application, Theme Park API. First though, let's run the publish to Maven local task within Theme Park Ride Status to make this library available to any consumers. The Theme Park API project has been somewhat simplified, and we now apply the Java plugin and have a single dependency on the Theme Park Rides status library, which is published to my local Maven repository. The Theme Park application class has also been simplified to make a single call to Ride Status service to get the status of the roller coaster. Looks like we have a problem though. If we try to run this class, we get an error from the compile Java task saying object node not found. Once again, since object node is on the ABI of the library, or in other words, it's in the getRideStatus method signature, it's required at compile time by the consuming application. Here are some more specific details about the ABI. ABI types include return types, which we've seen with the object node, public method parameters, types used in parent classes or interfaces. Types that don't fall into the ABI include types used in method bodies, and types defined in private method declarations. The important thing to remember about the ABI is that any types used within it need to be declared on the compile class path of the consuming application. Let's think about how we'd build up the compile and runtime class paths for the application. The compile class path should contain Theme Park Ride Status, as we interact directly with the Ride Status service class, and Jackson DataBind as Ride Status service exposes object node on its method signature. Commons lang 3 isn't required here, as it's not part of the ABI of Ride Status service. And the runtime class path should contain Theme Park Ride Status and Jackson DataBind for the same reasons just mentioned, and commons lang 3 since string utils is used internally in Ride Status service. If we had the ability to build up these class paths selectively like this then, some of the benefits would be cleaner class paths. We won't accidentally use a library that we haven't depended on explicitly. For example, we can't use string utils in Theme Park API if it's not on the compile class path. Faster compilation due to our cleaner class path, and less recompilation as when artifacts defined only on the runtime class path change, we don't need to recompile. Gradle's core Java library plugin makes this fine-grained class path control possible. It allows you as the creator of the library to define which dependencies should be included in the runtime or compile class paths of whatever application is consuming the library. To achieve this, the plugin adds an additional dependency configuration, API. API dependencies are part of the library's ABI and will therefore appear on the compile and runtime class paths of any consumers. Implementation dependencies aren't part of the library's API and will appear only on the runtime class path. With this knowledge, we can go back to Theme Park Ride Status, apply the Java library plugin, and fix its dependencies so the Theme Park API application can work properly. Back in Theme Park Ride Status, swap the Java plugin out for the Java library plugin, whose ID is just java-library, All we need to change now is the Jackson DataBind dependency declaration from implementation to API. And let's publish to Maven local again so the application can pick up the latest version. Back in Theme Park API, we can rerun the theme park application which failed earlier, and now it has compiled and run, returning the rollercoaster status as expected. That's because it's picked up the newly published Theme Park Rides status library and figured out that Jackson DataBind now also belongs on the compile class path. To fix the errors in IntelliJ IDEA, just select Reload all Gradle projects from the Gradle panel. The last thing for you to see before summarizing should satisfy your curiosity if you're wondering what Gradle is doing in the background to manipulate the class paths like this. If we look inside the POM file of Theme Park Rides status in my local Maven repository, all will become clear. Under Dependencies, we have both the expected dependencies, but importantly, Jackson DataBind has a scope of compile and Commons Lang 3 of runtime. In Maven terminology, a compile scope dependency gets added to all class paths, and obviously the runtime dependency only goes onto the runtime class path. That's how Theme Park API can now successfully compile and run, this time with elegantly constructed clean class paths. The key takeaways from this lesson are that by default, when using the Java plugin, implementation dependencies of a library will end up on only the runtime class path of a consumer. The application binary interface represents any types which are required for compilation, for example types that appear in the method signature but not the method body. Any types that appear on the ABI of the library need to be on the compile and runtime class paths of the consumer. The Java library plugin allows us to achieve this with the API dependency configuration, which makes a dependency appear on the compile and runtime class paths of the consumer. And all this helps to keep class paths clean, improving performance and maintainability. See you in the next lesson. You've seen that including the Spring Boot plugin in your Gradle project generates an executable jar file. This includes an embedded Tomcat server, so as long as Java is available in the deployment environment, no other software is required to run your application. Whilst this is the approach I recommend, sometimes when working with older projects, you might have a requirement to deploy to a standalone Tomcat server. In this case, Tomcat is installed on a server, and to deploy your application there requires a web application resource WAR file. Since the jar file generated by the Spring Boot plugin isn't a WAR file, we'll have to do something different. The core Gradle plugin WAR replaces the jar task with a WAR task, which generates a .war archive following the required conventions. What's more, the Spring Boot plugin is intelligent and reacts to the WAR plugin by replacing the boot jar task with boot WAR. This produces an executable WAR file, as you'll see in a moment. Finally, to make a Spring Boot application compatible with the WAR format, we need our main application class to extend Spring Boot Servlet Initializer. Let's make all these changes on the Theme Park API project so we can deploy it to a standalone Tomcat server. So we'll modify Theme Park application to extend Spring Boot Servlet Initializer. That's the only application code change. In the build script, replace the Java plugin with the WAR plugin. The WAR plugin actually applies the Java plugin, bringing in most of the same functionality. The task dependency graph for Assemble now shows task dependencies on WAR and boot WAR. So run Gradle wassemble and have a look in the build/libs directory. We've got two new WAR files, a plain non-executable version generated by the WAR plugin, and an executable version generated by the Spring Boot plugin. It may sound strange that this WAR file would also be executable when it's intended to be deployed into an application server like Tomcat, but it actually works for both use cases. We can run the executable WAR file with the java-jar command like this, and that works fine. We can also run the same executable war file on a standalone Tomcat server. Let's use Docker to run Tomcat and copy our war file into the Tomcat Web Apps directory. This is where Tomcat looks for war files, and anything it finds there, it deploys. This simple Docker file uses Tomcat 9 and copies our war file into the right location. Let's build the Docker image. And run a Docker container from that image. I can now access the API on the path of the deployed web application and get the same response. Note that in the Docker file we're using Tomcat version 9 even though 10 is available. Tomcat 10 is currently not compatible with Spring Boot, but there are plans to fix that for the Spring Boot 3 release. Here are the key takeaways from this lesson. To deploy an application to a standalone Tomcat server requires a war file. Spring Boot applications need to extend Spring Boot Servlet Initializer to be compatible with war files, and replace the Gradle Java plugin with the war plugin to generate a deployable and executable war file. See you in the next lesson. At this point, you now have a good understanding of how dependency configurations generate the compile and runtime Java class paths. So in this lesson, you'll learn some more advanced techniques to control transitive dependencies to help solve some common problems. First, a note on terminology we'll use in this lesson. A direct dependency is a dependency that's declared within the build script. For example, this could be a specific library, like Guava, that your application's source code uses. That's in contrast to a transitive dependency, which is included in your project only because another dependency needs it. For example, the Guava library uses the Checkstyle library. Before moving on to some example problems and how Gradle helps us solve them, we need to learn more about dependency resolution in Gradle. The whole premise of this is that for each dependency group and name, there should only be one version that appears on the Java class path, whether that's a single version of Guava, Spring Web, or any other library. But multiple versions for the same dependency group and name can appear within a dependency configuration when direct dependencies bring in transitive dependencies of different versions. That's a problem that Gradle solves through a process called version conflict resolution. Gradle's rule is actually quite straightforward since it just chooses the highest version. So imagine that the implementation configuration has two versions of Checkstyle. Guava pulls in version 3.12.0 and another direct dependency specifies version 3.11.0. In this case, 3.12.0 wins because it's the highest. That means 3.12.0 is the version which will actually appear on the compile and runtime class paths. You can see that here with the arrow denoting the overridden version. By the way, this output has been generated with the dependencies task, passing a specific dependency configuration. There's an entire lesson on this task in the chapter on troubleshooting, so just know for now that the output shows us the transitive dependencies of each direct dependency within our build, including the versions. Before diving into how to get greater control of dependencies in Gradle, let's consider some possible scenarios that would benefit from this. In scenario 1, our project has a direct dependency on Google's Guava library. Guava pulls in several transitive dependencies. Since our application built by this Gradle project uses only one specific method within Guava, in this scenario we're 100% sure that we don't need the findbugs JSR 305 library. We'd simply like to exclude it to reduce the number of libraries required in our deployable artifact. In scenario 2, we have another project, also with a direct dependency on Guava. This is in fact the latest version at the time of recording. Imagine that we learn of a critical security vulnerability in the Checkstyle transitive dependency. The team responsible for Checkstyle very quickly release a new version 3.13.0 with the fix. However, the Guava team may take longer to release a new Guava version to incorporate the fixed version of Checkqual. In this case, we're stuck on the old insecure version of Checkqual. We could add a direct dependency on the new version, but that would incorrectly model our dependencies since our code doesn't directly interact with Checkqual. An option to use the new library version without adding a direct dependency would be ideal. In scenario 3, we have another project which depends on the Spring Boot Starter Web framework. This by default uses the logback logging framework, but for whatever reason we'd like to switch to Log4j 2 instead. So we add a dependency on Spring Boot Starter Log4j 2. But at runtime when we try using the logging framework, we get errors about multiple logging libraries being on the class path. We'd like a way to fix these issues by easily excluding the conflicting logging libraries. So let's run through the options Gradle offers and see how they address these three scenarios. The first and simplest option is the one you already saw in the Chapter 3 lesson on repositories and dependencies. It's where we add an exclude rule on the dependency itself. This lets us specify a transitive dependency that Gradle should not include in the dependency configuration. This helps us solve scenario 1, where we wanted to remove a library we knew would never be used. We can just add an exclude rule within the Guava dependency definition for findbugs JSR 305. Now within our runtime class path dependencies, findbugs is nowhere to be found. A dependency level exclude also helps with scenario 3, since we can exclude the conflicting Spring Boot Starter logging dependency, which we don't need on the runtime class path. Now our code runs fine and logs the expected line. The problem with adding an exclude rule to a direct dependency is it only works for that specific dependency. If another direct dependency pulls in the same excluded transitive dependency, the exclude rule is ignored. For example, in scenario 3, if we decided we wanted to start using the Spring Boot Starter Hateos library, then the problem comes back. That's because Spring Boot Starter Hateos also pulls in Spring Boot Starter logging, which contains the conflicting runtime dependencies. To solve this, Gradle offers exclude rules that are evaluated across a whole dependency configuration. In our case, we'll exclude Spring Boot Starter logging from the entire implementation configuration, removing the dependency level exclude we had before. The new configuration level exclude rule fixes our problem. The rule is applied to all Spring Boot dependencies and will work for any others we add in the future. Pretty cool. Use this approach only when you're confident that the transitive dependency should always be excluded from all direct dependencies. This approach would work for scenario 1, but for this reason a dependency level exclude rule would be better. Another option you have in Gradle is to replace one dependency with another, meaning when one specific transitive dependency group and name is found, it will be replaced by another entirely different group and name. That's useful for scenario 3, which can benefit from replacing Spring Boot Starter logging with Spring Boot Starter Log4j 2. We specify the group and name of the module to be replaced, and then its replacement, including an optional reason. And of course, we no longer need the exclude rule. Our code still executes OK. Module replacement is actually the recommended approach within the Spring Boot documentation. Gradle's dependency constraint allows you to introduce an additional version to be considered during version conflict resolution. Back in scenario 2, where we have a single direct dependency on Guava, since we need to increase the Checkqual version to 3.13.0, we can add a constraint on this version. We use the constraint syntax on a specific dependency configuration, passing a group, name and version, as well as an optional reason for the constraint. Now our runtime class path contains the newer version of Checkqual, shown by the arrow pointing to 3.13.0. There are two important considerations when using constraints. First, the constraint itself doesn't pull in the dependency. The version specified by the constraint is only considered if another direct or transitive dependency has the same group and name. For example, if we have no declared dependencies and a constraint, this results in an empty runtime class path. The constraint is slightly confusingly named since it's more of a recommendation than a constraint. For example, if we change the constraint version of Checkqual to one lower than the version pulled in by Guava, the constraint is ignored since Gradle picks the highest version. So the main use case for the constraint is when you want to increase the version number of a transitive dependency. Here are the key takeaways from this lesson. Use a dependency level exclude rule to exclude a transitive dependency from a single direct dependency. If the transitive dependency is also pulled in elsewhere, then the rule will be ignored. Use a configuration level exclude rule to exclude a transitive dependency across an entire dependency configuration when you're sure that the library should never be included. Use a module replacement rule to replace one group and name with another. And use a dependency constraint to add another version to be considered in the version conflict resolution process. This is helpful for increasing the version of a specific transitive dependency. See you in the next lesson. Welcome to the next chapter where you're going to learn techniques to keep your Gradle project well maintained, easy to understand and extensible. Hopefully by now you appreciate that using Gradle gives us engineers powerful ways to add rich functionality to our build through plugins, tasks, or custom code written directly in the build script. With great power comes great responsibility though. As a project grows, the build logic is likely to become more and more complex, leading to problems understanding, let alone maintaining it. Fortunately, Gradle has some tools in its tool belt, meaning your build can scale up with your application. This encompasses best practice techniques like splitting Gradle projects into logical subprojects and encapsulating build logic into reusable tasks or plugins. By the end of this chapter, you'll have a firm grasp of these concepts, along with the confidence to implement them in your own Gradle projects proactively from the start. A Gradle project property is a property that gets passed in from an external source when your build is executed, and can be accessed in your project's build script. Just like you might externalize configuration from an application so it can execute differently in different scenarios, the same applies to your Gradle build. One big reason to use project properties is to avoid storing credentials or other sensitive information in version control. This build.gradle is based on the lesson from the last chapter about publishing to Maven. It configures the Maven Publish plugin to publish a jar file built by the Java plugin. When Gradle wpublish is run, the jar gets published to my personal top-secret repository in AWS. It's top secret because I'd never allow you or anyone else to see the password. Oh no, that's a bit silly. Looks like I accidentally included the password in the build script. Well, I'm probably not the first to do this. Assuming we're committing our code into version control, then this represents bad practice, since anyone who checks out our code would immediately have access to the credentials. Much better would be to pass the credentials in externally using Gradle project properties. The build.gradle just needs to be modified slightly. Now when we call the publish task, we can pass the properties in using the -p flag like this. When working with repositories, there's actually an even better way to achieve the same thing with less code, by giving your repository a name and telling Gradle that it uses password credentials. Gradle will then look for a username and password property prefixed with the repository name you specified. Another reason to use project properties is when the build needs to run differently depending on the situation. For example, here the Maven repository URL is hard-coded. There may be a requirement to sometimes push to a different repository, in which case we could also use a project property. Here are some other ideas of when you might use project properties. Deployment. If your Gradle build is responsible for deploying, then you may need to pass in extra information such as the environment and region to which to deploy. Test memory allocation. The Gradle test task allows you to configure its max heap size property. By using a project property, you can externalize this configuration and easily tweak the memory allocation for different environments. Database connection string. If your build needs to connect to a database to run tests, you could use a project property to provide the option to connect to a different database. Gradle has several ways to pass project properties into a build, some of which have higher priority than others. Or, in other words, the same property key can be passed into the build in multiple ways, but the one with the highest priority wins. We'll run through them from the highest to lowest priority. And at the highest priority, we have on the command line when calling Gradle with -p. Next up is as Java system properties using -d. Then it's environment variables. And then in a Gradle.properties file located in the Gradle user home directory, which is normally your home directory /.gradle/gradle.properties. And this file is a list of key value pairs, each of which represents a property name and value. And finally, in a Gradle.properties file located in the project root directory. And you could use this option when the Gradle.properties file should be committed to version control and shared with other team members. By the way, not only can you configure project properties in Gradle.properties, but you can also pass non-project Gradle properties. For example, we discussed in Chapter 2 how to generate verbose build output by specifying --console equals verbose on the command line. You can get the same outcome by adding org.gradle.console equals verbose to the Gradle.properties file. The advantage of this is that the property will be applied whatever project you work in. I'll provide a link to the full list of non-project Gradle properties in the notes. Back to project properties now. Once a property has been passed into our build, there are three ways to access it. Firstly, you can treat a project property as a variable and just reference it by name. To illustrate this, here's an almost empty build script with a task that prints the value of the property myPropName. We can pass in the property using the -p syntax. If we don't pass a property value, then an unknown property error is thrown. Gradle provides the following method to access a property. Our example changes to this. Like before, if the property is not found, then an unknown property error is thrown. You might prefer this option to the first option since it's clearer to whoever is reading the build logic that you're trying to access a project property. When we need to access a property but don't want an exception to be thrown if it's not provided, use the findProperty method. Our example changes to this. This time, if the property is not found, null is returned. This can be very useful if we want to return a default value, which we can do using Groovy's Elvis operator. Finally, we can check for the existence of a property using the hasProperty method. This could be used where we have some build logic that's only enabled if a specific property is set. The key takeaways from this lesson are that project properties are a way to separate configuration and credentials from your build script. By externalizing configuration like this, it allows the build to be customized in interesting ways when it's executed, and to follow best practice security by keeping credentials out of version control. We can pass project properties into a project from the command line using -p, -d, environment variables, and Gradle.properties files in either the user home or project directory. In Gradle.properties files, you can also set non-project Gradle properties such as org.gradle.console equals verbose. Once a project property has been injected into a build, it can be accessed directly as a variable, using the property method, or using findProperty to avoid throwing an error if the property doesn't exist. Property existence can be specifically tested using hasProperty, which returns a Boolean value. See you in the next lesson. All the projects we've worked with so far have consisted of a single project, meaning that all of our source code and resources have been contained in a single directory, source/main. That can work well for small software projects as it keeps things simple, but as projects grow, we need to identify ways to group different areas of code for maintainability. One way to do this is to split the software into separate modules, or in Gradle terminology, separate projects to form a multi-project build. In this lesson, you'll learn why you'd want to use multiple projects, how to implement multi-project builds, and how to interact with them effectively. First off, let's look in a bit more detail about the use case of needing to split a growing software project into multiple modules. An example of such a project could look like this. There's a UI layer which purely consists of static HTML, CSS, and images rendered in the user's browser. The API layer represents a server-side application responding to HTTP requests from the UI, and the DB layer handles database connection logic and is consumed by the API layer. Each of these layers in Gradle can be modeled as a project, or more specifically, a sub-project of the main project. That's a lot more helpful than putting everything into one project, as we can apply specific build logic to each sub-project. For example, making sure the API and DB sub-projects are compiled as Java projects. It also allows more strict enforcement of interaction between these layers. For example, we might want to say that the API layer can access the DB layer, but not the other way around. If these layers were contained in a single project, that might be difficult to enforce, but with a multi-project build, we can model that with a single line of code in our build script. Even if you had a large software application in a single Gradle project that was well organized to enforce maintainability, there is still a performance impact to take into consideration. When small code changes are made, the whole codebase has to be recompiled. The time it takes to do this directly depends on the amount of code there is to compile. So with large projects, the time it takes to compile can become a burden. In this case, moving to a multi-project setup will help, since now a small code change will force recompilation of only one sub-project, saving a lot of time. Perhaps the simplest way to get going with a multi-project build is using Gradle init. So far, we've only used Gradle init to create basic projects, but now you'll see that when we create a Java application, it actually defaults to a multi-project build. So within an empty directory, I'll run Gradle init, select Application, select Java, select No as we're interested to see the simple use case right now, select Groovy, JUnit Jupyter, the default project name, and a package of com.Gradle Hero. When I open this project in IntelliJ IDEA, notice how we have a directory app, which contains a source directory following the standard structure of a Java project. App is the name of the subproject, and its contents live within this separate directory. Let's open the build script in the app subproject generated by Gradle init. It should look very familiar to you, using many of the concepts you've learnt so far in this course. So a subproject can have its own build script, which can reference code and resources from that subproject. In this case, the application plugin is applied, which will reference the contents of the app/source directory. Let's try running this application. Since it applies the application plugin on the command line, we can just run Gradle wrun, and I'll run with --console equals verbose so we can see what's going on in more detail. Hello world is the expected output of this application, and everything else looks similar to if we had executed the same task in a single project build, except that the task names are prefixed with the subproject name. Sounds pretty sensible. Before we move on to make this multi-project build a bit more multi, well, there's only one subproject right now, let's explore the top-level project known as the root project. You'll notice this contains most of the files and directories you're used to seeing in a standard Gradle project, including the .gradle cache directory, the Gradle directory containing the wrapper files, and the Gradle wrapper scripts themselves. There's also the settings.gradle file. In a multi-project build, all these files live in the root project only. It's only the build.gradle that lives in the subprojects, along with any specific code and resources that's being built in that subproject. Let's take a look at the settings.gradle file. Not only does it set the root project name, but there's an additional line which calls include with the string app. This incorporates app into the overall Gradle project. Right now we only have one subproject, but this is where you declare any more. Let's try adding another subproject. I'm going to take out the brackets since they're not required here, and copy this line but change app for service. I want to create a service subproject which will contain code to randomly return one of two messages to be printed out in the app subproject. If we run Gradle W run again, we can see that everything's still working. A subproject in Gradle doesn't need a directory or a build.gradle to exist. It just has to be declared in settings.gradle. We can verify this by running Gradle W projects, which now shows we have a root project with two subprojects. We do want our service subproject to do something though, so I'll create its own directory in build.gradle. Let's load Gradle changes and notice how IntelliJ IDEA has recognized it as a subproject. In the build.gradle, we'll just apply the Java plugin. That's it, load Gradle changes. And I'll add a package structure and a class messageService.java. This class contains a method which returns one of two messages randomly. Back in the app subprojects build.gradle, we're going to make a change which means we can use code from the service subproject in this subproject. You do that by defining a dependency, in our case an implementation dependency, but rather than specifying a library, we reference another subproject using this syntax. Load Gradle changes. Let's open the code for the app subproject. This class is what printed the message Hello World earlier. We can now change the getGreeting method to instead call messageService.generateMessage. Now when we run the application again, we get a random message. Very cool. So we're now running an application which is split across two subprojects using code from the service subproject within the app subproject. When it comes to executing tasks in multi-project builds, we have a few options. By default, any task names you pass to Gradle W will get executed against any subproject that contains that task. For example, if we run clean, we can see that it's been executed on both the app and service subprojects. However, if we execute a task that's only contained within app, for example run, the task only gets executed against app. In this case, we're also getting tasks executed against service, since app depends on service and Gradle needs to make sure the jar file has been built, but it's not trying to execute the run task against service. You can execute tasks against a specific subproject by using what in Gradle lingo is called a fully qualified task name, which includes the fully qualified project name and task name. The fully qualified project name can be found from the Gradle W project's output. In the case of app, it's a colon, then the project name. To execute clean within the app project, we add another colon, then the task name. You can see it's now executing clean against app, but not service. By the way, the initial colon is optional. If I take it out, it does exactly the same thing. In many cases, it should be sufficient to execute tasks using an unqualified name. For example, when building and testing your application, just run Gradle W build to build everything across the whole project. If you had multiple subprojects with a run task, though, you might want to execute only the one you're interested in. That's when you'd want to use a fully qualified task name. The key takeaways from this lesson are that Gradle multi-project builds promote modularization of your software project, which helps with maintainability and performance. In a multi-project build, each subproject can have its own directory and build.gradle, although these aren't mandatory. Inside the settings.gradle, at the top level of the project, you define include statements, which tell Gradle which subprojects to include in your build. Any tasks passed to Gradle W will be executed against any subprojects that contain that task. Use a fully qualified task name to execute a task against a specific subproject. The fully qualified task name consists of the project path and task name separated by colon. See you in the next lesson. You now know theoretically how to work with multi-project Gradle builds, but it's time to put that into practice in another practical lesson. Thankfully, Theme Park HQ have been in touch again with another assignment. Bowled over by the success of both Theme Park Ride Status and Theme Park API, they'd like to add a UI so that ride management can be centralized through one friendly web interface. The UI should return details of all the theme park rides, including their name, description, and status. They'd also like us to integrate with the latest webcam image for each ride so employees can verify that customers have smiles on their faces. The plan will be to reuse what we've already got as much as possible. We'll create a new Gradle project called Theme Park Manager containing 3 subprojects. The service subproject will be a copy of the Theme Park Rides status project. The API subproject will be a copy of the Theme Park API project. And a new UI subproject will contain the front-end HTML, images, and CSS, which you'll find contained in a zip file, ui.zip, in the notes below. All of this will be served from a single Spring Boot application, handling both requests for the API and UI assets. And the end goal is to run Gradle W boot run and access the website at localhost 8080. This is a practical lesson, so please follow along with this video or follow the step-by-step instructions in the notes below. Let's get cracking then. First things first, you need to create a new directory, Theme Park Manager. cd into that directory, then run Gradle init, create a basic project, Groovy, default project name, and now we're going to copy both the Theme Park API and Theme Park Ride status projects into this project. And just as a reminder, you should have these 2 projects as a result of the 2 practical lessons from the last chapter. So we'll start off with the Theme Park API, and in a Linux environment you can use cp-r, then the source and destination. And then the same again for the Theme Park Ride status project. Check the contents of this directory and make sure you've got the 2 directories contained in the root project directory for Theme Park Manager. Now there's a command in the notes below that's going to do some cleanup in each of the subprojects. It's going to remove things like the Gradle wrapper scripts, which we only need to be contained in the root project. So go ahead, copy that command, and then navigate into Theme Park API. And run that command. And then do the same thing in Theme Park Rides status. And if you have a look in one of these directories, you should just have a build script and a source directory containing the code. So let's go back to the top level. And we're going to rename these directories to make things a bit more straightforward. So we'll rename Theme Park API to API, which in Linux we do using MV. And we'll rename Theme Park Ride status to just service. Let's double check the contents here. And if your project looks like this, you're good to continue, and it's time to open this project in your IDE of choice. So here's the Theme Park Manager project, and you can see that IntelliJ IDEA hasn't recognized API and service yet as subprojects. To fix that, we'll go into settings.gradle of the root project, and right at the bottom we'll add the include, in single quotes, API. And in the last lesson you saw one way to do this, which is to add another line with another call to include, but you can also pass the subproject names separated by comma. So we'll try that now. So that's comma and then service in single quotes. Load Gradle changes. And now IntelliJ has recognized these 2 subprojects. Open up the build.gradle for the service subproject. And we're going to make one tweak, which is to change the Java plugin to Java library, because this project will be a library consumed by API. Now, before we go any further, let's just check that we can actually build this whole project. So on the command line, run Gradle W build with --console equals verbose. And that looks good. It's building and testing for both API and service subprojects, and it's been successful. And you can even run Gradle W boot run. That started the Spring Boot application of the API subproject. And in a browser, go to localhost 8080/rides. And we've got the rides with a name and description. But we need to add the ride status and also the webcam image URL. So let's fix that now. Go into the build.gradle of the API subproject. And we're going to add a dependency on the service subproject so that we can call services ride status service to get that ride status. So add an implementation dependency and then use the syntax project with the subproject name. Load Gradle changes. And now we're going to be able to access ride status service from within the code of API. So open up the code of API. And first off, open up theme park ride. And we're going to extend this entity class by adding a status and image path, both strings. And you can type this in yourself or copy the code from the notes. Now open up theme park ride controller. And you'll see right here we've got errors because it's expecting a status and image path to be passed in. To save time, you can just copy the code from the notes. So the first two arguments are the same, the ride name and description. Then we're calling ride status service.getRideStatus, passing the ride name. That returns us the ride status. And then here we've got an image path, which refers to a path in the UI subproject, which we'll look at in a moment. Restart the application. And in a browser, hit refresh and verify that you also have the ride status and image path now. If you do, you're good to continue. If you don't, you can always start a discussion and ask for help on this lesson. Now I'd like you to download the UI.zip file attached to this lesson. You can stop the application, and then you can copy that zip file into the root project theme park manager. Unzip the file, which in Linux you can do with the unzip command. Delete the original zip file, which in Linux you can do with rm. Now if we look at the contents of this directory, we should have a new UI directory. Back in the IDE, open up settings.gradle and let's add UI as a new subproject for this build. Load Gradle changes. IntelliJ IDEA has picked up this new subproject. Let's have a look inside. And we've got a source main resources containing a static directory which has HTML, CSS and images. If you look in the build.gradle, you'll see this project applies the Java library plugin. What happens here is that source main resources gets packaged up and will be available for any other projects that consume this subproject, which is actually what we're going to do now. We're going to set API to depend on UI so that all of these UI assets will get served up by the Spring Boot application. So open up build.gradle for API. We can just copy this line and change service to UI. That's all the code changes we need to do. Let's restart the application. This time, if you're using an IDE with Gradle integration, let's go ahead and run it from the IDE. So in IntelliJ IDEA, I open up the Gradle panel. You'll notice we have listed the three subprojects. I go into API, I go to Tasks, Application, and then Boot Run. Okay, that started the Spring Boot application again. This time, go to just localhost 8080, no path required. And there's our theme park manager. And what we're seeing here is the HTML provided by that UI subproject, which got incorporated into the API subproject. So go ahead and hit the Get Rides button. And that's gone ahead and hit the API and returned the ride name, description, status, and we've even got an image link. So just for fun, let's take a look at these images. First off is the roller coaster. This is definitely a software developer on the front here. Then log flume. And this is how I would look if I was ever to ride on a log flume. And then teacups. This is definitely more my style. So well done. If you can see all this, you've successfully created a multi-project build with an API, service, and UI subproject. The only thing left to do now is to commit this project. So run git init. If you're using IntelliJ IDEA, add the .idea directory to the .gitignore file. Run git add git status, take a look through, and if you're happy, then run git commit -m initial commit of theme park manager. That's great, good work, and I'll see you in the next lesson. An important aspect of most Gradle projects, and often a source of confusion, is working with files in the build script. The main scenario where we need to specify files is configuring tasks like copy and zip, which you used in Chapter 1. By the end of this lesson, you'll understand how to configure tasks with single and multiple files and directories, as well as how to safely reference files in your Gradle project using relative paths, whether you're working in a single or multi-project build. Before getting into the Gradle implementation, let's take a step back and think about the ways in which we might need to reference files and directories in a build. The first one is simple. It's a reference to a single file or directory. For example, where you want to copy some files and need to specify a directory into which to copy them. This is exactly what you did in the practical lesson in Chapter 1. Another use case is to copy multiple files from one directory to another, preserving the directory structure of the source directory. For example, this happens when Java resources are copied from source/main/resources into build/resources. A slightly different use case is when you want to copy multiple files but don't want to preserve the directory structure of the source directory. With the second 2 points, we may also need to include and exclude certain files. For example, match any text files in a specific directory. Let's see how to achieve each requirement with the Generate Descriptions copy task from Chapter 1. As it stands, it copies files from the Descriptions directory into a subdirectory of the build directory. I've removed the token substitution as it's not relevant for this lesson. Say we just want to copy a single file, descriptions/rollercoaster.txt. We can just pass a string with a relative path to that file. That works absolutely fine. Another option is to call the project.file method, passing in the file name, which produces the same result. Now the file method actually returns an object of type file. So how is it that we can pass these different types to the same from method? If we look at the method signature, it says it takes the object type, which means it can take any type. It's very flexible, and there are in fact 13 different ways you can pass files and directories to it. Don't worry though, as we're going to cover only the most important in this lesson. With the copy task, you can also set into, which must be a single directory. Once again, there are many ways to specify this directory, 9 in fact. It's currently configured as a string representing a directory, but we can use the file method here too. Another way to refer to a directory within the build directory is to use the project.layout object, which provides helpful references to other directories. For example, we can write layout.buildDirectory.dir, passing the name of the directory we want to copy into. This syntax has the advantage that it's more programmatic than the string substitution approach. Now let's look at copying multiple files. Let's create an additional directory structure sub under descriptions with another RIDE file dodgems.txt. This way we can see how directory structures do or don't get preserved. The simplest approach is to specify the directory as a string like we had before. This results in all the files and the directory structure getting copied into the build directory. Copying the directory structure like this is the default behavior of the copy task when you specify a directory. Another way to specify the directory is to use the file method, giving the same result. Or there's the more explicit layout.projectdirectory.dir method, taking the directory name. You can also call the file tree method, which creates an object of type file tree. A Gradle file tree represents a collection of files with a common parent directory where the directory structure is maintained. One nice thing you can do with a file tree is pass its own include pattern. We can remove some duplication by passing the project directory to the file tree method and including only files under descriptions. The value passed to into can then be simplified, so we only refer to descriptions once. And this produces the same result. Of course, you could do the same thing by calling the include method on the copy task rather than the file tree. But the file tree does offer more flexibility, as you could copy from multiple file trees, each with their own specific include or exclude rules. So when we use any of these mechanisms, the files get copied across with the directory structure. The last scenario is when you want to copy multiple files without the directory structure. To do this, we need to use a different type called a file collection. A file collection is like a file tree, except it doesn't maintain the original directory structure. Going back to our file tree example, we can actually generate a file collection from a file tree by adding .files on the end. We also have to specify the descriptions directory again when we call into. Now when we run the task, the directory structure has been removed and all the files are sitting at the top level. Another option is to call project.files and pass the relative path of each file. This produces the same result. Let's try taking these ideas and applying them to the zip task. Here's the task as we left it after making changes in Chapter 3 to link it to the output of the Generate Descriptions task. Looking at the documentation again for the 13 different ways to pass files to from, we see that passing a task is indeed one of these options. Here it's the best option since we want zip descriptions to dynamically refer to the copied files, without having to specify each file individually. Let's leave from as is then, but look at the destination directory. According to the docs of the zip task, this property requires an object of type directory property, representing the directory where the zip should be created. Right now we're using project.buildDIR, which returns a file object. In the background, Gradle is automatically converting between types where necessary, in this case from file to directory property. This automatic conversion can be a bit confusing, but it does make our build scripts less verbose. But we could equally use layout.buildDirectory, which does return an object of type directory property. If we want to create the zip file in a different directory, we can call .dir on layout.buildDirectory. The zip task will then automatically create the directory for us and place the zip there. One thing we can't do with the destination directory is specify a string. If you try that, you'll get this error. So if you want to specify a full relative path as a string, in this scenario you could use the file method. When you use these Gradle file APIs, Gradle handles making sure they work relative to the project you're working in. That means if you're in the build script of a multi-project build, any files you reference are relative to that subproject's directory. For example, here we are in the UI subproject of Theme Park Manager, and we'll add this copy task that configures the from as a relative file path to index.html. When we run that task, Gradle successfully copies the file using the subproject directory as the root of the relative path. This means that you should always use the file APIs and never create a file object directly using, for example, new file. If you were to do that, the file would be created relative to the current working directory, which Gradle makes no guarantees about. The key takeaways from this lesson are that single or multiple files and directories can be configured with tasks like copy and zip. The source files and directories of these tasks can be configured in many ways. You've seen a simple string representing a file, getting a file object using project.file, getting a file object using the layout object, such as layout.buildDirectory.file, using a file tree, which preserves any subdirectory structure when used for copying, or using a file collection, which doesn't preserve subdirectory structure when copying. And remember to always use the Gradle file APIs and never create a new file directly. See you in the next lesson. As your application grows, your Gradle build logic will likely grow to meet an increasing list of requirements. This may include custom logic, tasks, and plugins. As you incorporate these features in your Gradle project, your build scripts will inevitably increase in size. You'll start to have duplication between those build scripts, and things may start to become quite unmaintainable. Fortunately, Gradle offers several mechanisms to combat these problems, with an aim to keep your individual build scripts as concise as possible. buildSrc is one such mechanism, which lets you pull logic out of your build script into a directory called buildSrc at the top level of your project. The extracted build code can then be reused in any project of your build, which both cleans up your build scripts and promotes reuse. Build logic written in buildSrc can be written in any JVM language, Groovy, Kotlin, Java, or Scala. This can be helpful, for example, if whoever is maintaining the build is more familiar with a specific language. Be careful not to introduce too many languages in your project though, as it may cause more problems than it solves. In terms of what you put in buildSrc, well, it can be any code logic you want to call from build scripts, your own custom task classes, and plugins. In the rest of this lesson, we'll explore one use of buildSrc, which is to define convention plugins. Convention plugins are a way of applying the same build logic to multiple subprojects. Within a growing multi-project Gradle build, you might notice subprojects falling into distinct categories. For example, if several subprojects applied the Java plugin and specified certain repositories, you could extract that logic out into a Java-specific convention plugin. Let's move back to the Theme Park Manager multi-project build to explore how convention plugins work. I've made a small change by adding a test for the Theme Park Ride entity class. It just makes sure we can create a theme park ride and all the fields have the expected values. To achieve this, I've also had to add the JUnit Jupyter dependencies to the build script and configure the test task to use the JUnit platform. If we compare the build scripts for API on the left and service on the right, we can see that there's some duplication in the repositories, dependencies, and test task configuration. Let's fix that using a convention plugin. First off, we create the buildSrc directory at the top level. Inside, we add a build.gradle file with a single plugin. This plugin means that we'll be writing our convention plugin with the Groovy DSL, which in this case makes sense as that's the same language as our actual build scripts. I need to click Reload all Gradle projects for IntelliJ IDEA to recognize buildSrc. Now we'll create a directory source main Groovy, then a file called com.gradlehero.themepark-conventions.gradle. The part of this file named before .gradle is the name with which we'll refer to our convention plugin from within our subproject's build scripts. Within the plugin's .gradle file, we can write any build logic as though we were in a normal build script. When the plugin gets applied to a project, the logic contained in this file will also be applied. I'll copy the repositories, dependencies, and test task configuration into this file, and I'll remove it from the other two build scripts. We'll also apply the Java plugin, which I'll put at the top. And that means we can remove the Java plugin from the API subproject. So any subprojects that apply this convention plugin will get the Java plugin, the repositories, the dependencies, and the test configuration. Nice. Now all that's left to do is apply the convention plugin to the API and service subprojects using an ID which matches the file name of the convention plugin without the .gradle. And we'll do the same for the service subproject. Let's run Gradle build to see everything's working properly. Looks good. If we compare the build.gradle of the service subproject before and after our change, we can see that the convention plugin has reduced the length significantly. Before we wrap up this lesson, we'll take a quick look at a slightly more advanced example of convention plugins, this time provided by Gradle init. In the new directory, we'll run Gradle init, choosing Application, Java, and when asked split functionality across multiple subprojects, this time we'll choose yes. This creates a project with 3 subprojects. There's app, which is the main application, and this depends on utilities, which in turn depends on list. We won't get into the implementation details of this project, but what's interesting is how the convention plugins are used. The app subproject is an application and needs the application plugin applied, whereas list and utilities are libraries and need the Java library plugin to be applied. In the build source directory, we have 3 convention plugins. There's Java Application, Java Library, and Java Common. With convention plugins, you can have one plugin apply another for yet another level of reusability. In this case, the Java Common convention plugin is used by Java Application and Java Library. Let's take a look at the Java Application convention plugin. So it applies the Java Common and also the core application plugin. Likewise, the Java Library convention plugin is the same, but the Java Library plugin is applied. Looking inside the build scripts of the list and utilities subprojects, we can see the Java Library convention plugin is applied, whereas in the app subproject, it's the Java Application convention plugin. So this is a nice way to categorize your subprojects and apply common logic based on that category. The key takeaways from this lesson are that as projects grow, the complexity of your build grows too, which can be mitigated by extracting logic into the build source directory. Build logic within build source can be reused within any project of your build. Build logic can be extracted into a convention plugin and then applied to specific subprojects. And you can use multiple convention plugins to apply different build logic to different categories of subproject. See you in the next lesson. All of the tasks we've worked with so far in this course have been either based on pre-packaged task classes like copy or ad hoc tasks defined in the build script with a do first or do last configuration to perform some action. But what if we wanted to create our own task class to be reused within our project? Well, in the last lesson, we saw how within build source you can create convention plugins that let you apply common build logic to multiple projects. In this lesson, you'll see how to create your own task class to represent whatever it is you need to get done in your build, and how to extract it out to build source to be shared across your project. Imagine within the UI subproject of Theme Park Manager, we have a requirement to add a new task to the project. When given 2 files, it should print out which is the larger. We'll use this requirement to explore creating task classes, starting off with a basic implementation with hard-coded file names. Then we'll update the task to allow the file names to be configurable. Here's the Theme Park Manager project as we left it in the last lesson, and I'll open up the build script for the UI subproject. To define a custom task class in Gradle, we create an abstract class which extends default task. That's all that's needed, and we can now define an instance of this task using tasks.register called FileDiff. When we run the FileDiff task, unsurprisingly, nothing interesting happens because our task class doesn't do anything yet. Let's fix that. Within the class, we can create as many task actions as we like, simply by defining a method and annotating it with @taskAction. We now have a diff method, and to save time, I'll paste in the method body. This code references 2 files and compares their size. Whether they're the same size, the first is larger than the second, or the second larger than the first, an appropriate message is printed out. Run the FileDiff task again, and it's telling us that logflume.jpg is larger than rollercoaster.jpg. Okay, cool. We can take this one step further and make the task customizable by allowing anyone that defines an instance of this task to dynamically set the files. We do that within the task class by defining an abstract method which returns a Gradle property object of a particular type, in this case file. These Gradle property objects are used for configuring tasks. They're special since the property value isn't read until it's actually required, or in other words, it's lazily evaluated. Their value can be set when you define a task, and you can get their value within the task action when it's needed. We should also annotate the method with @inputFile, which declares this property to Gradle as an input to the task. This allows Gradle, where appropriate, to mark tasks as up to date if it knows that none of the task inputs or outputs have changed. You can refer to the docs linked in the notes to learn about other types you can use for inputs. For example, if you wanted to create a task with a simple string property, annotate it with @input instead. Repeat the same process for the second file. Now we can remove the hard-coded file1 and file2 variables. Wherever we reference file1 and file2, we must now call .get to get the actual file from the property object. Where we've defined our task instance is where we now need to configure file1 and file2, like this. This produces the same output when we run the task, but now we can more easily configure the task without having to change the code of the actual task class. The last stage is to extract this task into buildSrc. Within source main Groovy, create a package com.gradlehero.themepark, and within there create a Groovy class FileDiffTask. Now let's cut the code from the build script into the class. Now this task is available to any of the build scripts of any project within this multi-project build. Back in the build script of the UI subproject, we just need to import the task. We can now execute the task in the same way, but now the task class has been neatly extracted into buildSrc, making our build script a lot cleaner. The key takeaways from this lesson are that you can define a task class directly in the build script. The class must extend default task to work properly. Any work to be done is defined in an action method annotated with @taskAction. These methods are executed when the task gets executed. You can extract configuration into property methods, and these methods should return a Gradle property object of a specific type and have an appropriate @input annotation. And finally, you can move a task class from the build script to the buildSrc directory so it can be reused within any project in your build. See you in the next lesson. This is the first of 3 lessons to show you step by step how to create a custom plugin, how to share it, and how to test it. Whereas tasks accomplish a single discrete action in a build, plugins work one level higher and automatically define tasks and other configuration in a project. An obvious example of this is the Java plugin, which defines tasks such as those to compile and test our code, but it does even more, such as registering Java-specific dependency configurations for us to declare dependencies against. As your build logic grows, there's no reason you can't make use of the same mechanism by extracting it into plugins to be applied in whatever projects you like. In this lesson, we'll take the FileDiff task from the previous lesson and package it up inside a plugin, so it's automatically available whenever the plugin is applied. We'll start with the simplest option to create the plugin in the build script itself. In later lessons, we'll extend the example by pulling the plugin out of the build script into a separate project, which is a lot more useful in real-life scenarios. Here's the Theme Park Manager project as we left it in the last lesson, with the FileDiff task extracted into the buildSrc directory. A plugin is simply a class which implements the plugin interface. The interface contains an apply method in which we'll add some project customization, which for us will be to define a FileDiff task. So let's create a FileDiff plugin class implementing plugin. We can use autocomplete to add the apply method. Now we just need to fill it in. Since we can reuse the task definition from this build script, let's cut and paste it and make some minor changes by using the project parameter passed into the apply method. Note at this point the build script is valid, but we no longer have the file diff task available as the plugin hasn't been applied yet. To do that, we use the legacy apply plugin syntax, referencing the class name. Now we can run the file diff task and it produces the same output as we saw in the previous lesson. Awesome! One more thing to do is to make the plugin configurable. That means rather than using hard-coded file names, it's up to whoever applies the plugin to pass them in. We'll use the same mechanism you've seen many times before, where a plugin exposes a custom configuration you can set in the build script. For example, when the application plugin lets us set a main class by calling application and then main class. This plugin configuration is referred to as an extension in Gradle because it's a way of extending the Gradle DSL beyond what it can do by default. So how can we create an extension for our file diff plugin? Well, we have to define another abstract class with abstract getter methods for each property we want to be able to set on the extension. So that's just a class definition, but to be able to configure the file diff plugin in our build script, we create an instance of the extension in the plugin's apply method. The project.extensions.create method takes a name and type. The name is how we'll refer to the extension in the build script. By creating an extension called file diff, we can now add this plugin configuration to the build script. Finally, back in the plugin's apply method, we can replace the hard-coded values with the configured files by referencing the extension. The file diff task still works, now using a plugin configured in the build script. The benefit of all this will become more apparent once the plugin is extracted into its own project, which we'll do in the next lesson. But you've just seen the main principles of creating custom plugins with this simple example. Here are the key takeaways from this lesson. Writing custom plugins allows us to create reusable task definitions and configuration logic to apply to one or more projects. A plugin is represented by a class that implements the plugin interface and can be defined in the build script. Inline plugins are applied using the legacy plugin syntax. Extensions allow plugins to be configured using a plugin-specific DSL. And to use an extension, you create an extension class and a named extension instance. See you in the next lesson. In the last lesson, we created a plugin which adds a file diff task to one specific project. Now it's time to extract the plugin into its own project, letting us develop and publish it independently. Once the plugin is published to a remote repository, anyone who has access to that repository can then apply the plugin in whatever project they like. Right now, the plugin consists of 3 classes: the plugin class itself, the extension class, and the task class. All 3 of these are required for the plugin to work, so will be extracted out into the new project. Plugins can be written in any JVM language, including Java, Groovy, or Kotlin. Our plugin code right now is Groovy, which we'll also use in the standalone project. So let's create a new directory for the plugin project, then run Gradle init to initialize a basic Gradle project using the Groovy DSL. In the build script, we'll apply the Groovy Gradle plugin, the same plugin we used in the lesson on convention plugins. It automatically applies the Groovy plugin and sets the project up so it can build and publish plugins. For example, one thing it does is add a special plugin descriptor in the generated jar file, which you'll see in a moment. And by the way, if you want to write your plugin in Java, use the Java Gradle plugin instead. We configure the Groovy Gradle plugin by calling Gradle plugins, then our plugin name, which is file diff. In here, we specify a plugin ID, which is the ID by which someone will apply the plugin, so including a unique namespace is a good idea. Also specify an implementation class, which is the class that implements the plugin interface we wrote in the last lesson, which will move into this project next. So we'll create a package structure following the Groovy project conventions, create a file diff plugin Groovy class, Then paste in the plugin class from the previous lesson. Let's do the same for the FileDiff plugin extension and FileDiff task classes. At this point, we can build our plugin with the build task, and the jar file is generated. Taking a look inside, we have the compiled class files in com.Gradle Hero, and within metaint we have a Gradle plugins directory added by the Groovy Gradle plugin. This contains a special file known as the plugin descriptor. It maps the plugin name, which is in the file name, to the implementation class contained within the file. Projects consuming this plugin will use this information to locate the plugin class within the jar file. Now it's time to publish the plugin, which we'll do with the Maven publish plugin you learnt about in Chapter 4. Let's provide the required group and version to be used in the generated pom.xml file. Then publish to Maven local to start with. Back in the Theme Park Manager project, we can delete the 3 classes we just moved into the standalone plugin project. Remove the previous Apply Plugin line because we're going to apply our standalone plugin using the plugin's DSL syntax. Use the ID and version we set up. Load Gradle changes and we get an error saying it couldn't find the FileDiff plugin in the Gradle Central plugin repository. Well, that makes sense because we published it locally, so we need to make a tweak to get Gradle to also look in the Maven local repository for the plugin. To do that, within settings.gradle, we can configure repositories specifically for finding plugins. Call plugin management, repositories, then specify the repositories we want Gradle to look in. We need to include the Gradle plugin portal as we're using plugins from here within this project. But let's also include Maven local where our FileDiff plugin is published. Now when we load Gradle changes again, everything's okay. So let's try the FileDiff task, which successfully gives the same result. But this time it's using a standalone plugin published to my local Maven repository. Of course, you'll likely want to publish any plugin you write to a remote repository, which you can do by configuring the Maven Publish plugin as shown in Chapter 4. For example, here I've configured the plugin project to publish to my AWS Maven repository. There's no reason to set up publications as that's configured automatically by the Groovy Gradle plugin. And I can publish the plugin with Gradle wpublish. In the consuming projects settings.gradle, I need to update the plugin management repositories by replacing Maven local with details of my remote repository. And the FileDiff task is still working as expected. Here are the key takeaways from this lesson. The plugin class, plugin extension class, and task classes can be extracted into a standalone plugin project. Apply Groovy Gradle plugin or Java Gradle plugin to ensure the project is set up correctly for building and publishing plugins. Configure the plugin's ID and implementation class to be used in the plugin descriptor within the generated plugin jar file. Publish the plugin locally or remotely using the Maven Publish plugin, and consume your custom plugin by configuring your repositories in plugin management in settings.gradle. See you in the next lesson. To develop robust plugins that we're confident still work as expected when changes are made, automated tests are a very good idea. In this lesson, we'll focus on writing a functional test for the FileDiff plugin. The functional test will run the plugin in a real Gradle build as any consumer would, and ensure the diff functionality works properly. This test will be added into the plugin project we created in the last lesson. To write the functional test, we're going to use a Groovy testing framework called Spock. This framework allows you to write expressive tests using the behavioral-driven development given-when-then style. To interact with Gradle from our functional test, we'll use a framework called Gradle Test Kit. This framework allows Gradle builds to be executed programmatically and the build output and task status to be queried. That's exactly what we need for writing functional tests. Gradle Test Kit is applied automatically by the Groovy Gradle plugin and Java Gradle plugin plugins, which we used in the previous lesson within our plugin project. With a high-level understanding of how we can test a Gradle plugin, can you guess how specifically we should functionally test the file diff plugin? Well, I think at a minimum we need these three separate tests. One which creates two files of the same size within a Gradle project, runs the file diff task, then checks that the plugin prints the expected output. And two more similar tests, one where the first file is larger than the second, and one where the second file is larger than the first. With these three tests, we can be sure that we've exercised all possible logic paths of the plugin. So let's get started. In the file diff plugin project, we'll first apply the Spock testing framework to the test implementation dependency configuration. We'll also need to configure repositories to include Maven Central. This version of Spock actually uses a JUnit 5 runner, so from Gradle's perspective, it will be just like running a JUnit 5 test. So we need to configure tests in this project to use JUnit platform. Now create a new directory structure, source test Groovy, a com.Gradle Hero package structure, and within there a file diff plugin functional test Groovy class. Before continuing, load Gradle changes so I have the Spock dependency available to this test class. The class needs to extend specification to make it into a Spock test. Let's start off with a test to ensure the diff works for files of the same length. Spock tests consist of a human-readable name, then specific given when then sections. We just need to fill them in. Our given will consist of creating a Gradle project directory. In there, we need the two files to be compared and the build.Gradle, set up to apply and configure our plugin under test. First, we'll create a temporary directory for our Gradle project to be used only for a single test execution. That's handled by the Spock at temp.dir annotation. All our project files will go in this directory. Now create the two files to be compared, test file 1 and test file 2. We'll leave them empty, which means they both have the same size. Create a file build.Gradle. We can use this special Groovy syntax to append to the file and use triple quotes to specify a multi-line string. In our case, we want to apply our plugin, then configure it based on the two files we just created. Moving on to the when section, this is where we make use of the Gradle test kit I mentioned earlier. It exposes a Gradle runner class, which we use to actually execute our build. Pass it the project directory, an argument of the file diff task name, and call with_plugin class path, which sets up the class path based on the Gradle plugin conventions. And we need to also import the class. Finally, the then section will query the build output to verify it contains our expected string. We do that using the result variable and check it contains the string output by the plugin. We can also query the outcome of the file diff task to ensure it succeeded, using this success class that we can import from the Gradle test kit. That's it for our first test. We can run it in IntelliJ IDEA with Ctrl+Shift+F10, and it's passing fine. Let's copy and paste the test and make a new test for when the first file is larger than the second. We'll set up the precondition by adding some text to test file 1, then change the expected outcome. And this test passes fine too. But can you spot any duplication? The code to create the build file, create the two comparison files, and apply and configure the plugin is the same between the two tests. It can be extracted into a setup method to be executed before each test. And let's refactor the second test to make use of the new setup method. And both tests are still passing. Finally, let's add a third test for when the second file is larger than the first, again by copy and pasting. Just change the file which gets text written to it and change the expected output. Now all three tests are passing. Great! You've just seen how to easily add functional tests to a custom Gradle plugin. Of course, these tests will be automatically run when you run the build task. Perfect for verifying everything works before pushing plugin code changes or within your CI environment. To take a look at the test code, follow the link to the GitHub repository in the notes below. Here are the key takeaways from this lesson. Using the Spock framework allows us to write expressive tests in Groovy. Gradle Test Kit is a framework for functionally testing plugins and comes automatically with the Groovy Gradle plugin and Java Gradle plugin plugins. In the Given section of the functional test, create the relevant build.gradle file for your plugin. In the When section, use the Gradle runner provided by the Gradle Test Kit to execute your build. And in the Then section, verify the expected build output or task status. See you in the next lesson. Welcome to this first bonus chapter where you're going to learn the techniques to solve any issues when running your Gradle build. The only thing that's certain is that things won't always go to plan, so the following series of lessons will help you get the necessary insights into what's happening during both the configuration and execution phases of your build. By the end of this chapter, you'll know how to generate detailed log output from the command line so you can see what's going on when a problem occurs. This includes adding your own logging to any of your custom code. Investigate the dependency resolution process to understand why particular dependencies are on the class path, and view the task graph for your build to see how all the tasks relate to each other and understand why tasks run when they do. As a reminder, we already covered debugging the build script in the lesson IntelliJ IDEA Gradle integration and debugging Java applications in the lesson running Java applications. We won't be covering debugging again in this chapter, but feel free to go back for a reminder. See you in the next lesson. So far, we haven't talked about logging in any detail, but it's important to understand so you can both set the appropriate logging level when you're running a build and also add helpful log statements in any custom code you're writing. As you might expect from a framework built for the JVM, the Gradle logging options are extensive, with the ability to output log messages at the fairly standard levels of error, warn, info, and debug. Gradle adds 2 more log levels of quiet and lifecycle, with lifecycle being the default. You can specify the log level on the command line when running a task using the displayed command line option. The levels give you progressively more detailed log output from error to debug. Let's try an example. Elsewhere in this course, we've used the println method to output strings during the build process. This is absolutely fine, and in fact, using println logs at the default lifecycle log level. So in this brand new empty Gradle project, let's add a task with a doLast action, which prints a moderately amusing string using println. When we run this task with no special command line options, it prints the string. Likewise, if we run the task using the logging levels quiet, warn, info, and debug, the string is still printed. At the info and debug levels, you'll see we have a lot of additional information about what's going on in this build, which we'll look into later. If you want your log output to appear at a different log level, for example info, you can use the logger object which you get from the Gradle project or task object. Logger is of type org.slf4j.logger, which is part of the popular Java logging framework SLF4j, which you may have heard of. So we just replace println with logger.info and pass the string. Now, when we run the task at the lifecycle log level, we don't see our log output. But if we run at the info level, then here's our output. The reason for this is that info is a more detailed log level than lifecycle. Since our log statement is at the info level, it will appear when we set the level to info or debug. As Gradle uses SLF for J, we can easily insert variables into our log statement using the curly bracket syntax, which denotes a placeholder. We then pass any values as arguments to the logging method, in this case the info method. So with this information about logging, where might you use it to generate your own log statements? Well, this very much depends on your specific requirements, and it's perfectly valid not to add any extra logging at all in your build. But if you find yourself frequently troubleshooting and having to add log statements temporarily to see what's going on, this could be a good candidate for a permanent log statement. Be careful about choosing the log level though, because what might be important at the time might not be important to a developer who's running the build many times each day. Custom tasks might be another candidate for extra logging. If you have some intricate logic, then you could log to say what's going on. If you log at the info or debug levels, you have the option to easily switch on the logging when you need it. Now let's run through 4 example scenarios where logging can help us out when we get into trouble. For these examples, we're back in the Theme Park Manager project as we left it at the end of Chapter 5. If you ever have a syntax error in your build script which surfaces when running a task like build, Gradle will helpfully print out the problematic file path and line number. In this case, it's easy to see that I have a typo in the word implementation. If the error is caused outside the build script, the log output is slightly less helpful. Here's an example where the error is in the code of a custom task which is being executed, and there's no detail about the specific line number. By default, the stack trace is hidden, but you can see it by adding the -- stack trace command line option. When we do that, we can see the exact line number where the error was thrown and navigate directly there to resolve the issue. Next, here's an example of how you might want to use the detailed logging that Gradle outputs at the debug level. If you run the compile Java task with -- debug, you'll see a full list of compiler arguments. This could be helpful if you need to know exactly how your code is being compiled. Finally, let's run compile Java at the info level and pass the -- refresh - dependencies option, which forces Gradle to go back to the repository to ensure it has the latest version. In the output, we can actually see the individual URL that Gradle is checking for each dependency. This might be helpful to understand issues like dependencies that Gradle can't find in your repositories, as it will also tell you when a dependency is missing. It's impossible to predict in advance of a real issue exactly what logging output you'll need, but now you've got a good place to start. See you in the next lesson. In Chapter 4, we learnt about the different tasks in a Java project and the dependencies between them, using a visual representation called the task graph. This tree structure just shows us the tasks that will take part in the build. The task passed on the command line is the root of the tree, and the lines between other tasks represent task dependencies. This format can give you insight into tasks in your project on top of what you might get by just running Gradle W tasks. Specifically, it can help you to understand why a particular task is running. For example, if you're sure that a task shouldn't be running, by analysing the task graph, you can see which task depends on it. Or to figure out a more efficient way of executing a build by choosing a more specific task. For example, running assemble rather than build in a Java project saves time by avoiding test execution. Unfortunately, printing the task graph isn't something that's built into Gradle. It's easy enough though to use a plugin to do this, which is what you'll learn in the rest of this lesson. The best plugin to print the task graph is the Task Info plugin, and the link to the plugin page is in the notes. We'll apply the plugin to the Theme Park Ride Status project, which is a Java project. We can now run whatever task we want to see the task graph for, along with the TI tree task. So in our case, we'll run Gradle W build TI tree to get the task graph for the build task. When we run this, the plugin cancels the build task, so a project doesn't actually get built, and instead prints the task graph. Here, the root of the tree is the build task, which was passed on the command line. The lines to assemble and check represent task dependencies, and so on, all the way up the tree. So run this on any task in any project to get a better understanding of the task dependencies. While we're here, another option which you have, which might give you what you need to know without applying an additional plugin, is to use the command line --dry-run option. This disables all the tasks, which is why it says skipped, but helpfully prints out the tasks which would have been executed. In this case, for the build task, it shows the same tasks from the task graph output. Of course, it doesn't show the dependencies between the different tasks, but it might be useful nonetheless. See you in the next lesson. In Chapter 3, you learn how to specify dependencies in the build script, which Gradle fetches from the configured repositories during build execution. Dependencies are grouped in dependency configurations. For example, with implementation, dependencies end up on the compile and runtime class paths. However, what dependencies are specified in your build script and what dependencies are actually used during your build are not necessarily the same. Here are some reasons why. Transitive dependencies are also taken into consideration. If you declare Spring Boot Starter Web as an implementation dependency, then the compile and runtime class paths will contain many transitive dependencies brought in by that single dependency. If any of the resolved dependencies have the same group and name but different versions, this is considered a conflict and Gradle will pick the one with the highest version. And the build script may define dependencies which Gradle can't resolve from any of the specified repositories. For example, if you want to use Spring Boot but only have your private Maven repository listed, then unless your private repository contains Spring Boot, Gradle won't be able to find it. Given all this, you'll sometimes come across issues which require you to be able to say for sure which dependencies Gradle is using. Fortunately for that, you have the Dependencies task available in any Gradle project, which prints out all the dependencies in a tree structure. To see it in action, we'll use this simple sample project which has two implementation dependencies, Guava and FindBugs JSR 305. It doesn't matter what these libraries actually do, all we're interested in is to see how the dependencies are resolved. On the command line, run Gradle W dependencies, which prints the dependency tree for all dependency configurations. There are quite a few, so I recommend limiting to a specific dependency configuration you're interested in. In our case, that's compile class path, so we just need to pass -- configuration with that dependency configuration name. So here we have all the dependencies which will be added to the class path during compilation of any code in this project. The Guava library brings in 6 transitive dependencies, whereas FindBugs JSR 305 brings none. Next to each dependency group and name is the version. Note how next to FindBugs JSR 305 it has 2 versions separated by an arrow. This indicates there was a version conflict and Gradle has picked a different version. In the transitive dependencies of Guava, we see a dependency with the same group and name, but with a more recent version. That's why version 3.0.2 was chosen by Gradle. That was a simple use case. For a more realistic scenario, let's jump back into the Theme Park Manager project, which, if you remember, is a multi-project build for a Spring Boot application. When we run Gradle W dependencies on the root project level, nothing gets printed as this task only works on one specific project at a time. Let's try again against the API subproject by prefixing the task name with API:. We see a lot of output here. So let's be more specific and ask for the compile class path dependency tree. Okay, that's a bit more manageable. We see dependencies on the service and UI subprojects and also on Spring Boot Starter Web. Those are actually the only dependencies specified in the build script of API, and all the rest are transitive dependencies of Spring Boot Starter Web. If you look carefully, you'll see some dependencies are starred, for example the ones for Spring Core. This means that Gradle decided to leave out this portion of the tree as it was shown already. So for Spring Core, this portion of the tree was shown here, so there's no point showing it again and again later on. The last thing to show you with the Dependencies task is what happens when the dependency can't be resolved. We'll add a bogus dependency to the build script. And now the dependency tree shows that dependency as failed. One thing that the dependency tree doesn't show you is why a particular version has been chosen during a version conflict. For example, in this tree we can see SLF4J API version 1.7.31 was replaced with 1.7.32, but without us manually reading through the rest of this tree, it's not easy to see why. The Dependency Insight task is the solution to this, as it shows you the tree from the perspective of a specific dependency. In fact, it outputs the tree in the opposite direction of the one in the Dependencies task. We must pass the -- dependency option with the dependency we want to see, and a mandatory -- configuration option. Now we can see that the SLF4J API was brought in transitively by 3 separate dependencies, but it was JUL to SLF4J which brought in the highest version, which was ultimately selected by Gradle. The key takeaways from this lesson are that the dependencies defined in your build script are not necessarily the same as those that get resolved. Use the Dependencies task, along with an optional dependency configuration, to see an overview of all the dependencies in one place. And use the Dependency Insight task with a mandatory dependency name and configuration to see why a specific dependency has been added. See you in the next lesson. Welcome to this next bonus chapter where you'll learn how to use Gradle to overcome some common challenges you might encounter in real-world scenarios. At this point, you already have deep knowledge on how to use Gradle, but in the lessons that follow, you'll discover some powerful techniques and plugins to take your project to the next level. See you in the next lesson. A popular metric that teams often use to measure the quality of their tests is code coverage. It represents the percentage of lines of production code that are executed by tests. If a code base has high code coverage, in theory that means that it's well tested. There are of course other factors to bear in mind, like how maintainable the tests are, but code coverage is a good place to start. So how do we calculate the code coverage metric? A popular tool in the Java space is called Jacoco. The way it works is that when you run your tests, a Jacoco agent attaches itself to the JVM. The agent tracks which lines of production code are executed as your tests run. Jacoco can then generate a detailed report including the code coverage metric. If that sounds complicated, don't worry, because fortunately Gradle wraps all of this functionality into a core plugin. And it's called, you guessed it, Jacoco. With the plugin with ID Jacoco applied, any task of type test will generate what's called execution data. It's the raw binary data generated by the Jacoco agent describing which lines of code have been executed. That file isn't readable by humans like you and I, but the Jacoco plugin also registers a Jacoco test report task, which by default generates an HTML report. This task can be configured to generate XML and CSV reports too. One last cool thing that this plugin does is register a Jacoco test coverage verification task, which validates the code coverage metric is above a predefined threshold. That means you can fail your build if someone makes changes that don't meet your standards. To demonstrate all this, we'll use the code coverage project, which you'll find in the Gradle Hero GitHub repository. The project already has production and test code. We'll configure it first to generate the binary test execution data, then to generate an HTML code coverage report. We'll also set up a rule to ensure our build fails if the code coverage goes below 80%. The code coverage project contains Java code to simulate an ice cream stand in the Grelephant's Wonderworld theme park. The main ice cream stand class at the start of the day contains 100 ice creams. Customers can buy a standard vanilla ice cream, a vanilla ice cream with a flake, or the ultimate chocotastic chocolate ice cream with flake. Not recommended before going on the roller coaster. As ice creams are sold, the ice cream count is decremented, and we also call validate stock, which throws an exception in the nightmare scenario that we run out of ice creams. Of course, as good developers, we have unit tests to cover this class. A test for the standard vanilla ice cream, one for the ice cream with flake, and one where we buy all the ice creams. Here's our simple build script, which configures unit tests to use JUnit Jupyter using the JVM Test Suite plugin discussed in the Adding Integration Tests to a Project lesson from Chapter 4. We can run Gradle W test, and the test report shows the 3 tests passing OK. So to generate code coverage data, apply the Jacoco plugin with ID Jacoco. As soon as we do that, when we run the test task again, you'll see a new buildSrc directory containing the test execution data. Like I said, this data isn't human readable, but instead we can run the Jacoco test report task. This uses the test execution data to create an HTML report in Build Reports Jacoco. Opening it in a browser, we see a detailed report for this project's code coverage. The most interesting data is the coverage column, which shows the percentage of lines of production code covered by tests. 72%, not too bad. Jacoco also gives you data on the percentage of branches in your code that are covered. For example, if-else statements. There's also the complexity column, which indicates the number of unit tests required to execute the code. We'll focus on the first metric for the rest of this lesson. Click the package name to see code coverage at the class level. We can even view a particular class and see which methods weren't covered by tests. Okay, so let's add a new test for the chocotastic ice cream. We'll run Jacoco test report again and view the report. It's still only showing 72%. Any ideas why? If we run again with -- console equals verbose, we see that the test task isn't running, so the test execution data isn't regenerated. Let's fix that by adding a task dependency from Jacoco test report to test. Run the task again, and our code coverage has jumped to 91%. Awesome. With such a good code coverage score, we don't want anyone coming along and messing it up. So let's add a rule requiring at least 80% code coverage. We do that by configuring the Jacoco test coverage verification task, configure violation rules, a rule, a limit, with a minimum of 0.8. When we configure these rules, we express percentages as a ratio from 0 to 1. Let's make this task depend on the test task, since it relies on the binary test.exec file. When we run the task, it passes. Let's remove the unit test we just added earlier to ensure we get a failure. In this case, the task fails, saying that our code coverage wasn't high enough. The final thing you might want to do is configure the check task to depend on Jacoco test coverage verification. Locate the task and add a depends on relationship. This way you can run check before pushing code or in your CI pipeline, and it will automatically validate the code coverage. Here are the key takeaways from this lesson. Use Jacoco to measure the percentage lines of production code covered by tests. Apply the Jacoco plugin to automatically generate test execution data in binary format. Run the Jacoco test report task to generate an HTML report from the test execution data. And configure the Jacoco test coverage verification task with rules to fail the build if code coverage doesn't meet your standards. See you in the next lesson. When working with a team of developers, it's important that everyone's on the same page when it comes to code style. At a basic level, that includes things like indentation and the never-ending debate on whether the left curly bracket should go on the next line or not. To enforce these rules, we can use Gradle's core Checkstyle plugin. It runs the Checkstyle tool against production and test code, using an XML configuration file which you set up with your choice of checks. There are hundreds of checks to choose from, which you can browse on the Checkstyle website, linked in the notes below. The Checkstyle plugin exposes Checkstyle main and Checkstyle test tasks, which are configured to run with the check task. If any of the checks you've configured fail, the Checkstyle task will fail too. To see how all this works, we'll use the code style project in the Gradle Hero GitHub repository, linked in the notes below. I've taken the opportunity to write some really bad code in this project, so let's configure some Checkstyle checks to fail our build. Here's the offending class, which has 3 problems, one of which is a matter of opinion, but 2 are undisputable. Can you spot any of them? If not, don't worry, because we'll run through them one by one, adding the corresponding Checkstyle checks as we go. But first off, let's apply the Checkstyle plugin. We'll also need to include the Maven central repository, since the plugin automatically adds some dependencies. Then add a configuration file, config/checkstyle/checkstyle.xml, which is the default location that the plugin looks in. Here we add this doc type element and a module element as expected by the Checkstyle tool. Within this checker module is where we'll shortly add a list of Checkstyle checks. With this in place, we can run the check task, which I'll run with the -- console equals verbose. We see that it's run the Checkstyle main and Checkstyle test tasks, and despite our bad code, they're passing right now as we haven't configured any checks. Okay, the first rule to add is unused imports. For checks to run against every Java source file, they need to go inside a tree walker module. Within that element, configure a module called unused imports. Now when we run the check task, it fails with Checkstyle violations. We get a link to a report which shows that our class has an unused import for Java lang string. Oops, let's fix that. Next up, we'll add the indentation check, which validates the code indentation. When we run check again, the report says that we have a right curly bracket with incorrect indentation. Oops again, so let's fix that. Finally, let's add the left curly check, which by default expects left curly brackets to be on the same line. Running check and viewing the report shows us we're currently failing this check. We could fix that, but instead let's explore how to customize a Checkstyle check. For left curly, we can set a property to insist that left curly brackets are on a new line, like in our class. With this in place, the check task is now passing because our code now complies with all configured checks. Here are the key takeaways from this lesson. Apply the Checkstyle plugin to validate your code against your choice of Checkstyle checks. Add a configuration file at config/checkstyle/checkstyle.xml and customize it using the Checkstyle documentation. Run the check task to run Checkstyle main and Checkstyle test, which will pass or fail your code based on your configuration file. See you in the next lesson. Now that you've seen how to enforce code style with Checkstyle, there's a similar tool that you should be aware of called PMD. Just like Checkstyle, it analyzes your code during the build process and passes or fails based on criteria that you define. So what's the difference between PMD and Checkstyle? Well, the focus of PMD is on code quality. It has many checks that analyze code beyond simply layout. For example, ensuring that you use logging frameworks instead of system.out.println statements. On the other hand, Checkstyle is mainly focused on code layout and style. For example, ensuring 4 spaces are used for each level of indentation. There is some crossover between the two tools. Both can detect unused imports, for example. Which tools you use will depend on your project's requirements. But before you make a decision, let's see how to implement PMD in a project. Here we are in the Code Quality project, which you can find in the Gradle Hero GitHub repository, linked in the notes below. This project has a class with some deliberately bad code. So let's see if PMD can give us some suggestions to fix it. Let's apply the PMD plugin and add the Maven central repository since the plugin defines some dependencies. With this in place, we can run the check task with -- console equals verbose. It includes the PMD main and PMD test tasks registered by the PMD plugin. These validate production and test code. It's passing right now since no rules have been applied. Let's fix that by configuring the PMD plugin's rule sets property. In PMD, a rule set is an XML file containing a list of individual rules. The nice thing about PMD is that it comes with predefined rule sets which you can easily apply to a project. Find a link to the PMD website in the notes below. For example, here's a best practices rule set. You can see all its rules on this page, but what we need is its XML file location. Copy the location and paste it into the build script. Now when we run check, we get a failure due to a PMD rule violation. In the linked report, there's an error because we're using system.out.println. Click on the link to see why PMD thinks that's a problem. Let's also add the codestyle.xml rule set and run check again. Now we have more violations, including one for the unused import. If you need more control over the exact rules that PMD applies, you can set up your own rule set XML file. Let's create pmd-rules.xml in the root of the project and add the expected PMD format. Within the rule set element, we can add rules directly from the PMD website. For example, within documentation rules is comment required, which we can copy into our XML file. Reference the XML file from the PMD configuration by setting the rule set files property. Run check again, and this time it fails due to lack of comments. With hundreds of rules available, you're free to customize your rule set to your specific requirements. Here are the key takeaways from this lesson. Apply the PMD plugin to check your code quality. The PMD main and PMD test tasks validate your code when you run the check task. Specify the rule sets property to use built-in rule sets provided by PMD. Alternatively, define your own rule set XML file and set the rule set files property. See you in the next lesson. If you're writing Java applications to run in the cloud, there's a good chance you'll need to package it up inside a Docker image. Once you've built and pushed your image, it can then be deployed to services like Kubernetes or AWS Elastic Container Service, which will run and manage your application as a Docker container. So how can you build and push a Docker image with Gradle? Well, fortunately, several options exist in the form of third-party Gradle plugins. In this lesson, we'll specifically focus on one of these, which is the best choice if you're building Spring Boot applications. The Spring Boot plugin we explored in Chapter 4 can already build images with its boot build image task. This packages your application's jar file inside a Docker image using a technology called Cloud Native Build Packs. This uses best practices to ensure the image that's built is most suitable for your application. For example, it picks the most appropriate Java runtime environment version. The other great thing is that there's no need to maintain a Docker file. You can configure the boot build image Gradle task to customize your Docker image to your requirements, as you'll see shortly. Finally, the task will publish the image to your Docker registry of choice, whether that be Docker Hub, AWS, or anywhere else. So let's explore how to build and push a Docker image for a Spring Boot application using a simple project whose repository is linked in the notes below. This application is already set up with the Spring Boot plugin. When we run Gradle w boot run, it starts up, prints an amusing string, then exits. With this in place, to build a Docker image is as simple as running Gradle w boot build image. This by default uses the project name as the image name, which in this case is imaginatively called Docker image. We can now run the image with the docker run command passing the image name. I'll also pass --rm to clean up the container once it's stopped. The Spring Boot application starts up, prints out the message, then stops. The base image used by the Spring Boot plugin also prints detailed memory information on shutdown. As you can see, it's very simple to get your application running in Docker. But what ways do we have to customize the Docker image? There are quite a few, so I definitely recommend checking out the documentation linked in the notes below, but let's run through a couple right now. First, the image includes a Java runtime environment to match the Java toolchain configuration. For the image we just built, that's Java 17. But if we switch the Java toolchain from 17 to 11 and run boot build image again, in the output we can see that it's now using version 11. All the configuration here can be customized. For example, we can override the JVM version by configuring the boot build image task and setting the environment property like this. You can also add Java command line options by setting these key values. If we rebuild the image and start a container, you see the configured option printed out at startup. Now let's look at how to publish an image to a remote Docker registry. In my case, I have a repository already set up in AWS's ECR service called Docker in Gradle. Here's the URI of the repository, which we'll have to configure in our Gradle build to override the default image name. Do that by setting the image name property of the boot build image task, including the latest tag. And within Docker, publish registry, we configure a username and password. For ECR, the username is always AWS, and I'll provide the password using a project property on the command line. So let's run boot build image, this time passing a special --publish image option to tell the plugin to also run the publish step. We'll pass the Docker password property using a value I have stored in a variable. We see console output confirming the image push. The AWS console also says it has the new image, which is now ready to be deployed into any environment using your container orchestration tool of choice. And everything we've just discussed about building and pushing Docker images with Gradle should be set up to run in your continuous integration pipeline. Here are the key takeaways from this lesson. To build Docker images for Spring Boot applications, use the Spring Boot plugin. The boot build image task builds a default image without the need for a Docker file. To push an image, configure the task's image name and Docker registry credentials, then run the task with --publish image. See you in the next lesson. When you use enough dependencies in a project, you may start to notice duplicated versions. Duplication can happen within a single project, like when declaring JUnit Jupyter dependencies, or between subprojects which need to use the same versions of dependencies. Until Gradle 7.4, there wasn't any fully supported way to centrally manage all these dependency versions. Now we have the version catalogs feature, with which you can centrally define dependency coordinates, then refer to them from any build script in your multi-project build. So in this lesson, you'll learn how to create a version catalog in your project's settings file, specifying versions, libraries, and plugins. Use a version catalog by referring to libraries and plugins from build scripts. Use the alternative TOML syntax, and use bundles to easily define multiple dependencies at once. Here we are in a multi-project build based on the Theme Park Manager project from Chapter 5. There are two subprojects containing dependencies, API, and service. First, we'll centralize dependencies from service. The way to do this using the Gradle APIs in code is within the settings file. We call dependency resolution management, then version catalogs, then create a named catalog which normally is called libs. Now define whatever libraries we need with an alias and a group name version string using a colon separator. The alias we'll use in a moment as a way to refer to the library from the build scripts. Repeat the process for the other dependencies. In Services build script, we can now refer to the required dependencies using what's called a type-safe accessor. This is the version catalog name, followed by the alias we just declared. Dashes are replaced with dots, so for example, JUnit Jupyter API becomes junit.jupyter.api. Notice that in the version catalog, we still have some version duplication, which we can remove by defining a named version. You can refer to a named version within the version catalog or even from a build script, and it comprises an alias and version string. To use the named version for the JUnit Jupyter dependencies, we have to remove the version and split the library group and name. Then provide the version by reference by calling version ref. That's the service subproject sorted, so let's move on to API. Right now in API, we only have one dependency which can benefit from version catalogs. This Spring Boot Starter Web dependency uses a version set by the Spring Dependency Management plugin, which in turn gets its Spring Boot version from the Spring Boot plugin. Let's move all the dependency, version, and plugin information to the version catalog. To define a plugin in the settings file, call plugin passing an alias and the plugin ID. The version is then specified by calling the version method. Use this process for both plugins. Back in the build script of the API subproject, to apply a plugin from a version catalog, call alias, passing the catalog name libs, then plugins, then the plugin alias. Next, in the version catalog, define a library for Spring Boot Starter Web. In this case, since we're using the Spring Dependency Management plugin to set the version, we can call .withoutVersion to tell Gradle that no version is expected at this point. And reference the library in the build script using the syntax we used earlier. Run Gradle wbuild and we see that everything's building okay, with all the dependency and plugin versions extracted into the version catalog. When using version catalogs, my recommendation is to ensure all dependencies are defined in the version catalog. This means there'll be a single source of truth, and it will avoid any confusion figuring out where to define dependency group name and versions. There's an alternative version catalog syntax using a .toml file, which stands for Tom's Obvious Minimal Language. Nothing to do with me, I promise. TOML was specifically designed for configuration, and the files consist of sections of key-value pairs. But the values can not only be simple types like strings, booleans, and dates, but also complex types like lists and maps, as you'll see shortly. If you're using IntelliJ IDEA, you can download this plugin to provide syntax highlighting for TOML files. So let's convert our version catalog to TOML syntax. To do that, in the Gradle directory, create a libs.versions.toml file. Within this file, versions, libraries, and plugins are all split into their own sections in square brackets. The libraries we define as simple key-value pairs. The key is the library alias, then use curly brackets to define a map. That contains a module key and value of the group and name separated by colon. And then provide either a version or version.ref key value. And we can define the JUnit 5 version in the versions section using a simple string value. I'll repeat this for all the other libraries. Note how for Spring Boot Starter Web we provide an empty version, since the version is actually handled by the Spring Dependency Management plugin. Finally, we define the plugins in a similar way, but specifying the plugin ID rather than a module. Delete the version catalog in the settings file, and run the build again to check everything is okay. So how to decide whether to create your version catalog in a TOML file or within the settings file? My recommendation is to use the TOML syntax as it's more structured and completely independent from other settings configuration. One last thing to see before wrapping up this lesson is another type of entity you can declare in a version catalog called the bundle. A bundle is a group of dependencies you can refer to by a single alias to apply them all at the same time. To show you how this works, let's bundle up the JUnit Jupyter API and params libraries. Although these libraries don't always go together, let's assume within this project they do to demonstrate this concept. Within a new bundles section in the TOML file, define a bundle alias, and the value should be a list of all the library aliases to include within that bundle. In the build script for the service subproject, note that a bundle is applied to a single dependency configuration. To do that, refer to libs.bundles, then the bundle alias, once again with dashes replaced with dots. Now our build script is slightly less verbose thanks to the bundle. Here are the key takeaways from this lesson. Use a version catalog to centralize dependency group name and version information. Create a library for each dependency with an alias you can refer to in the build script. Create named versions and refer to them from libraries to ensure versions aren't duplicated. Define plugins in version catalogs using the plugin ID and refer to them in build scripts by alias rather than ID. And define bundles in version catalogs to group commonly used dependencies together. See you in the next lesson. Congratulations on reaching the final part of the Gradle Hero course. If you've completed all the previous lessons in full, then you now have the knowledge and skills to finally take back control of your Gradle build. Let's quickly recap what you've learned in the course. You now have the mental model and understanding of the Gradle foundations to have confidence working with any Gradle project as well as making sense of documentation. You've mastered interacting with Gradle projects in the most effective ways via the command line and the IDE, as well as getting an understanding of how Gradle works in the background through the 3 stages of the build lifecycle. You're proficient in all important aspects of the build script in Groovy and Kotlin, allowing you to write and maintain build scripts using up-to-date best practices. You've got a professional level understanding of how to create Java projects in Gradle, from building and testing to publishing, running and configuring your project to meet your requirements. And remember, you know how to build Java applications and libraries. And you've learned the tools of the trade when it comes to being able to scale up your Gradle project, with knowledge of multi-project builds and promoting build logic reuse with tasks and plugins. Of course, everything you've learned you can now apply to your own Gradle projects. If you've yet to start any of your own, then you can now be confident to kick one off on the right foot using all the best practices. If you are currently involved in a Gradle project, though, here are 5 pointers to take what you've learned and translate it into improvements in your project. Can you streamline how you interact with your Gradle build? Are you using the Gradle wrapper? Is your Gradle version up to date? And are you making full use of the IDE integration? A few seconds saved on each repeated task could translate to minutes or hours saved per week. Are you following best practices you've learnt for building Java applications? For example, are your dependencies declared against the correct dependency configuration? Are you making the most of available plugins like the Application plugin, Java Library plugin, and Spring plugins? Do you have any opportunities for making your Gradle build scripts more readable and maintainable? This could be as simple as clearer organization of the build script or extracting common logic into convention plugins or custom tasks. Are you working in a single module project? There's nothing necessarily wrong with this, but if you're constantly hitting problems with maintainability or slow builds, then consider moving to a multi-project setup. And finally, do you now have the confidence to implement some of your own ideas that you had been putting off due to lack of understanding of Gradle? These kind of ideas might start with, wouldn't it be great if, or I wish our build could. Well, the chances are these things are possible in Gradle since it's such a flexible build tool. Now you've got a solid foundation, you should feel more confident browsing official documentation and plugins, which will help you come up with a plan to nail these kind of big wins. Once again, congratulations, and thank you for joining me on this course. Now it's time to put everything you've learned into practice and take back control of your Gradle build.